You hear me?
Yes, we can hear you.
Okay. So yes, please let me know when I can start.
Yeah, share your presentation. Share your slides.
Yeah.
Thank you.
Yes. So can you see my slides?
Yeah, it is okay.
Okay.
A moment,
So
a moment.
yes.
Okay. So good morning. So welcome to the last day's session of the Zeldovich meeting. And we are very happy to welcome Maria Denotti. I think you are working in Japan, yes?
Yes. Currently
Yeah.
I'm at NOJ, the National Astronomical Observatory of Japan.
Oh, okay. So she will talk about the gamma ray burst as a cosmological standard, also very important with new statistical assumption for dark energy. Very interesting talk. So please start. Thank you.
Okay, thank you very much. So I would like to start by saying that it is important for GRP cosmology to have standard features. And in the past few years, we have been hearing a lot of discussion and talks about peculiar gamma ray burst. But for cosmology, standard is good. And one of the features that are pretty much standardizable in the GRB afterglow is the plateau features. So this picture shows the one of the example of plateau emission with the Swift telescope that at the moment is not working, but some reorbiting strategy has been applied. So we hope that in a near future, Swift can still restart the observations. And the plateau has been observed for most of GLBs, around the 60% of cases. But why are we going to choose the gamma ray burst standard plateau features? Because compared to the prompt emission, they are less varied. And the next question is that what it is the standard set of GRBs to be used? For example, if we focus on the plateau emission properties. And we have already established that most of cases we have the plateau emission. This analysis that I'm going to show you, it has been done thanks to the work of several collaborators, and this is coming from the work from Srinivasa Varagan, myself et al., in which we have also updated the sample, and the new update of the sample has been found in this paper by Narendra et al. 2026 for the machine learning analysis. So we have an update that goes from January, February 2024 until the end of 2023. So we have a sample of 255 GRBs. But as you all know in the audience, that this analysis of the 2D relation, which correlates the luminosity at the end of the plateau emission and time at the end of the plateau emission, didn't come overnight. This has been a work that started in 2008, and then it was also completed and actually expanded with other observers and other astronomers. For example, there is the Ots relation in optical domain. This relation has been corrected for selection biases, and then we added the third parameter, which is the peak prompt luminosity in the prompt emission, that it is correlated with the luminosity at the end of the plateau emission. And since those two variables are already correlated, basically we could combine these three variables to obtain the fundamental plane relation that I will show you in a moment. Those correlations, both in X-ray and optical and in 3D, are reliable because even after we correct for selection biases, those stand as reliable relation. And indeed, we extended both relations in 2D and in 3D, also in optical, and we have also the extension of the 2D relation in radio. So this is the timeline, and of course, this is continuing here. The advantage of having this three-dimensional relation is that we are tightening up the correlation. So why it is so important? Because for GRB cosmology, not only we would like to have as many GRBs as possible, but also we would like to have as tightest as possible with the highest correlation our variables correlated. In this case, we can see that this shaded region is the fundamental plane. Those colorful points are the several classes of GRBs. Here we have the canonical short gamma ray burst, the X-ray flashes, that they have the ratio between X-ray and gamma ray greater than 1, the purely long gamma ray burst for which a supernova 1BC has not been associated, and this triangle for which the supernova has been seen. But now we can see from this plot that the long, purely long gamma ray bursts, they are sticking closer to the plane compared to the other classes. And because of that, we focus on this long gamma ray burst. So in this way, we could reduce the intrinsic scatter further by 24%. Then we used a subsample of gamma ray burst that we called gold gamma ray burst with very defined plateau features, so almost a flat plateau with enough data in the plateau. We definitely redefined this gold sample in a platinum sample in which you have enough point in the plateau feature. What are the two solutions that allow for independent calibration? This is very generic. So first, we can have a simultaneous fitting. So we fit simultaneously the correlation parameters and the parameters of a cosmological model that it is of our interest. And the other possibility is that we calibrate gamma ray burst with low redshift probes, for example, cosmic chronometers of supernovae. So the assumption is that the objects at the same redshift should have the same luminosity distance regardless of the underlying cosmology. This paper that was published in 2023 showed the combination of gamma ray burst plus supernova plus bioacoustic oscillation before the DESI release. We can see that the cosmological parameters actually agree with the standard cosmological model with omega m around 0.31 and H0 around 69.70. But the question that comes to our mind when we look at this corner plot picture is that whether are the supernova 1A, which is the most numerous sample, that drives these results. And I would like to point out also to a similar analysis that has been carried out by Wang et al. 2022 in APJ in the context, instead of the two-dimensional relation, with the inference of the cosmographic parameter, the jerk, and the Q0 parameter. So the point is that we need to consider if we are using a Gaussian prior or uniform prior around the value of omega m and H0. Now, if we use the Gaussian prior, we indeed see that the parameters of omega m and H0 are recovered in terms of the standard lambda CDM model. And this plot on the left-hand side is obtained by varying only omega m with evolutionary function. So it means that when we consider selection biases, we should also include these selection biases into the analysis of cosmology. And when we consider omega m and h0, that they both vary with evolutionary function, but we know that basically h0 is independent from this evolution, but the dependence of this evolution is carried out by omega m. So the problem here is that yet if we would like to relax this condition of the Gaussian priors, then we have somehow issues in the sense that gamma ray bursts at the moment cannot tightly indicate and constrain cosmology. But the very interesting point that we can see here from this plot on the upper side is that if we run this analysis 100 times, we have that the omega m parameter are shifted at larger value, the same for h0, and the value of W is slightly smaller than -1. So this is without considering the evolutionary effect, and if we consider fixed evolution, we see similar trend for omega m h0, and the value of W is more aligned with the -1, that it is compatible with the lambda CDM model. So the tension actually increases compared to the tension that we see between Planck and supernovae, but the error bars are larger and the central values are actually closer to the value of supernova 1A. If we consider instead the evolutionary function, we still see that omega m is shifted at larger value. In this case, we are using very wide uniform priors that goes from 0 to 1, so we are almost in the De Sitter universe, or a universe that is completely filled with matter. But if we consider the limit to omega m to values that are 5 sigma to the current values in the literature, we are going to have much tighter constraint, as I've shown in the previous picture. And if you consider the evolution and the cosmological parameters varying together, you see that this value of omega m is even shifted at larger value. Now, how can we cast light on the Hubble constant tension within this situation of uncertainty? First of all, we strive to reach precision cosmology, but the problem is that we have some assumption on the likelihood, which are the Gaussian likelihood for the supernova and BAO. But are all these like valid as well as quasars? The answer is not. So in fact, you can see that the best fit for the Pantheon sample, which is a collection of 1000 supernovae, is the logistic distribution, while for the Pantheon Plus is the T-student distribution. And here you can see that those two distributions differ, and they are also heavily tailed distribution. So when we apply this analysis, we need to take into consideration of this distribution. In fact, we have to define the logistic distribution and the T-student distribution, and so we have inserted a new parameter, which is the variance, that it is defined in this way with the scale factor. So we see that they depart from the Gaussianity assumption, and in the case of the T-student distribution, we have that the gamma function plays a role together with the degree of freedom, and this variance that it is also related to the degree of freedom and the scale factor. So we leave all these parameters free to vary in our analysis, but we have also fixed those values and we have checked that the results remain consistent. So I would like to also to point out that I said that the most numerous are the GRBs, or the sample the most we can get from cosmological parameters, but also, as you can see, what it matters is also the scatter here at the denominator of this function, so that the scatter matter the most compared to the rest, compared to the number, as we can see from this function. When we consider the result for omega m and the h0 within a flat lambda CDM model, then we can see that the logistic and the t-student significantly reduce the uncertainty on both the cosmological parameters. We have a reduction of omega m by 43% and 41% for H0 respectively. So it goes the uncertainty from 0021 to 0012, and for the case of H0 from 034 to 020. And for the t-student distribution, we go the reduction by 42% in the case of omega m and 33% in the case of H0. But regardless of the number, I would like to show you how this visually is really impactful, because you can see that both the logistic distribution and the t-student distribution, they provide much smaller contours. So this is a pretty leap forward in the constraining of cosmological power, and this is without using additional data. I will not present today, but there is also a new collection of data. The supernovae, I'm happy to provide this data, and we can definitely start a collaboration together. Now, with this new statistical assumption, we have to correct for this non-Gaussianity likelihood for the supernova and the quasars, because the quasars are affected by the same issue. And when we consider all the probes together in a non-flat lambda CDM model, but also with a flat CDM model, but also we used the regular lambda CDM model, we can see that with this delta percentages, the reduction of the uncertainty that we have in these cosmological parameters, you see here that are all negatives, with the only exception of this value when Pantheon Plus is considered with no evolution, but because we know that the proper analysis will involve varying the evolution, so this is the last line here, we can see that there is a decreasing in the scatter that goes from 17% up to 34%, and the same for the Pantheon. When we consider the Pantheon Plus analysis, we have this similar reduction in scatter. So this is the advantage of combining all the data together, but also with the new likelihood assumption. And I mentioned in the beginning of the talk that there is another way to calibrate GRBs, for example, with the cosmic chronometer. And this paper now has been accepted in Journal of Energy Astrophysics, in which we use this correlation, the 2D relation, because we saw that basically the B parameter of the 3D relation goes towards zero. And the very important point in this analysis is that currently the 2D relation, that it is calibrated, the cosmic chronometer, managed to reach an intrinsic scatter of 0-20, which is actually comparable with the Epike-ISO relation, which we have already seen that depends on the sample size and reaches also larger value according to Liu et al. 2022, Liang et al. 2022, and Li et al. 2023. This is the value according to the larger sample. So we can trust this platinum sample for GRBs to have meaningful cosmological parameters. Indeed, this is comparable with the fundamental plane relation when we consider also the changing of the evolutionary parameter. And here we have this sigma intrinsic scatter that reaches even 0.18 plus minus 0.09. So what else can we do for GRB cosmology? At this stage, of course, we can increase the sample size. We can have additional cosmology independent approaches. We can also find new or tighter relation. And of course, the physical interpretation is very important, and also how to connect with the theory in the quest of the standard set of gamma ray bursts. Now I would like to give you some forecast, because the point is that how many gamma ray bursts do we need in the future to be much more powerful in constraining cosmological parameters? It depends, because if we use the optical sample, we may need 1,000 gamma ray bursts with a given precision, but if we consider also the optical GRBs, but with uncertainty that are divided by 2, we may settle for a smaller value of the GRBs, around 300. And I would like to summarize this in relation to the precision. So the good news is that we have already achieved a precision that was achieved with the supernova 15 years ago, and we achieved this precision already 2 years ago. This is the precision of Colli 2011. The precision of Betulle that was achieved basically 12 years ago, it has already achieved now. And if we want to achieve the precision of Skolnick that was achieved 6 years ago, then we need to wait 16 years. But worry not, because this is a pessimistic approach. And in these days, we are actually working very actively on the machine learning analysis and the light curve reconstruction so that we can reduce further the parameters of the correlation, but also have a larger prediction for the number of gamma ray bursts with redshift, and so the number of years that we need to wait are going to be reduced. But now going back to the equation of state, because I mentioned in one of the previous slides that it is irrelevant to understand how W can change according also to this forecast. So if we have this sample that we trim a posteriori, so we want to say how many GRBs we need very close to the fundamental plane to have a given uncertainty on W, and this is our results. So we can see that on the left-hand side, the uncertainty are derived from a mock sample of 2,300 simulated GRBs, and this simulation is based on varying the parameter A and C and the sigma intrinsic scatter, so we are using the two-dimensional correlation. And when we see on the right-hand side, we have the optical sample. So we can see that the optical sample basically reaches a slightly smaller scatter, because you see you have 0.09, but we have also quite some uncertainty. So I would say that for the value of W, it is rather similar, the analysis with either the optical or the X-ray. And if you would like to check more information on this paper has been posted in archive in March of this year. So our question was, can we be competitive with the Planck alone? Definitely yes, because with already a sample, with the current sample of roughly 50 GRBs, we already reached the same precision as Planck, that it is highlighted by this horizontal line. But if we would like to check the precision of DESI, that it is again this horizontal line, then we would need around the 700 gamma ray burst. So now, around 600 gamma ray burst. So what it is the forecast with the GRB alone, if we consider without Planck value? Basically, if we consider the transfer learning analysis, that it is a technique we are using indeed these days to increase the sample size, we only need actually 5 years from now to reach the same goal of having Planck measurement uncertainty reduced. And if we vary all the correlation together, the parameters together. But if we fix actually the C parameter, that it is normalization, and we use a calibration, then we can reach this constraint even now, as I have shown before. However, if we would like to test gamma ray burst as probe of the dark evolving energy model, so if we want to change W0, WA contemporaneously, this is going to be very challenging, and we have to wait 30 years from now, which means that we are not very, how to say, appealing in this regard. However, this is in consideration with the X-ray. However, if we use the optical sample, you see that the situation when we want to reach the Planck analysis is similar to the X-ray, and it is less constraining if we consider the W0, WA varying together. However, if we consider simulation also with the Planck data, basically what we can see is that we cannot constrain W0, WA contemporaneously, but if we leave W as a parameter free to vary, then we are able to actually check evolution of dark energy model, and this is going to be reachable with the transfer learning analysis in really a few years from now, 6 or 7 years, when we consider the calibration with the other probes. If, for example, we consider W0 is fixed and we want to check what it is the variation of WA, we can reach this even in the same amount of years, so we can still have an indication of dark energy models. But one can ask what it is actually the indication with the zeta score about this W0 WA model, and you can see that you can have a difference, a departure from the lambda CDM model when you have around 700 gamma ray bursts. You can see that you already have a zeta score of 1.5. Of course, if you increase the number of GRBs, you are going to reach a zeta score of 2, but this would require 4,000 of GRBs, so it's not meaningful. We can be settling ourselves for this number of GRBs and being happy to reach these goals in few years from now. These are the table of the mission for which we did the computation of the forecast. Some of them, unfortunately, have not been selected, like Strobe X and Theseus, but there is a discussion in the community that Theseus can be connected maybe with IZ Gundam, and then we can see also many more GRBs at high redshift in the near future. And also we are going to have Ultimate Subaru that is going to also observe 8 GRBs per year. And again, IZ Gundam 47.5. But also we will have the Vera Rubin Observatory with the Orphan Afterglow are going to be really considerable number, around 1,000. So another point, because now my time is almost finishing. So I would like to tell you that there is also possibility not only to provide the cosmological parameters, but also with the correlation, the dynamic relation, also to consider whether or not we have dipole information. And when we consider the long gamma ray burst, X-ray flash, and X-ray reach, or the combined sample, we can see that this dipole parameter, they depart from the value of 0 that you would expect, in which no dipole is present. And in this analysis, we did 2 methods, anisotropic residual and full sky and fixed direction. And we also practically considered the comparison in the literature. So what it is going to be next? We have to update the sample with the largest optical catalog, because this is something that has not been done yet. And again, this is an invitation to the community if people would like to join this effort, and also concern more with the physics and machine learning method. So thank you very much for your attention. Can you hear me? Hello? Am I audible?
Okay, now you hear me?
Yes, yes.
Okay, thank you, Maria, for the talk. My question is, in your forecast, what is the impact of the GRB luminosity function?
Yes, thank you very much for your question, because in this forecast, we have considered the basic analysis without the evolutionary effect. So we did this for simplicity, because we wanted to have first an estimate of how many do we need. And of course, if you consider evolutionary effect, this number is going to be slightly larger than that. But because now the goal, I mean, the primary goal of this forecast was to see whether or not, with the machine learning analysis, we can actually reduce this number of GRBs needed, and how many more years we can gain. And in fact, currently in these days, we have already checked that the prediction is going to increase for 20%, and also the sample is going to increase of 20%, but we are we are striving to have more precision and also a larger sample. So this kind of estimate are conservative, I would say, but yes, they don't take yet into account this evolutionary effect. So your question is very relevant, because then if luminosity function departs, then we may need more data. Thanks.
Any other?
Yes, we would have liked very much to have you here to discuss and to have the pleasure to see you, but also to indicate you some progress we are making about the general light curve of long GRB and also short GRB. We will come back to you and indicate some of the new region which we find some new interesting feature, correlated also in some cases with your relation, the Dynoti relation.
Okay, that would be very interesting. Yes. Thanks.
Okay, any others? Okay, no. And Maria, you may be interested in the next talk.
Yes, of course.
Fatima used the machine learning to find many correlations, and I also checked your correlation, your famous correlation. Thank you. Thank you.
Okay, thank you. Thanks.
So now let's to the next speaker, Fatima.
Hello, everyone.
Okay. We can hear you and we can see you.
Okay, thank you. And how can I share my screen? Sister Mander, could you give me the permission to share my screen?
He's working on it.
Okay.
Fatima, can you share?
No.
Oh.
Let me. Okay.
Okay, good. So please start. Okay, we can see your slides.
Okay, good morning, everyone, and thank you for being here. I am Fatima Rastegarnia, and I'm a researcher in ICRANet. Before starting, I would like to thank my dear collaborators, Dr. Rahim Moradi, Dr. Wang Yu, Burwa, and Mohsen Asadi. And today, I'm going to talk about the prompt plateau correlation in gamma ray burst and using one of the very interesting machine learning methods, which is symbolic regression. And then I'm going to talk about the ranking of the correlation that we achieve. Let me briefly outline the structure of my talk. First, I'm going to talk about our motivation for doing this research. By reviewing the X-ray plateau and the classical Dynoti relation. And I will explain why we ask whether it is truly the best, whether it is truly the best low dimensional description of data, or it is the projection of a fundamental and higher dimensional relation. After that, I'm going to describe our research strategy, and I will explain how we analyze a sample of 251 gamma ray bursts and used a symbolic regression to systematically explore hundreds of candidate relations. And then I will present the main result, which is really interesting, and I will show how the analysis naturally extend the classical two-dimensional dynody relation into three-dimensional prompt plateau plane by introducing the prompt peak luminosity. And finally, I will discuss the robustness of the result, including the statistical tests we perform, the role of the distance effect. The story is after the prompt emission, many GRBs do not immediately follow the simple fading behavior. Instead, their X-ray light curve often enter to a shallow plateau phase before transitioning into the standard power law decay. And this behavior suggests that central engine may continue to inject energy into the relativistic outflow after the prompt emission has ended. So several physical mechanisms have been proposed to explain these prolonged activities, and including the magnetory spin down, a fallback accretion, or other form of the long-lasting energy injection. And at this stage, we do not need to assume any particular physical model. What is important for us in our work is that the end of the plateau provide us two directly measurable quantities. One is the plateau luminosity, and another is the rest frame plateau time. These two observable are connected through one of the best known empirical correlation in GRB studies, which is the dynody relation. This relation shows an anti-correlation between the plateau luminosity and its duration, meaning that the brighter plateau tend to end earlier. Dynody relation has been extensively studied and has become an important tool for investigating the GRB's physics. Despite its success, an important question remains. Is the dynody relation truly the most compact description of GRB plateau data, or is it simply a two-dimensional projection of a more fundamental high-dimensional relation? To investigate this question, rather than assuming a particular mathematical form, we use symbolic regression, which is an interpretable machine learning approach that searches simultaneously for both the variables and equation that best describe the data. Here in our research, we assembled a sample of 251 swift gamma ray bursts covering both the prompt emission and the X-ray plateau phase. And our target variable is the plateau luminosity. Since this is the quantity that we ultimately want to predict and understand, and after that we consider 13 candidate predictor, including the plateau duration, prompt, peak luminosity, spectral and temporal parameters, intrinsic absorption, and several physical motivated combination of this observable. And rather than selecting variables by hand, we allow the algorithm to explore every possible combination up to 3 predictors. This resulted in 377 different feature space, and each representing a candidate search space for symbolic regression. And throughout this work, all luminosities and time are considered, are expressed in base 10 logarithm. And one important point is that both the plateau luminosity and prompt peak luminosity contain the same luminosity distance term. Therefore, any apparent correlation between them could be partially driven by distance rather than intrinsic physics. For this reason, testing the impact of the common distance dependence become an essential part of our analysis, and I will return to this point later in my presentation. And now let me briefly explain what we mean by symbolic regression. Let me explain it in this way. When we are talking about the conventional regression analysis, we first choose the mathematical form of the model. For example, we consider a linear model, and then we try to estimate the best fitting coefficient. But in symbolic regression, instead of prescribing the equation, we provide the algorithm with a set of candidate variables and a collection of mathematical operators like addition, multiplication, division, logarithm, and square root. And the algorithm then searches simultaneously for both mathematical expression and its numerical coefficient while balancing predictive accuracy against the model complexity. And so you can see that in this diagram, you can see what the algorithm works. First, we feed the algorithm with some set of variables and collection of mathematical operators, and then the algorithm started to generate many candidate equation, and then it started using the errors estimation. It's try to test the accuracy and the simplicity of the equation, and then gives us the most readable and best equation. And an important advantage of this approach is that the final result is not a black box prediction, but an explicit analytical equation that can be interpreted physically. So, in this view, the question, in other words, instead of asking, what are the best parameter for our equation, we ask, what is the simplest equation that best describe the data? And this is really important. In our analysis, we trained the symbolic regression using 75% of the sample and evaluate its performance on the remaining 25%, and using the validation mean absolute error as the primary metric for ranking the candidate relation. And after the symbolic search identified the most promising functional form, then we re-estimate their coefficient using a conventional regression method and perform additional statistical tests to evaluate their robustness. Before searching for new correlation, we first want to validate our approach. To do this, we perform an anchored symbolic search, forcing the rest frame plateau time to appear in every candidate equation. And also we started the simplest possible case, using the rest frame plateau time as the only predictor. As you can see here, I cannot use my, it's okay. Okay, as you can see here on the left, the left equation, the symbolic regression naturally recovered the classical Dinoti relation, and this is a very, very important validation because the algorithm was not given a functional form of the relation in advance, and this relation is identified directly from the data. And then we refitted, and then we refitted the same functional form using D'Agostini error in variables. This is another regression method to obtain a final coefficient and intrinsic scatter. The coefficient, you can see the coefficient are slightly differ, differ slightly, because the symbolic regression is designed to discover the equation, and but the D'Agostini error in variables regression is used to estimate the parameter while accounting the measurement are uncertainties. And although the known Dinoti relation is successfully recovered, but as you can see, the intrinsic scatter remains relatively large. It's about 0.82 dex. And what does it mean? This suggests that the two-dimensional relation, the classical Dinoti relation, does not capture all available information. So in the next step, we remove the anchored and ask whether introducing another observable can explain part of remaining scatter. This is the equation, and this is the important point. Now we remove the anchored and let all candidate variable to compete under exactly the same search procedure. And here you can see in this plot, here you can see the 377 feature that the symbolic regression find through the variables and using the mathematical operator. These are our feature subset and are ranked according to the validation mean absolute error. And you can see on the left lower part of the plot, you can see the best prediction symbolic regression made for us. And so the lower values indicating the better predictive performance. And so the best performing relation was the prompt plateau plane. And the important point, the important result is that the classical Dinoti relation also remains highly competitive among these 377 relation, which is have the score, the rank of 87, and with R square 0.53. Now the question is, which variables appear most consistently among the top model? You can see in this histogram. You can see, you know, that in this histogram, you can see that how often each variables appear in the top 20 symbolic regression model, and the prompt peak luminosity appears in all 20 leading model, making it the most consistently selected predictor. And also, what does it mean? This tells us that prompt emission contains additional information that is not captured by the classical Dinoti relation. And also you can see the plateau duration, the plateau rest frame time duration is also selected frequently, while the remaining spectral absorption and afterglow parameter appear just only frequently. So the symbolic regression naturally extends the Dinoti relation from 2D correlation between plateau luminosity and plateau duration to three-dimensional prompt plateau plane, where the plateau luminosity depends on the plateau duration and prompt peak luminosity. And here I will present the equation of this newly identified relation. You know, after finding the prompt luminosity, prompt peak luminosity, and as the key additional variable, now we examine the best relation discovered by a symbolic regression. Here you can see the winning expression, which is the three-dimensional prompt plateau plane, and achieved by the symbolic regression. And this relation naturally extends the classical Dinoti relation by adding information from the the prompt emission through the peak luminosity, while preserving the anti-correlation with the plateau duration. The positive coefficient of the peak luminosity indicates that brighter prompt emission is associated with brighter plateau, and the negative coefficient of the rest frame time duration confirms the longer plateau corresponds to lower luminosity at the plateau end. And this model achieves the validation root mean square error of 0.45 and the R square of 0.88, and meaning that the prompt plateau relation explains about 88% of variance in the plateau luminosity. After identifying the variables and the functional form, now we refine the relation using the conventional regression in order to obtain the more compact and more interpretable equation. And I have to add that this relation that is achieved by symbolic regression has the same structure as the 3D Dynoti relation, which is published in Dynoti et al. In 2016, 2017, and 2022. But the main point is that the algorithm didn't assume any Dynoti relation, and it identified this relation directly through the data. And another important point is that the symbolic regression discovered the structure of correlation, while the conventional regression provides the statistical characterization. After identifying the prompt plateau relation with symbolic regression, now we perform an independent conventional fit on 246 complete bursts using another method, which is ordinary least square, and we obtain this following equation. And as you can see, ordinary least square method also recovered the three-dimensional Dynoti relation. And this relation gives a Pearson correlation coefficient of 0.90 and explain about 82% of variance in logarithmic plateau luminosity for the observed sample. In this 3D plot, the left one is the observed three-dimensional plane, while the right plot shows the same structure even after removing the common luminosity distance dependence. The obtained relation is quantitatively consistent with previous reported three-dimensional Dynoti planes, and the coefficient of prompt peak luminosity is around 0.8, is somewhat higher than some previous estimates, which can be related to difference in sample selection, calibration, fitting methods, or evolutionary correction. However, this raises an important question. How much of this apparent plane is intrinsic, and how much is simply caused by the shared luminosity distance dependence? To answer this question, we perform a distance residualization test. The problem is that you can see here the plateau luminosity and the plateau and the prompt peak luminosity share the same luminosity distance, so we have to remove this connection to be sure that the correlation between them is come from their physical connection. So for each luminosity variables, we first fit its dependence on the logarithmic luminosity distance and then subtract this fitted distance trend, as you can see here in these plots, and then leaving only residual luminosities. Then we repeat the correlation analysis using these residuals while keeping the rest frame time duration time unchanged because it is not directly depend on the luminosity distance. And after that, after removing the common distance trend, the performance of the relation you can see obviously decreases, and the coefficient of R square, as you can see here, drops from 0.82 to 0.62, while the root mean square error increases from 0.53 to 0.56. What does it mean? This tells us that the luminosity distance does contribute significantly to the observed correlation. However, the relation does not completely disappear. A substantial correlation remains ever after the distance effect has been removed. And this suggesting that the prompt plateau relation cannot be explained only by a sheer luminosity distance dependence. It is important to note that this is the only distance control diagnostic, and it does not correct for other observational effect, and such as selection bias or population evolution. Therefore, in the next part of the analysis, we perform additional validation tests and resampling analysis to further evaluate a robustness of this relation. After examining the effect of luminosity distance, now we perform 3 additional tests to assess the robustness of the prompt plateau relation. First, from the left, first, we repeat the fit using D'Agostini error in variables method, which accounts for uncertainty in both variables and include an intrinsic scatter. The resulting slope are consistent with the ordinary least square fit, and with an intrinsic scatter about 0.51 dex. This confirms that the relation is not strongly dependent on the choice of the fitting methods. And then, as the second test, we perform a partial correlation analysis by controlling simultaneously for luminosity distance and plateau time. And the remaining partial correlation between prompt luminosity and the plateau luminosity is about 0.53, and with a very small Pearson value indicating that the significant association remains. And finally, we test the predictive stability for the relation using a 100 random train validation split. In every split, we fixed prompt plateau plane provides a better performance than the two-dimensional dynody relation. Therefore, these tests support the robustness of the prompt plateau relation, although the physical interpretation of the fitted exponent should still be treated with caution. The prompt plateau relation can be also examined from an energy perspective, and we define the energy proxy as a product. You can see the formula here as a product of the plateau luminosity and the rest frame plateau duration, and from this equation that achieved by symbolic regression, we can have this quantity as a energy proxy, and this suggests that bursts with more powerful, you can see from this relation, you can see that the bursts with more powerful prompt emission tend to have larger plateau energy proxy. indicating a possible coupling between the prompt phase and the plateau energetics. And a direct regression between the energy proxy and the prompt peak luminosity gives a slope of 0.770 plus and minus 0.036 with an R square of 0.6 T. However, after controlling the luminosity distance here in the right plot, you can the explained variance decreases about 0.25, and showing that part of this apparent correlation is related to the common cosmological distance. So we should interpret this. We should interpret the energy proxy, this product of a plateau luminosity and the rest and the time duration, just as a energy proxy, not as the full integrated plateau energy obtained from the detailed light curve modeling. And the trend suggests a coupled energetic between the prompt and plateau phases. But the strength of this connection should not be interpreted as the universal conversion efficiency for all bursts. Now we test the constant efficiency scenario by examining this parameter. I mean, plateau luminosity, product of time rest frame time duration over the prompt peak luminosity. If a fixed fraction a fixed fraction of the prompt energy powers the plateau, and this scenario should be constant. However, we find a scatter of 0.62 dex and significant positive trend with plateau duration with a slope of 0.33. Therefore, near unity exponents do not imply constant efficiency, and the prompt plateau energy transfer varies among the GRBs. And here we check whether the symbolic regression relation is stable across the GRB subclasses, and using the 222 burst catalog from Narendra et al. For 2025, and with the class labels, and all sufficiently, we consider all sufficiently large group and which preserve the same sign pattern. I mean, the positive dependence on the peak luminosity and negative dependence on the rest frame time duration. And this supports the robustness of this relation. However, this is only the stability check, but also it's not the proof of universal subclass independence. And after that, in this slide, we test whether the symbolic regression could be produced by chance. So we performed a restricted Monte Carlo null test by randomly permuting the plateau luminosity values of plateau and among all GRBs, and while keeping all predictor variables and their distribution, you can see unchanged. For each randomized sample, we repeat the symbolic search over the 5 best performing feature combination identified from the real data, and we record the best root mean square error. This process is repeated 100 times. In the left histogram, you can see the distribution of the root mean square errors and obtained by this randomized data set. The null result is concentrated around the root mean square error of about 0.2, representing the performance expected when the physical correlation is removed. And the right histogram compares this random result with the real data relation. The real model with an root mean square error is about 0.47, lies far outside the null distribution, and it shows that none of the 100 randomized realization perform better. So the distance control relation remains separated from the null distribution, suggesting that the result is not purely caused by a luminosity distance effect. So this is the restricted null test and not complete rerun over all possible feature combination. Yes? Therefore, it demonstrates that the detected structure is unlikely to arise randomly with this search, but it should be interpreted as it shouldn't be interpreted as a proof of the universal physical law also. And so I will review our result. Our main result is that the prompt plateau emission are statistically coupled in GRB sample, in this GRB sample, I mean. And this suggests that they may originate from connected central engine process. And the classical Dinoti relation may represent a two-dimensional projection of a broader prompt plateau plane. However, this is an empirical relation and not a proof-specific engine model or a causal mechanism. It does not imply a constant efficiency or a universal physical law. The distance tests show that the relation is not entirely due to common luminosity distance effect, but a complete selection bias analysis would require additional information. And in conclusion, we recovered the Dinoti relation by symbolic regression, identifies a more informative prompt plateau relation involving the peak luminosity and involving prompt peak luminosity and rest frame time duration. The robustness test that I've shown indicate that this relation is unlikely to be a random feature of the data. However, this should be considered a performed empirical projection and not yet a universal physical law. Okay, I think my talk is over here. Thank you for your attention. And
Thank
I'm
you,
ready
Fatima.
for question. You're welcome.
Thank you. Any question?
Yes,
Okay.
so first of all, thank you for your very nice talk, and I would like to say a couple of comments. So you mentioned about this test that you deconvolute with the redshift, and this has been done also in Dinoti et al. 2015. I
Okay.
did with Petrosian and collaborators, in which we used the partial correlation coefficient to de-evolve the relation. So we already demonstrated in 2015 that the 2D relation, luminosity, it is not due to this distance dependence, and therefore this test can be surely carried out for the 3D relation. And also, it's very impressive, that you could recover with symbolic regression independently the relation.
Mi
And
chiami Andrea Reguitti?
if you had
Non sta di
compared
là.
with the parameters corrected by selection effects, because I expect you recover the relation without correction. So
Yeah.
if I understand correctly now, you won't implement this Efron and Petrosian to check whether you recover the correlation intrinsic. Am I correct?
Okay. Yeah.
Yes,
You are.
so
Yes.
yes, will be next step. And also it is
Mhm,
it's very impressive that you did this 100 split test and
Yeah.
still you record the same results. So I think that this is quite
Yeah.
substantial. Double check. But also another comment that I want to make, you mentioned that there is no physics behind. Of course, this is a linear relation, but also as pointed out by Wang et al. 2022 and other people, including myself, and there was also being done with the Magnetar and Rovlinson and Strata and myself. We did some work with connecting this correlation with the Magnetar model. So.
Okay.
Therefore, I think it is important to stress that this correlation, although comes from the data, actually it is driven by the physics,
Yeah.
and
Yeah.
this
Sure.
can magnetar-driven analysis. But we also had another idea that it was like the accretion onto black hole, and you can look at the Lennart 2000 et al. 2025 paper in which we can explain also the plateau as accretion onto black hole, and
Okay.
also the model of Professor Fini also was recovering this relation. So I think it would be wise to add this important information about the physical modeling.
Okay, so no, I didn't say that there is not any physical origin of this. I just mentioned that for our analysis, no need to assume any physical model.
Yes, you recover directly. Yes. Okay, very impressive. Thank you so much.
Thank you for your comments. It's really informative and very important for me.
So I have a very short technical question. So for the symbolic regression, did you use any particular software framework or software package that is available for performing similar analysis in other data sets?
What do you mean with packages?
Python packages. I think you used a Python package.
Oh, yes, sure. We use SR. Sorry, I forget the name. I didn't write it. SR, yes, we use SR. Yes, sure.
Okay, so Professor Ruffini.
Yes, very interesting, especially this new technique introduced by Fateme. But I would like to, we have been working a lot in the last days and week about this X-ray emission plateau. And what I will suggest to both of you is we think there is an interesting possible discriminant for different GRBs family in the relation between, possible relation between the X-ray plateau and the optical observation in the same region. And,
you mean finding the relation between X-ray and optical?
Yes. And,
okay.
We have very clear evidence that there is a relation between information between the optical and the X-ray luminosities in different kind of GRBs.
I see.
In GRBs like around 10 to the 52 to 10 to the 54, but then a different class of GRB going over 10 to the 54, the most powerful one, like 220101. But the only thing I want to say is interesting to correlate the X-ray to the optical. Thanks.
Yeah.
Thank you. So
Thank you,
if I may add something, currently we are also doing some transfer learning from the X-ray to optical domain because of the shared feature variable. So I completely agree with Professor Ruffini about this comment. Yes, thanks.
Okay, thank you.
And Fatima, I think Maria has a paper collecting all the optical afterglows.
Maybe I can use this catalog.
Yes, you have the optical catalog. This is open, so you can then transform in luminosity. And of course, if we think about the possible collaboration, I would be very much interested. We can work out this together. Thanks.
Okay, thank you, Fatima. Thank you.
Thank you, Wang Yu, and have a good day. And sorry for I couldn't present in person because of Roham, and I have to take care of him. Sorry about that.
No problem.
Bye bye.
Okay. Okay. Thank you. And then we have, I think next one is Constantino, but I don't know if he's Constantino.
Yes, I
Oh,
am
you're
here.
here.
I'm
Okay.
trying
Oh,
to
good, good.
activate. Can you hear me?
Yeah, we can hear, but we
Very
cannot
good.
see your slides.
There is someone else is connected and I cannot share.
A moment.
Okay. I will share this whole screen. Can you see well?
Yeah, very good.
Thank you.
Okay.
Good morning to everyone. Thank you for inviting me to present this talk, especially to Professor Ruffini, to this very important meeting, remembering Yakov Borisovich
Excuse me, can you
Zeldovich.
make the full screen?
Full screen.
Yeah.
It's good?
It's good.
It is full?
Yeah, yes, please continue. Thank you.
Okay. Thank you. Want this thing? Okay. No? Okay. The first time I met Professor Zeldovich was thanks to Professor Ruffini 35 years ago. Obviously, I am younger than the lifetime of Yakov Borisovich Zeldovich, but thanks to the lectures of Professor Ruffini in 1991, he presented to us a very nice paper, Pre-Stellar State of the Matter. I found here the link to recover it on the NASA ADS. And this paper was about cosmology, the cold Big Bang solution based on the degenerate state of the matter, of the cold fermions. So I bring you to your attention this paper in honor of Yakov Borisovich Zeldovich. He made many other things, but this was very particular, and Professor Ruffini pointed it out at the lecture. So I remember this. About the theme of this paper, I have to remember the paper of 2024 appeared on Universe. We prepared it just before the Marcel Grossman meeting, number 17, that we had for the first time in Pescara. And a month later, the journal asked to us to prepare a cover because the paper was receiving many readings. So with the help of Laura Manfrini, a student of Pescara, we prepared this cover that you see on the left side. In this cover is summarized the historical events regarding that famous bright star seen in daytime in 1054. This year, this cover was awarded as the most popular one, always by the MDPI editor. So we were proud to receive also this award. And I want to use this cover to recall the main points of that paper. The first one is to resume all the historical accounts in a single day from 3 to 4 July 1054. The historical accounts are spread, the dates of the historical accounts are spread over at least 2 months, 2 or 3 months, and the reasons are several. The first one is mentioned on April 19, the day of the death of Pope Leo IX, and there are other dates that are beyond the normal standard date of the supernova of 1054, which is the 4th of July. So we have the accounts from Japan manuscripts even in August 1054. So why all these dates can be resumed in only one? America witnessed the event at the horizon with a high atmospheric thickness. Europe and Africa and Egypt witnessed the event at noon with the lowest air mass, so without protection due to the atmosphere, and China witnessed the event the morning after. So the morning after is commonly considered as the 4th of July, and then our proposal is to consider all this observation condensed between the 3 and the 4 of July. The exponential decay of the brightness of the gamma ray burst made it very dangerous at the beginning, so in particular for Europe and Egypt, and it made it simply bright but not dangerous for China the day after. The idea of Professor Ruffini to connect this event to a gamma ray burst was also supported by the news of plugs exploded in Cairo and in Constantinople and connected with the star. So we have the name disaster. Disaster is a name also, is a word also in English, not only in Italian, but the root is Latin. Disaster means a bad star. And this bad star was the one visible by day and appeared over the sky of Europe. The final point of that paper was to extrapolate the exponential decay of a gamma ray burst, very powerful, of the order of 10 to the 54 erg per second at the beginning, isotropical, to the present, to find the Crab's emissions in the various wavelengths. These are this is the light curve extrapolated, the light curve of GRB 190114C extrapolated to the present, which is around 10 to the 11 seconds after the explosion. The rapidity of the decay made the luminosity, the optical luminosity, becoming enough to be seen in daytime after 1 day of the explosion until 23 days, for 23 days. And in 2 years, the observability of the object became at the limit of the naked eye, even by night. The Chinese accounted for this event, but the manuscripts of these accounts were copied only 1 to 2 centuries after the event and were adjusted to the current policy, to the current emperors. Since a bad star was a bad omen for an emperor, it was better to avoid to mention it for the astronomers. That is for the astronomers and for the people in charge of recording the astronomical events. So this is one of the one of the problems connected with history. Another problem connected with history is the spontaneous connection between a strong astronomical event and a religious event. For example, the death of the Pope Leo IX. He died 19th of April in a chronicle written in Belgium. This death is connected with a vision in daytime of a big sphere in the sky, which has been explained as the immediate appearance of a very bright object in the sky, point-like, producing, for optical reasons, a great ring. But the association between the death of the Pope, so an event to be interpreted also in a mystical and in a heavenly way, to the astronomical event is probably forced, that and this not means that the event did not occur, but this means that the date can be not trustable. This is the drawing on the stones in America, in White Mesa in Arizona, where the Indians, the local Indians, drawn near the moon such a bright object. It has been interpreted in this way by archaeologists, and we add to this fact the chronology saying that the Indians saw it at the rise of this object, so illuminating the sky as in daytime. But thanks to the fact that the object was low, the air mass was high, and that observation was more safe than the one occurred in Europe and in Egypt, which produced the same plagues of atomic bombs in Hiroshima and Nagasaki. So immediate plague, immediate blisters on the skin, which were generally interpreted as plague in the former chronicles. The new insights came from this meeting, the Zeldovich Sixth meeting on 15 of July by Taghi Mirtorabi. He presented the phases of the explosion of the GRB 220101A, And he described these phases as the explosion of a supernova triggering another supernova, which produce the pulsar. This high definition of the high time resolution of this gamma ray burst allows to associate more convincingly this mechanism of gamma ray burst production to the Crab nebula as we know it today. The Crab nebula is the remnant of that event in 1054. We know that Hewish and Jocelyn Bell found the Crab pulsar, and now only the black hole is to be found there to complete the picture of the gamma ray burst in that framework of BDHN model. And this is my last image. I want to thank you for your attention.
Any question? Any question? Thank you for interesting presentation. How do you estimate points on the graphic that was after seconds after Bart's? It was 1,000 years ago. Does it possible to estimate such concrete points?
I can tell you that we use simply the exponential decay. I know that, for example, for gamma ray burst 220101A, there are recent papers showing bending of the radiation, a general bending in all wavelength around 8.4 days. But I didn't do this calculation with the new gamma ray burst. This is in the presentation I shown only the extrapolation of the previous one. So this is under study yet. Your question is fully correct.
Okay, any others? Professor Ruffini?
The key point that we are noticing in the new analysis of the new GRB is that there must be a pulsar present, and this is the pulsar, not only the key point of the Jewish discovery was the discovery of the pulsar, and it fits very beautiful on this picture if you consider that that supernova was of the kind of GRB 220101 and produced a pulsar which has been observed by Jewish. This was the only new point, because in the previous case of 190114C, it's not clear there was a pulsar left, but in the case of the new GRB, yes, we can for certain associate also the observation of a pulsar, the existence of a pulsar, which fit the extrapolation after 1,000 years. I mean, you can take GRB 220101, the luminosity of the pulsar at the explosion, extrapolate for 1,000 years, and you see that they fit.
Thank you for your presentation. And
You're
one of
welcome.
according to my knowledge, maybe something more is known, certainly. But in the 90s, it was a supernova explosion in Magellan cloud.
I'm sorry, I don't
Magellanic
hear
cloud
clearly. Please
galaxies.
speak aloud.
And is it known something similar for that supernova explosion concerning possible gamma ray evidence of gamma ray flash or pulsar formation, etc.? It's
I didn't hear clearly the
you see
question. I'm
that
sorry.
Magellan cloud galaxy close to our galaxy, and in the 90s or 1908, it was a supernova explosion, which was very seen in various ranges of wavelengths and discussed very actively. My question is, do you know, or others, about gamma ray burst in this situation and formation of pulsars, some indications? It's just my ignorance for my.
I can tell only one thing about the 1987A supernova.
Yes.
You are correct. It was well observed. It was, well, by naked eye, it got magnitude 3. So, with respect to what we are dealing with, there are at least 8 to 10 magnitude of difference. The one of Crab Nebula was much more bright, extremely more bright. Production of pulsar, yes, it is produced. It is produced by such supernovae, but for the 220101A GRB, this production, as far as I understand, is deduced by theory, because it is witnessed by the third bump that Professor Mirto Rabbi shown yesterday. I should show it to you again, but you have seen it. So is this one? The third bump that he mentioned is in the framework of BDHN, an indicator of such a supernova, which includes a pulsar.
To tell differently, we fitted first with 190114C, but there we had not the evidence that 190114C could explain the observation of a pulsar. Now we have
Non sento nulla, eh? Don't hear anything. Use the microphone. Please.
We see a pulsar emission, and therefore we recalibrate this data, which confirm the data of 190114C, but they add the presence of the pulsar, and the energetic is perfectly okay, both for 19 and this one. But this one, we are repeating all the analysis for this source, but the key point is that we can conclude is that supernova was exceptionally powerful, and we have now, not years ago, now in 2201 220101, we have the evidence that the pulsar should be there. And this is quite exceptional.
Wangyu, dai il microfono al professor Ruffini. Give the microphone to Professor Ruffini.
It's not a general GRB. Now, the fact that the pulsar is predicted, is observed in 220101, and the energetic can fit all the data like 190114C, proves that supernova, which the mechanism which generated the supernova 1054 had to be like GRB 220101. It's fascinating.
Okay. Okay, thank you, Constantino.
You're welcome.
Yeah, so we have 15-30 minutes rest, and we meet again at 11 o'clock.
We have coffee now.
Yeah, we have coffee now, yes.
My topic is slightly different from gamma ray bursts. It's on double white dwarf mergers. Compact objects are interesting. Most of the talks this week was on them, but I'm interested in compact binaries. After the 2017 merger, there has been a lot of searches for binary neutron star mergers that appear as like kilonovae or supernovae, and then double white dwarf mergers will soon also gain the spotlight when you have missions like LISA, Tiankin, and Taiji. So why are we studying double white dwarf binaries? When you have when you compare the supernova rates with the rates of double white dwarf binaries that are in the galaxy, you find that there's a slight discrepancy. So it suggests that maybe there are non-explosive outcomes. And also we have seen with Gaia that there are ultramassive white dwarfs. So I'm exploring in this line if we have these remnants after a merger, then probably there should be a sign that we can detect when the merger occurs. So in my model, there are two cases. In our model, when there's a white dwarf remnant, we take fallback accretion as the source of the energy of this transient. And then when there's a neutron star remnant, we take the spin down of the neutron star. The ejecta setup is quite simple. We take a power law density profile, gray opacity, and the photosphere evolves by the derivation from the density. For when the opacity becomes 1, we have a particular value, but after it becomes transparent, it evolves as the outermost ejecta layer. And finally, this is the energy equation that we are trying to solve. We introduced this efficiency of absorption based on the opacity. And there is also, there is also a part of the radiation that's leaked without interacting with the ejecta. And finally, these are our results. We have a bolometric luminosity. So in red is the radiated thermal transient, and then in green is the leaked radiation. This is something that we are still modeling. It could be a synchrotron radiation. And when we convert them into what we observe as magnitudes with telescopes like LSST, we obtain these light curves for different configurations of the neutron star energies. The light curve of the white dwarf is quite similar to the lowest case of neutron star. It's not as bright. What we find is that the strongest neutron stars with like millisecond rotation and like 10 to the 14 Gauss magnetic field are very bright and could be detected by instruments like LSST. So when we look at it in the broader scheme of transients, it falls in line with the gap transients. The fast evolution of it would make it hard because if we take LSST, they have like a cadence of 2 to maybe 3 days. So we would need multiple synchronous efforts to kind of capture the entire light curve. And we also predicted the rate at which these events occur. We took into account the cadence, so we are not only calculating the magnitude at peak, we also calculate a horizon for the magnitude at a particular cadence. So we checked for how many events can we detect if we require that we are able to make 2 observations or 3 observations. And finally, for the rates, I'm using the double white dwarf rates from Mawos et al. And supernova 1A rate from Perley et al. We are making this assumption to get an upper limit that all of the non-explosive cases end up as a neutron star or white dwarf, depending on what we are looking at in our analysis. So for the case of the neutron star remnant, we find that in ZTF band, within 20 to 70 megaparsecs, we would get up to 10 to 100 per year. Again, these are upper limits. And with LSST, we could get somewhere from 100 to up to 1 million sources. But again, the limit is that the cadence is you have to account for that. And also you have to take into consideration that this is made with an assumption that all the non-explosive cases end up as neutron stars. So there are detectable transients, and we are looking into expanding our semi-analytic solution with simulations like POSIS to get the realistic light curves. So Megadas and Matiabulla, they are working on that. And we are also looking into ways with which we could see these like triggers in LSST and possibly collaborate with other telescopes to get a complete light curve and see if this prediction is true. Thank you. It's a short presentation, I guess. Yeah.
So any question?
Compared to all other progenitors of 1A supernova,
Yes.
how much? What is the fraction of double white dwarf merger you expect to?
I have it in the first slide. So these, when I say double white dwarf binaries, these are the ones that will merge in Hubble time. So somewhere to 10 to the 5 gigaparsec in per gigaparsec cube per year.
I miss you talk.
Sorry.
Because we were having a discussion, very heated discussion upstairs. But you have a non-explosive merging.
Yes.
And evidence for merging in a neutron star. Is this the key point?
The key point is non-explosive merging from double white dwarfs. And we don't have an evidence. We have a prediction on if we can detect that with LSST, for example. We are still working on seeing if we can find this evidence with our collaborators.
If you find the evidence that after the merging you have a neutron star, this is the idea?
Yes, a neutron star or a massive white dwarf.
Yes.
Yes.
Oh, and you're looking for this, yes, but this is precisely what we expect in 1708-17.
Yes.
You mentioned that, yes. Okay, that is beautiful. Well, I feel happy that you are keeping going in this direction.
Yeah.
It's very, very important. Not very important. It is just to show that the 1708-17 has no mystery for the electrodynamical part. Of course, there's a big mystery about the gravitational wave, because I don't understand, and some people don't understand, how could this happen in the same physical event to have on one side a gravitational wave binary, neutron star, and on the other side a white dwarf binary merging, which looks very, very good, but completely unexpected for the first event. On the second event, of course, the more we learn about white dwarf, the more important it is.
Yeah.
And to make solid that the second part comes out of this, there was for a while an evidence that maybe you have a neutron star, but it's not confirmed. There were not enough data for the neutron star appearance in 1708-17. It's not been confirmed, no?
I
the data of Chandra were not good enough.
True.
And they're still trying to find this. The time is passing, therefore it's not clear that new detector can be in condition to look at it. But let's hope so. And of course, like you say, we can just look all over the galaxy for white dwarf, white dwarf emerging, and see if indeed they form a neutron star or a massive white dwarf.
Yeah.
Thank you for, I feel reassured.
Thank you for the opportunity.
Okay, thank you. Okay,
any other
thank you,
questions?
Linda. So we have next to speak Mario. It's too low. You need to wear this very close to your mouth.
Closer. Okay.
It's okay.
Is it fine? Okay.
It's okay. Okay.
Yeah, it's
you uploaded.
yes, it's on the.
Yeah.
Should I use the laptop to? Yeah. Okay. Okay.
Please.
Okay. Okay. So good morning, everyone. It's a very pleasure to me. It's the first time being in Pescara and at ICRANet. So let me thank Professor Ruffini and also Gregory for the invitation. And I'm very excited to present the status of the Euclid mission in these few months before our first cosmological data release. So my name is Mario Ballardini. I'm a researcher at the University of Ferrara, and within the Euclid collaboration, I'm one of the lead and coordinator of the theory working group. In particular, I'm focused and leading the analysis for all the science related to initial condition. So this is the outline of my talk. It's divided mostly in two parts. First, I will try to give you a structure of what is the Euclid collaboration, the organization, and what is the experiment, the spacecraft. And then I will move a bit on the cosmological forecast, since we haven't published yet any cosmological result. So what is the Euclid Consortium? Euclid Consortium is a massive collaborative effort involving more than 2,000 active members. We have a portal where regularly we upload all the activity from each individual member in order to really get track of all the different contribution and who is active and who is not active in collaboration. All these persons come mostly from 15 European countries, but there is a large partnership also with the US, Canada, and Japan. This is a picture from the latest consortium. We have one consortium collecting all the collaboration for every year, plus different, let's say, meeting or workshop from different operational units, working group, working package. It's a bit a structure of the mission, which is a partnership between ESA, so the European Space Agency, and the Euclid Consortium. ESA took care of all the spacecraft and the operation of the spacecraft, while the ESA Consortium has, let me say, took care of the instruments, so the instrument on board of the spacecraft, the data reduction, and of course the scientific exploitation. And here on the bottom row, you can see all the different unit and working group inside the collaboration. So the most relevant two, let's say, are the SGS, the sand ground segment, which takes the raw data and deliver internally to the collaboration the summary statistic that we will use to perform, let's say, the cosmological studies and also other legacy studies. And then here, the SWG, the science working group where I live, which is the science working group where we use all this summary statistic to perform all the cosmological study. So let's start from a bit what are the main targets? So Euclid is a cosmological mission, is a medium mission selected by ESA, whose main target is cosmology. The plan is to do cosmology through galaxies, so of course there will be a lot of legacy science on top of the cosmology that will be possible to do. And the main target is to perform a map, a three-dimensional map of the geometry of the dark universe. This is the usual sketch picture of the expanding history of the universe according to a hot Big Bang model. And in this context, Euclid will trace the latest 10 billion years of history. And the idea is that by collecting billions of redshift, so somehow position and shapes of galaxy, to perform and deliver it to the community the largest catalog of galaxy accessible. These are the main scientific cosmological targets that was defined when the mission was selected. So this coming from this huge definition study report from ESA. And as you might guess, and somehow I already mentioned, the main known topics are related to the dark component of the universe, with the main idea is to characterize, if not unveiling, the nature of dark energy or the cosmological constant, and the nature of dark matter. So also in between, you might think of test of gravity on cosmological scale, and eventually test of deviation from gravity. But it's also important, and quite important also for myself, and it's not always so highlighted, that Euclid also in the context of cosmological perturbation will be of unique importance for test of initial condition. Usually we are told that the initial condition of cosmological perturbation is something more related close to cosmic microwave background observation, but Euclid will also be unique in this regard. So what is the Euclid satellite? Let me talk a bit, mention a few things about hardware, even if it's not really my things. So the Euclid is a spacecraft, is on space, and is built around a 1.2 diameter main mirror. Is a cross telescope, so it has 3 different mirrors. The structure is divided in 2 main units. So there is a service module, which is the large part, which hosts all the hot electronics, and the main features is the sun shield, which has 2 main rules. One protecting all the instrument from the emission from the sun, and the other one is with solar panels to get energy for all the operation. Then inside we have the service, the operational system that has inside the 2 main instruments. This is one of the unique aspects of this mission compared to other previous and future and competitive telescope or spacecraft for detection of large-scale structure. This is the only experiment that is able to perform spectroscopic and photometric surveys, while in general all the other experiments are focused on one of those. So this is one of the key aspects also of the mission. Here you can see the optics with the 3 main mirrors. There is a main mirror with a diameter of 1.2 meters, then which is gathering all the light, then is reflected and converged in the holes inside the first mirror by the second mirrors, entering inside and collected finally for the third mirror M3. And then there is this unique part of the very important, which is this dichrotic plate, which is dividing the light and passing the same field of view in the two different instruments. So the 2 different instruments, the visible and the near infrared instrument, are observing the same field of view, which is quite large. This is why we are using this kind of optic. The field of view is 0.5 degrees, so almost 2 orders of magnitude larger if you can think to Hubble Space Telescope or James Webb. So 2 instruments. The first one is VIS, so a visible imager, so which has this camera with 36 6 times 3 CCD with a resolution of 0.1 arcsecond per pixel, with a total number of roughly 600 million pixels. It has no moving part and is collecting spectra in the visible range without different split of the wavelength band. And the main target of this instrument is to collect shapes, so picture with shape of galaxy. Then we have the NISP, which is a near-infrared spectrometer and photometer, which operates in two different modes. It's a bit more complex unit. We have the camera, a smaller one here on the right, and then we have this unit here with all the filter with the wheel that change the filter times by times. So it operates in the photometric mode with three different bands, Y, H, and J, collecting photometric redshift of galaxy, and then it can also operate in the spectroscopic mode with two red grism. So is a sleepless unit, so different from other experiment based on slipped or fiber. If we think to spectroscopic telescope from Earth, is able to collect a lot of different lines. It's not observed directly the galaxy, is observing the emission and absorption lines that we will use then to reconstruct with high accuracy the single redshift and the position of this object. So primary probes. We can use these two different instruments to perform two very complementary probes of the large-scale structure distribution. The first one is the so-called galaxy clustering. So with a very accurate and precise measurement of redshift and position of galaxy, we can really reconstruct the three-dimensional distribution of galaxy. This is a very important and unique probe connected to the evolution, if you want, of the Newtonian potential on some limit, so strictly connected to the evolution of the non-relativistic matter. With this probe, we can do the standard cosmological rulers or measurements, so focusing on particular features of this distribution, as you might have heard about BAO and RSD, but also with the large collective areas that we will be able to It really depends on the wavelength band that we can cover. So at some point we have a budget cap, and we have to decide for which range to cover. Also, Euclid was for the spectroscopy selected really to tackle H-alpha emitters. So this is a bit the range is easier also to detect line from this specific family of galaxies. And also it was to be a bit more complementary to other experiments that we already have.
That is another reason.
Yeah. But I mean, we had the cost budget, so we had to decide also. This was a limitation. So the first proposal was indeed to have, I think, 3 red grism, so also able to go a bit lower in redshift from 0.4 from 0.5. But then due to all the budget, we decide to go for this range.
There is no reasonable principle. It's just the 1.8 is a reasonable principle, but 0.9 is not a matter of principle.
No,
it's
indeed.
Just a question of economy.
Indeed. This for what concern the spectroscopic experiment, the collection of spectroscopic redshift. Then we can collect photometric redshift on a way larger redshift interval range. This is just a positioning on Euclid in terms of performance with respect to other experiments. So you see on the x-axis the coverage in comoving volume, and on the y-axis the absolute number of redshift collected. And you can see on the top the red one is Euclid, and the diagonal dashed line are isodensity lines, so it's performing very well. There is some better coverage in terms of volume by in particular the quasar survey expected from DAISY, but the number of objects and redshift is way lower. Then the second primary observable, let's say, is cosmic shear or weak lensing of galaxy. So by collecting shape of galaxy, we can reconstruct the distortion, so the presence of matter, in particular dark matter, along the line of sight that through gravitational effect is distorted the propagation of light. So another different probe connected to the propagation of light, while the galaxy cluster is more connected to the distribution of matter presence. Also here you can see in the bottom left some performance expected in terms of number density with respect to the current stage of experiment, DES, HSC, and KIDS. This is a similar test where we forecasted the performance in terms of measurement of a two-point angular correlation function and with respect in comparison to the current performance of existing service. This is indeed a cartoon that I just plot to show what is the current status. So this is the density of galaxies that we have already now with Euclid DR1. We already collected this object. And this is the same for the current stage of photometric shear survey. So we already pass by a lot in terms of density and in terms of galaxy. Of course, if you consider to DES, the areas that we cover at the moment is a bit smaller. Then, of course, since we have a collection of and a catalog of photometric redshift galaxies through the collection of also of shear measurement, we can perform also using this catalog galaxy clustering with a reduced redshift resolution. So the strategy is a bit different. We can't really perform a three-dimensional reconstruction of all the matter distribution. We have to collect a bit this in shells, in tomographic beams, and perform a two-dimensional projection, but in different slabs. So still there is some three-dimensional information. And this is a bit the same considering the collection, comparing the collection of photometric redshift used for clustering with respect to that. So already we have 3 times already now the number of objects on a smaller patch. And since we have photometric information, we can also cross-correlate position redshift with shape measurement. And this is the full strategy for the photometric analysis to combine in what we call the 3 times 2-point shear measurement and galaxy clustering measurement. So a bit of status, some dates. Euclid has been launched 3 years ago with 1 year of delay due to geopolitical evolution in 2022-2023 from Cape Canaveral. It took 1 month to reach its position. It's a Lagrangian point 2, so it's not orbiting around the Earth like COBE, SPHERIX, other satellites, but is operating from this L2 point, similar to what did WMAP and Planck. Survey, this is the target. So the main target of Euclid is to perform a wide survey, so eventually a very large survey with the limitation of parts that we can observe due to other contamination, in particular the galaxy and the zodiacal light. So once we remove these 2 bands, almost 1/3 of the sky is the maximum that we can perform. It's collecting almost 10 degrees square by day and is not going back to different paths. So it's collecting time by time. This is why now we have almost collected 2,000 degrees square and it will increase year by year. We have a main wide survey divided with this geometry mostly in two main patches in the north and in the south hemisphere, and then we have 3 deep fields, 2 in the north, 2 in the south, Euclid South and Fornax, and 1 in the north as this small green point. In this specific point, the experiment will pass and collect a lot of time data, and it will go deeper in magnitude in order to calibrate shapes and the evolution of galaxies. So they are very important for calibration and control on systematics, these 3 deep fields. This is a bit the time schedule of the mission. So after the launch and after it reaches location in L2, there was a first period of all verification if the instrument were working correctly. And then after almost a bit less than 1 year, the nominal mission started. The schedule of the mission is to collect 6 years of data. Then after that, depending on the status of the instrument, we might have an extension period, but it is a bit early to say that. We expect to release 4 quick release. We already had 2. I will show some picture in the next slide. They are most meant for legacy science and to showcase the performance of the 2 instruments. So there are these Q1, Q2, Q3, and Q4. And then we have the main cosmological data release 1, 2, and 3. The data release 1 is near to come, and for different reasons, we decide to split that. So there will be a first, which will be called DR1 Foundation release this November, should be the 9th of November. This will release all the legacy science images and catalogs. So from a cosmological point of view, it will be quite key for study like strong lensing, cluster, and these things. And the full data release 1 with the publication of all the cosmological result and the release to the community of all the products will be next year in June. The exact date is still to be decided. So what we had so far, there was images, tester imager from the really first minutes of observation that have been released just after the start of the nominal mission. Then there was, in May 2024, a first ERO, early release observation, collecting images from the first day, so just 24 hours of observation, demonstrating the quality of the data, and also coming out with a collection of papers. You can find them on the ESA website, demonstrating already the first science possible to be done with Euclid. We had already quick 1 release, which is a part of data collection from the 3 deep field, so the 2 in the south and 1 in the north. Is a very small area, 63 square degrees, but it was possible really to do a lot of science. There were already tens of papers from the collaboration and many more from outside the collaboration. All the data, once we publish the things, are publicly available, so you can already find and use and play with this data. This data, as I was mentioned, was mostly thought for a showcase of the performance and to be used for legacy science, more astronomy, astrophysics related science. But with the quick 1, we are already releasing some first cosmological result. It should be out end of summer, let's say late August, beginning of September, by using the cross correlation with the CMB. And then a few weeks ago, we had the second quick release. So the second, the third, and the fourth will be quick releases will be targeted to specific objects. So we are still deciding inside the collaboration what we'll target for the third and the fourth. And the second was targeted to imaging of the bulk of the Milky Way. Now let's pass to cosmology. So the cosmology and the way we think about cosmology is a bit structured in this way inside the collaboration. We have 2 primary science working groups dedicated to clustering and to weak lensing. They will do the measurement, validate the pipeline, and release the main standard cosmology, meaning inference on cosmological parameter within the lambda CDM model and minimal extension. And then we have the theory working group that I'm leading, which is doing all the extender or interesting cosmology, which is structured in this way. We have 4 main active packages, 1 related to dark energy modified gravity, dark matter and particle at large, where of course neutrino from cosmology is one of the main topic and initial condition. And then as a transversal package, we have this modeling where we try to extend and validate our pipeline to perform the analysis for this non-standard, let's say, cosmological model. Everything is implemented, the main pipeline and the tool to analyze Euclid data, in this CLOI org framework, which is already publicly available, is constantly updated. So also the pipeline to analyze the data, not only the data will be released to the community. Some of the tools are already public. So some result forecasted, just to mention a few, then please ask me questions if you are interested in things. We are in a specific era, is few years, where this, from the cosmological point of view, there is this all interest or related to the possibility of having deviation from a cosmological constant if we look to the late time evolution of the universe with these non-statistical evidence, but hints, intriguing hints of dynamical dark energies. The funny thing is that if we look to single cosmological probe, BO, supernovae, CMB, everything fits well with the cosmological constant, but the problem is when we start to take combination of this. Every fits the cosmological constant, but with slightly different parameters. So when we start to combine the things, we start to see these mild, let's say, or intriguing tensions. But the other funny fact, which is not always so clear, at least in my point of view, is that it's not the full combination. It's just if we take combination of two. So even if we can get rid of one of the possibilities that we have in terms of measurement, we use only supernova and BO, or clustering, we use the CMB and not the supernova, all the possible combination, this intriguing deviation from the cosmological constant is there. So this is a collection of results from a few months ago, from different of this combination in terms of the equation of state parameter at late time, measure at different pivot scale from different combination where this data maximizes this signal. And you can see that all the possible combination is not statistically, there is nothing statistically evident, but there is this discrepancy always at the level at least of 2 sigma. For some combination is still 3 sigma. So something is there, and we are really to get into that with an independent experiment. This is a bit the forecast that we expect for Euclid, and in general, in order to tell the constraining power of a survey for what concerns dark energy parameter, we try to use this W0, WA, so evolving background description of the dark energy component, and to quantify the content information with this figure of merit, which is somehow related to the area of the ellipse that lives in these two parameter space. So it's taking into account the constraint on the single parameter and also the correlation. And the idea is that we will be able with the final, not the DR1, the DR3, Euclid data release combining all the probe to at least, but probably more, double all the information. This only with the primary probe. I already mentioned a few times that we have primary probe, galaxy cluster, and weak lensing, but also we will have cross correlation with CMB, Sixth Zeldovich, a cluster of galaxies, super strong lenses, supernova. So there is a lot of additional information that we can inject to make these things really a reality, not just a hope. In terms of modified gravity, this is a bit not super nice, in my opinion, parameter that was put in the table of the study report from ESA. So ESA wants that we go back to the number that and the parameter that we mentioned 20 years ago. So in order to test of modified gravity, the focus is the main focus is on this gamma parameter, so the rate of the growth of structure, so the rate of structure that it has a clear prediction in GR, so the idea is really to be able to test this, and also here you can see the improvement with respect to the current survey. This is not the only thing that we will do. So these are the main parameters that will be studied, but then there are a lot of things. So we'll test, do in particular independent test of coherence stance of what is happening at the background level through versus perturbation, and there will be a lot of study on specific physical motivated model for dark energy, and in particular for modified gravity. Particle cosmology, the main focus here is the detection on the constraint on the neutrino from the cosmology. So we know that the caveat always that we are not directly sensible to the neutrino parameter, but through assuming a model, lambda CDM or extension, we can infer constraint. And the two main parameters here are the effective number of degrees of freedom, so the contribution from neutrino or extra particle to the radiation component of the expansion of the universe, and the other one is mostly the sum of the single neutrino masses. And our forecast allows that we will be able, with Euclid alone, to get this sensitivity, so somehow of the order of the minimal mass, if we believe to neutrino oscillation, and with the combination of SIG-B reaching with current or future that will be available at the time of the last data release of Euclid, CMB measurement reaching a level of a detection at 3 for sigma of the minimal total neutrino mass. And this will allow us eventually also to have a clear statement from cosmology on the hierarchy if neutrino have a normal or inverted hierarchy. Also, some information will be possible in terms of constraining the effective number of neutrino or the effective number of additional relative species that they contribute to the total, let's say, radiation component in the expansion of the universe. So this is a bit a dense plot, but depend different additional particles as myrons, while fermions, they can contribute to the radiation component in a different way, in a different number, depending in particular when they decouple from the plasma. So the latest they decouple, lower temperature, they contribute more, and we can constrain more and more all this scenario. Also here, this is the minimal setting of tests that we will do already in DR1. Also here we will test work dark matter model, decay in dark matter with different kind of decay. So there will be a lot and a lot. And a final topic that I want to show is regarding the constraint on initial condition. Also here, there are many tests. Of course, the main target when we refer initial condition, if we want to try to understand if there was an additional mechanism for or before Big Bang, if it's cosmic inflation, if it's an alternative, if there is nothing. And of course, there's the main target. We all know that is the possibility to detect the B mode of polarization of the cosmic ground radiation. This will be a clear, unique test, not model dependent, if we will be able to detect a new method. But there is a lot that, without relying on primordial tensor perturbation, we can do on the scalar sector. And this is the rule that will be played by Euclid and by the possibility to measure Raschke structure on smaller scale compared to the one that we can do so for the CMB. Also here, we are living in some years where there is some confusion on many parameters in the context of initial condition. So we know that after Planck, latest cosmological measurement of CMB, for instance from the Atacama telescope or from BO, have started to put an hint that the value of NS is shifting a bit. It's not a big shift, it's 1 sigma, 1.5, so nothing very relevant. But if you want to start to play on this famous NS versus R space, the game of what is the best preferred model, is Starobinsky the best model, is some alternative, just this minimal shift make a very important and profound implication of which are the best model consistent with the data. So it will be very important to have complementary information, so not just relying on, for instance, DCBO, to understand if this shift is unique of a specific observation experiment or is something that is really driven by some common physical ability. This is some forecast for NS expected for the final data release. So we expect to reach the same sensitivity that we reach now with CMB, but without relying on CMB data. And the combination is expected to go down by an additional factor 2 or 3. Then we can expand the parameterization of the primordial power spectra that we use in a standard cosmological model to describe the primordial perturbation. So instead of using a simple power law with an amplitude and an index, the scalar spectral index that I was mentioning before, We can add in a tailored fashion a second order, which is so a scale dependence, which is usually labeled with this alpha, the rounding of the scalar spectral index. This is a unique parameter connected, if we believe, to cosmic inflation, and if we believe that cosmic inflation in the scale relevant for mass evolved in a slow roll regime. This is a unique test that we can perform to test slow roll prediction at second order, which at the moment is not possible. And our forecast is that we will be able to reach the sensitivity on the alpha parameter in terms of uncertainties closer to the prediction of slow roll. So there is really a possibility to go beyond the knowledge that we have now. And also here, just to mention, if you want to just focus on the upper part of this plot, these are the constraints that we have at the moment, so measurement on actual cosmological data on the alpha parameter. So you see how the different experiments also in this specific parameter space are pointing to different directions. So also there is some cosmological confusion that we will try to make some understanding there. Final topic, which is super interesting, is the possibility to test primordial features. So deviation from the minimal parameterization of the primordial power spectrum that might be global as oscillation, linear or logarithmic in K-space, or even localized, sometimes connected to particle production during inflation. And it's already been proved, there are already tests on real data that galaxy clustering, galaxy extraction survey will be able to do way, way better than what we do at the moment with the CMB study. And also, this is not just a possibility to do some phenomenology. I mean, we have the data, we start to study some extension, but also all the business of primordial features is somehow motivated by features that appear, for instance, in the CMB data. All the different features, outliers that we see in the measurement, for instance, of Planck, but many of them were already in WMAP data, can be connected with features outliers in the primordial power spectrum. So we can already use feature to explain anomalies that we already see in the CMB. So the idea is to try to improve, in particular, the statistical leverage for this point, adding large-scale structure clustering data. So this is just a result on the forecast that we perform on this. Also super interesting, but there is no time, is the contribution from the bispectrum for this specific study of primordial features. And I leave you with my conclusion and final slide. Thanks a lot.
Very nice talk. So comments? Question?
Thank you. It's a great project. Of course, it's difficult to ask a single question. I paid attention on one of your slides when you discussed distribution of matter in the universe with such the web structure, and you said about some average properties. And this idea stems from the first work by Zeldovich, who said that about formation of pancakes. It was a very simple theory, mathematically and physically, but extremely rich heuristically. Next step was done by Zeldovich and his younger colleague, my friend Sergei Shandarin. And then a real breakthrough happened when great mathematician Vladimir Arnold joined this team, and they published a paper saying about predictions for things made with catastrophe theory of mathematics. They predicted formation of singularities of various types. I remember vaguely it's cusps, swallowtail, butterfly, etc. And can you resolve these singularities and identify them in your project? First question. And second, if so, can you do the same for dark matter?
Well, regarding the second question, what do you mean? Can you do the same for dark matter?
Because you have formation of singularities of normal matter. And can you identify that locally, but it is of course many galaxies are there, that we have this type of singularity or that type of such another singularity according to Arnold's theory, because of he is one of the founders of this catastrophe theory in mathematics. And second question, if you can resolve these structures in normal matter, which you can observe optically or some other means, but with lensing or some method which you know better, to say something about dark matter distribution.
Okay. Well, honest question is I don't know, but I think that yeah, I'm not sure about the resolution that we can reach on a single object to perform really study on distribution of the core and the profile of the object. For sure, we will have all this information, so it's something that I expect that will be possible at some level, but I don't have the number for the statistics, so I'm not sure really what will be, but it's a super interesting topic. Thanks for raising it. Yeah, thanks a lot.
When did you participate to this meeting? When you arrived here? Today or the beginning?
No, today. I arrived yesterday late.
Yesterday.
Yes. Sorry for that.
Well, I think you missed a lot.
Yeah, yeah.
You will have the occasion to see in the tapes.
Yes.
But you missed a lot.
Yeah, unfortunately, yeah.
Because today is very clear, since the fantastic work presented here yesterday by many people, including Wen Dao Luo. It's very impressive that if you look at the distribution of matter around galaxy, there is a very clear signature for the matter distribution in flat rotation curve. This was the most fascinating, that you have the black hole mass, but also the mass in general galaxy. In our galaxy, the mass of in the rotation curve is very sizable. It can be 10 to the 2 times larger than the mass of the black hole. And in particular, what we have understood is that that same mass is the basis to understand the dark matter distribution of Sagittarius A. And we had a splendid lecture by our colleague about this possibility to prove that that distribution of X fermion, the way we introduce a particle which is, if you like, to give you an idea, is similar to an electron.
Okay.
But the key difference is that there's no other interaction, the gravitational interaction.
Okay.
And that appears to be the basis for the dark matter distribution, which is enormously important in the universe, and in our galaxy, and around our galaxy, and in Sagittarius A. You cannot neglect this thing any longer, because now they are observed in the red dots, and the only way to explain them is use this result on dark matter and the mass corresponding to 10 to the 6 solar masses. And they are distributed all over. And I will be curious to see what your instrument can do to help understanding all this. And the red dots and the physics and all this physics. Everything was missed. If you were arriving here at the beginning, you will have learned a lot.
Yeah.
And to all the benefit of the University of Ferrara, to all the benefit of everyone, but I don't despair, because science will go over anyway, and maybe you can catch up.
No, indeed. Thanks a lot for raising this this point. Of course, I mean, this was a very broad presentation of the main target of the collaboration, which somehow is just on the statistical information. We're not really are going through the detail of single object and just looking to the distribution of object to extract some popular science. There is a lot to do. The quality of data is huge, but the important message to vehicle probably is that the Euclid collaboration is an open collaboration. So it's a European collaboration. Everyone can enter. Still now, in the future, it's not closed. We don't have fees to enter as other international collaboration. So if there are idea, expertise, everyone is really welcome to enter, to pursue eventually new things that we are not doing so far.
And they will be financed?
This I don't know. I don't know.
But this is an important point.
This is an important point. I mean, there are tables, board where these things can be discussed. I'm not in charge of this kind of discussion. But the important point is that you are really welcome to any new collaborators inside. I think that from the ICRANet network, there is inside the theory working group very active Antonio Nea Romano, for sure, that I know. Yeah.
Okay, I have questions. I have quick questions. Can Euclid probe the time variation of this Einstein cosmology constants, even spatial variation?
Well, I think that well, first things
we very large scale.
Yeah.
Okay.
Well, I think that one crucial aspect is the possibility to have access also to the information of perturbation. So the anisotropic.
Incorrect with the dark matter.
Yeah. I mean, I think from only background measurement, you eventually cannot do that. I think that if you have access to the background distribution and perturbation, so the evolution at all the scale of the homogeneous distribution of matter, you can eventually disentangle this effect. Then, of course, the point is that are your results relying on a model, how this thing distributes this and another matter, and eventually you might need good theory and different theory to test the data. But I think that this is possible.
Very properly, this omega 0 and omega r interpretation is a sort of effectively reflect to the variation of the dark energy in space and time interacting or incorporating with the dark matter.
Yes.
So that interpretation omega, you just put by hand. There's no really understanding.
No, I agree. And also it's not very big.
So measurement, it should be really reflect something
you
understand.
You're right. This is just a proxy.
Omega 0, omega A, omega B, what's that?
This is just a proxy, the first things that we can do. I mean, we have to do what people expect us to do. But then there is a lot of physical models that we are going to test. So this is the only zero things, but then there is a lot of things based on physics model that we can do, and that will be for sure way more interesting. But it's the first test to do. If you don't see anything, eventually, we are not really pushed to do for something. If you see something, then the point is that what is that connected with? It's true that parameterization per se is not very informative. I fully agree with this point.
Mario, when you mentioned this, the gamma parameter for modified theories of gravity. In lensing, this parameter is degenerate. It has a degeneracy with the mass models in lensing. So my question, if in this case, there is any degeneracy of this parameter with any other, or you really, from Euclid data, you expect to have really pinpoint this parameter?
Well, I can avoid to reply you directly. The point is that this parameter is terrible because it's a parameterization of the quantities that you cannot really propagate on all the observable. But someone wrote that in this report from ESA, and so ESA wants that we measure that parameter. So we will do that, but then we will go for physical mode. So it's very difficult to propagate that to perturbation, to background, to CMB, how to extrapolate that. So I think that we have if you assume a way to propagate this parameter using perturbation, BO, weak lensing, you can disentangle and have really the number that I was showing for the forecast. But also that parameter is way worse than what we were discussing about W0, WA parameterization.
I have a quick question. To your knowledge, can you put any constraint on self-interacting dark matter, whatever type, warm dark matter, whatever? Any constraint would be possible?
We will do that. We will do that already in year 1. There are already studies that will be dedicated to self-interacting mixed of warm and cold dark matter, decaying dark matter. So there will be a lot also in this regard. Thanks for the question.
Okay, thank you. Any other questions?
I like the fact that you mentioned LP.
Okay.
We are going to help him.
Okay.
And it could be a very good contribution to your team.
Yeah, he's super active inside the theory working group. No, I know.
Thank you, Malia. Thank you.
Thanks a lot.
We need the microphone. Yeah.
Okay.
This one? Yeah. Okay, I'll put this on the screen. Okay. Okay.
Okay, so we have Gregory. So Greg, the organizers talk. Cooling and emission of newborn quark stars.
Okay, can you hear me? So, morning. So I would like to return to the topic which has been discussed already in 2 or 3 talks during this meeting, and usually for Zeldovich mission, this is the 6th one. We try to find to report on a problem on which Zeldovich works himself sometime. So in this case, I would not say it's directly his topic, but it's related to the topic he was interested in, and the relation is the very strong field problem. Zeldovich published a report, a review paper with Popov about overcritical electric fields, and this back in '75. And he was, of course, interested in astrophysical applications of this problem, also in pair creation and so on. So there is some relation. So let me say just a few words. What is this topic? Of course, Professor Bulanov is an expert in this field, and I think his talk was not related to this problem, but I think you will appreciate this. So there is a statement or an opinion in the literature that you can find sometimes that such a huge electric field that can, in principle, produce electron-positron pairs, and this is the value you can see, 10 to the 18 volt per meter or 10 to 16 volt per centimeter, which is so-called critical electric field in quantum electrodynamics when the vacuum breaks down. So there is an opinion that such field cannot be reached in principle in nature. And why this opinion? It's sometimes attributed to Niels Bohr, but actually we could not find any reference. So why there is this opinion? Because there has been attempts in the laboratory, at least in different disciplines, to reach this field. Because potential observability of pair creation out of the vacuum is an interesting and predicted phenomena by Julian Schwinger. So there could be interesting to study this. However, attempts were so far unsuccessful. So one attempt was in heavy nuclei collision physics, and there was a hope to stick nuclei for a long enough time, heavy nuclei, completely stripped of electrons. In such a way, you can create a volume enough to produce electron-positron pairs. But the problem is that the time of sticking of nuclei was so short that this process cannot be observed. Another not related field is the field of ultra-intense lasers, where there are attempts to collide laser pulses with very high intensity. And so far, the best conditions could be created with optical lasers. And one of the places where this is done is LI in Czech Republic. And so far, again, the intensity is very much far below the requested intensities. The corresponding electric field would be 0.1% of the critical field. And in astrophysics, of course, there are ideas that such a field can be present in astrophysical sources, and two possible conditions to create such field would be the charge separation on macroscopical objects and the rotation of fast rotation of object endowed with a very strong magnetic field. Magnetars are observed, therefore this is a possibility, and therefore, of course, by induction, we should expect strong electric fields in these objects. So again, because we have these two possibilities, one detection in laboratory and one in astrophysical conditions, this field is, of course, of large interest. So when you have potentially creation of electron-positron pairs, in such critical or overcritical fields, pairs will be created in a very large amount, and we are talking about not just single pair creation, but electron-positron plasma. And the properties of this plasma should be studied using a kinetic approach, because just a thermodynamic approach is not sufficient. And this is the support for this statement comes both from observation of non-thermal spectra and from the theory. So we've been working on this field for quite a long time. So initially with Professor Ruffini and Shushenk, both present here with these physical reports, and later for some years also publishing some books. So the outline of this talk, it will be based on a series of works with my collaborator Nikolai Prokopenia from Minsk, from Belarus. And in one of the papers, also a Chinese collaborator is present. This is a specific problem, namely if you have an object with charge separation on the boundary macroscopic object, this should be a compact star, either a quark star or neutron star or whatever should be the method. It's important to have the charge separation. And if you have such an object in nature, how it will be appearing to an observer? This is the question. So what do I mean by a charge separation in this object? If I will specifically talk about quark star from here on, but there are papers also in the group of Professor Ruffini talking about neutron star with overcritical electric field at the boundary. So if this is not a new topic, of course, proposal of quark star goes back to the 60s when quarks were actually first introduced, and the idea is that quarks specifically are bound by the strong interactions, gravity, but the fact that they are bound by strong interactions with very strong surface tension limits put a very severe limit on the surface thickness. So the surface thickness should be of the order of pi wavelength, which is femtometer, and it's very sharp surface. So the density on the surface of quark star drops down from what is going on here? Supranuclear density up to basically 0 on pi wavelength distance. Instead, electrons are interacting with quarks by electromagnetic interaction, and due to the Pauli principle, they cannot be put with arbitrary number in a given state. Therefore, they are simply cannot be compressed following the complete charge neutrality condition, so they are extended over the surface of this object. So the extension is microscopic, is of the order of Compton wavelength of electron. This is farther than the pi wavelength by 100 times. And however, you understand that the surface of the object is microscopic. Therefore, even if you have microscopic thickness of this surface, it's macroscopic in volume. Therefore, pairs can potentially be created. The value of the electric field on the electrosphere object, the surface is called electrosphere. The value of electric field in electrosphere is actually overcritical. So this has been known from the 80s, but nobody actually considered any effects of that until Usov made a statement that, well, if the object is there, it can produce electron-positron pairs. The only condition you need is that the temperature is non-zero. At zero temperature, there is a full degeneracy of electrons, so all electronic states are occupied, and there is no possibility to have a new particle filling some empty state. But at non-zero temperature is possible, and Usov conjecture was that you can have just born object with high temperature, and this hot quark star should produce an enormous number of electron-positron pairs. In addition to that, slightly later, people considered also photon creation in this electrosphere, and I will come to this later on. So first, to understand the structure of electrosphere, you should actually understand what are the processes, what are the conditions there. And Usov originally just made a qualitative argument how pairs are created, considering the pair creation rate and the thermalization rate of electrons. And this qualitative argument resulted in a formula which has been used in hundreds of papers later on. Well, we actually revisited this situation following full kinetic treatment and found some discrepancy with the model. So I'll briefly report on this this work we did in the beginning, and then later the consequences of it. So to study what happens actually in electrosphere, we should consider various processes. This is pair creation itself. This is necessarily taking into account Pauli blocking of electrons. And then, of course, to consider thermalization, we must take into account particle collisions. And beside that, of course, this happens in a strong external electric field, external in the sense that this field is acting on the particles moving in it. Therefore, back reaction of charges on the external electric field has to be taken into account. So this can be done using the generally Vlasov-Maxwell equations, but these equations are reduced to basically two dimensions in momentum space and one dimension in physical space, and time dependence, of course, in this problem. This is quite a complicated problem. It's solvable by numerical methods. So you can see the equations here. The first one is the Vlasov plus Boltzmann terms equation, and the second is the Ampere equation. They take into account, as I said, Pauli blocking effects, collision between particles. They take into account the particle current, polarization current, the Schwinger rate, and it's possible to solve this equation. What is important is the boundary condition. So as I mentioned, if you have zero temperature, so cold system, the distribution of electron follows basically the electrostatic condition, which results in this electrochemical equilibrium, which of course requires that there is no change in the distribution of particles. And the boundary condition corresponds to the Poisson equation, basically with some charge density of positive charges, quarks in this case, which can be considered as a step function given the difference in the distances. And through this, one can find the electron distribution so consistently with the electric field. This is done in all the works. And as a starting point, what should be the electron distribution? One can, of course, take the Fermi-Dirac distribution. However, what we find is that this is a good starting condition, but then, of course, the equations show that the distribution adjusts to the self-consistently to the properties of the system. So the per creation rate can be computed again with the Schwinger rate here, differential Schwinger rate, and then out of this luminosity, final observed quantity would be the luminosity of electron-positron pairs, which can be computed basically integrating to the volume. And it's important to consider not only the rate of created base, but also their motion. And of course, they are put in external electric field. Therefore, they are accelerating or decelerating. Electrons are decelerating outwards, positrons are accelerating, and they are moving with the relativistic velocity. Therefore, the Lorentz factor should be also taken into account. This is the figure which shows the luminosity as a function of temperature. The blue line is the estimate in Usov paper, which was used in the literature, and the red line is the calculation we did back 2 years ago. So you can see difference both at very high temperature and very low temperature. This is significant difference. This is a logarithmic plot, and the rate changes here, for example, 5 orders of magnitude. Therefore, this is very important effect. And on the right, you can see the normalized electric field, red, and the rate of pair creation, blue, as a function of distance from the surface. So surface is here, and these are in Compton wavelengths the distance, 1, 2, 3, 4. So you can see that despite the electric field is maximum of electric field is located, of course, on the surface of quark stars, the rate, the maximum of the rate is shifted to larger distances, where electric field is relatively small. And this is a direct manifestation of Pauli blocking. So electrons are completely degenerate near the surface. So there are no phase space for electrons, positron pairs to be created. So there is no creation here. Pair creation happens outside the surface. And this is also important effect. Now, this is the result of the solution of those equations I showed you, with initial conditions showed in black, and the stationary condition that we find as the system evolves, shown with colors. So on the top, you see electric field in terms of critical electric field, and in bottom, you have density of particles in Compton wavelength, in Compton volume, and the horizontal axis is the distance from the surface. So you see initial condition we assumed were that the particle follow exactly Fermi-Dirac distribution with a given temperature. Therefore, at certain density, a certain distance from the surface, the density drops to 0. And the electric field correspondingly goes to 0. But the solution shows that when pair creation starts, and not only when it starts, but when the system starts to evolve, electrons start to extend. This is basically evaporation, like in our atmosphere. Particles in gravitational field evaporate outwards and extend in principle, having cosmic velocity, they just escape. This is the reason why the Earth will look like Mars in a few billion years without atmosphere, basically. So electrons are actually evaporating from the surface, and this is purely kinetic effect. It cannot be obtained with the thermodynamic methods. And then also electric field, these are electron, blue electron distribution, and electric field consequently also extends outward the surface. This is lesser than the critical field. However, considering the volume, it contributes significantly to particle acceleration and consequently to the rate of pair creation, not to the rate, to the luminosity of pairs. And in yellow, you see amount of positron created. So they are created near the surface here in the maximum, and then they are moving outwards, accelerated in the electric field. So this is the stationary solution to those equations, and it shows that electrosphere is actually extended quite a lot compared to the pure electrostatic solution. And these are the Lorentz factors for 1.5 MeV temperature and 3.5 MeV temperature Lorentz factors of electrons. Here is function of distance and of, these are positrons, they are increasing, so positrons are accelerated, and these are electrons, they are decelerated, but still they are moving outwards with quite large Lorentz factors. And for higher temperature, Lorentz factors increase even more. So this was information about the behavior of electrosphere on relatively small time scales given external temperature. So are there any possibility beside non-zero temperature to create pairs? Yes. You can in any way perturb the electrosphere, so the electrons fully degenerate initially can be perturbed, and then electrosphere starts to adjust itself to a new state where particles are created. So this is one of the examples. This is fully degenerate electrosphere, electric field function of distance, and electron distribution is function of distance, and the corresponding phase space of electrons. So you have on the vertical axis momenta, parallel to the field probably, and on the horizontal axis you have the distance. So all these states inside the yellow curve are occupied, and electrosphere doesn't produce pairs. When we perturb, so just make a push of this electron in some direction, and this is the perturbation. Of course, the system should relax to some new state, and what happens is, well, it's quite a complicated plot, but I can illustrate. On the left, you have energy densities in various component electric field, electrons and positrons. On the right, you have particle densities at different times. So this is first line on the top is a Compton time, 15 Compton times in the middle, and 30 Compton times in the bottom, where we actually reach the stationary solution. And you see that if you perturb initially, this is the small perturbation initial state was with the dashed condition, the dashed line, blue line, you have electric field is also going to be perturbed. So initially you have a relatively small field, but then it starts to increase. Then it remains in the surface where it's producing pairs. You see a number of positrons is increasing in yellow. First, positrons were actually created in the inner part inside the surface just because electric field oscillates quite a lot initially to adjust to a new state. And then all the process continues, so positrons and electrons escape, and again we come basically to the same condition that we see at non-zero temperature. And this is again energy density of electric field, energy density of electrons and of positron as function of time. So you see again these oscillations, so the adjustment of electrosphere and the corresponding phase space. So deep inside the star, the situation remains completely degenerate, and on the surface there is release of degeneracy and consequently possibility of pair creation. Yeah, I mentioned that also photon emission should be considered in this object, and this is a non-trivial point, so I would like to dedicate some time to this first before coming to the last part of my talk. So initially it was assumed that quark stars, or anyway such a dense object, cannot in principle emit photons, and the reason is very simple. The density of quarks is supranuclear, therefore you have the corresponding plasma frequency, which is of the order of tens of MeV. And of course, given this huge plasma frequency, all the electromagnetic radiation below this energy is not possible to emit at all. So this object was assumed to be, using Alcock expression, a silver sphere, an object that cannot actually emit from inside, and it can only reflect radiation coming to it. So this has been quite deep-rooted opinion in the literature. However, in the 2010s, roughly, people started to consider the effects of electrosphere itself, the motion of electrons. And the first works were treating electron-electron Bremsstrahlung, so collision between electrons in the electrosphere to produce radiation. It was Zakharov who first in 2010 and 2011 showed that the most dominant process, however, is not a particle collision, but the Bremsstrahlung of electron in external electric field itself, the very basic process, the breaking radiation. So he computed both the emissivity of electrons and spectra. But strangely enough, nobody followed this work, and nobody actually studied how what is the implication for observation. So I'm going to talk about in the rest of my talk. So the photon rate was computed very sophisticated method using basically the analogy with the synchrotron radiation theory. So the photon rate takes into account, of course, the degeneracy of states of electrons, here Pauli blocking, in other words, and also takes into account the plasma frequency or effective photon mass, which is related to the Debye mass of photons given by, in fully degenerate case, there is simply a function of the chemical potential, but if you have temperature, is also a contribution from the temperature. And the luminosity is given by the integral over momentum space and over the spatial distance. This is the final plot about the various luminosities in this problem. So on the left axis you have luminosities in arc per second, and on the bottom you have temperature. So in black is black body, is just a proxy to everything you see. Again, the surface is not emitted as black body, and in the sorry, by blue line we see the luminosity of photons, and red line shows the luminosity of electron-positron pairs. Surprise, because pairs have lower luminosity compared to photons. Therefore, the dominant energy loss mechanism from the surface is photon emission, not pair creation. Okay, this first statement. Second, the luminosity of photons is comparable to black body, as Zakharov actually found. It's slightly lower. Actually, the luminosity of pairs and photons almost coincide at very high temperature, but this is not very much relevant for observations. So going to lower temperature, if we have this surface cooling, we see that both luminosities actually decrease exponentially with temperature. And this is not surprising. Again, Pauli blocking. When electrons become more and more degenerate, there is no possibility for them either to emit or to create empty phase space for particle creation. And on the right, you see the rate of photon emission as function of the distance from the surface. And again, same feature, you see that photons are not generated on the surface itself. The maximum of the rate is displaced outwards from the surface, again, due to the Pauli blocking effect. So far, we discussed just a simple problem. If you have a temperature, constant temperature, what will be the percolation rate, luminosity in electron-positron outflow, and the photon emission rate, or luminosity in photons. But real objects, of course, cannot stay at a constant temperature. If this is a star, when it's created, so by the way, where does the temperature come from? When you have a collapse, for example, of massive star, it's heated, therefore the temperature comes from the gravitational energy. There is an alternative possibility. Neutron star can be transformed to quark star. This is the combustion process. It also operates releasing energy, and this energy goes to the thermal energy. So the temperature can be increased, and it was shown that it can reach tens of MeV initially. And then the question is, if you have such hot, bare, I'm using for the first time term bare, but it's essential to have this surface without any external matter, because if the matter is coming to the surface, all this region with the overcritical field is covered. But it was shown that due to very strong outflow initially, a hot object will not have any matter on the surface, so it's bare initially. So then, if you have such hot, bare object with electrosphere exposed, what should be the evolution with time on observable macroscopic time scales? So to address this problem, we solve, as many other people do, the heat transfer equation, and then considering that making usual assumptions that the heat capacity is mainly due to quarks, and also heat transport is due to quarks as well. And the main cooling mechanism would be two. One is the surface cooling, according to these two phenomena I described before. And the second is the cooling of the interior. So the only particle that can escape from the interior is neutrino. Therefore, neutrino cooling is essential to have the cooling dynamics fully understood. And of course, talking about neutrino, it's well known that at very high temperature, this object will not be transparent to neutrino either, because neutrino cross-section depends very strongly on the temperature. And we considered also that case, and noticed that taking into account neutrino opacity does not change very much qualitatively the results. Therefore, I will not discuss this in more details. So the heat transfer equations. So this one, the boundary condition correspond to the two main processes that I discussed, the Schwinger term and the Zakharov term or Bremsstrahlung term. And we assume for simplicity that the object has uniform temperature, isothermal. This might not necessarily be the case, but it was shown that neutrino actually very quickly redistribute heat inside the star. So on observationally relevant time scale, it would be enough to consider isothermal distribution. And of course, everything depends on the state of quarks inside the star, and there is vast literature on this. So quarks might be not paired at all, so just free quarks. Quarks might be in a partially paired state with a different equation of state and different properties, and quarks may be even fully superconducting with all quarks paired together. And this depends on the density and many unknowns in the theory of quarks. Therefore, we considered all of the cases, but there is little difference concerning the cooling, especially in the time scale of interest. And on the left here, we show the result for unpaired quarks. On the right, I think this is 2SC, so-called. So when you have just two species of quarks paired, and on top you have temperature dependence on time. On bottom you have luminosity dependence on time, and colors show different components. So neutrino shown in green here. Oh no, I'm sorry. This is the temperature at the different parts of the star. So this is the surface temperature is in blue here, and the interior, basically central temperature, is in green. So you see, and time now is not in Compton units, it's in seconds. Therefore, we start with very early, 10 minus 10 seconds, and then we evolve up to 10 to 5 seconds probably here. So, luminosity in neutrino on the bottom is shown in yellow, and in surface luminosity altogether is shown in blue. Well, qualitatively there is a little difference, even if quantitatively there could be, because of different heat capacities and different neutrino emission rates. But you see that generally we expect, as usual, at about a few milliseconds or 10 milliseconds, the core starts to, the temperature in the core starts to decrease due to neutrino emission. And then this, of course, changes the properties of the surface emission. But the surface is cooling much earlier. And the reason for that is, of course, very strong emission of photons and electron-positron pairs. And luminosities, you can see, they are huge initially, but this is not observable. So if you look at time scales potentially observable of the order of second or less, these are quite high luminosities, above 10 to 40 something erg per second in all the cases. So this is quite below gamma ray burst luminosity, for example, but this is higher than a neutron star luminosity, just born neutron star. So in principle, such objects can be observable. Apart from the luminosity, what can we say about the observational appearance? The spectrum, of course, and the spectrum is the key to this object, I think. This is the main result we obtained in this paper. And this picture shows the spectrum as function of energies for different temperatures. And in dashed line, we show black body for comparison, and in thin line, we show the spectra of electrosphere, photon spectra. So you see at a relatively large temperature, 0.1 MeV, which correspond in the previous figure to roughly, what is 0.1? Let's look here. To 10 to 5 seconds, for example, for 2SC quark star. The spectrum is close to black body at high energy, but it has a sharp cutoff at low energy. And of course, the smaller is the temperature. Red is 0.05 and blue is 0.01 MeV. The high energy part remains the same. We just decrease the temperature, but low energy has always the same cutoff. And this is the cutoff due to the plasma frequency I showed before. And this is the characteristic feature of this spectrum from electrosphere. Can we see directly this spectrum? Yes and no. In the beginning, when we have, I don't know if I have slides here, yes. When we have a temperature exceeding 22 keV, photons have sufficient energy to produce electron-positron pairs by photon-photon, Breit-Wheeler process. And when they produce pairs, the amount of luminosity is huge, the amount of photons is huge, therefore we produce opaque electron-positron photon plasma. This plasma, near the source, near the electrosphere, is well-known probably in gamma ray burst, but also in many other areas. You create unstationary electron-positron plasma, opaque, and this plasma starts to expand like in fire shell or whatever model you like. So then expanding plasma is still opaque until its temperature drops down to a certain value, and then because electron positron annihilate eventually, so then you can have photons streaming freely to the observer. And this happens when the temperature is about 22 kiloelectron-volt. Very characteristic temperature. It's well known in the literature, and we also derive a nice simple equation to show this. So if before this temperature is reached, so when the star has high temperature, we see just black body emission, because when the photons are emitted from the photosphere of this expanding electron-positron photon plasma, you see just essentially black body. This is a property of this electrosphere, of this photosphere. We studied this with great details, and the problem is not a trivial one, but the result is simple. We see just black body spectrum with decreasing temperature. However, when the temperature finally, the temperature of the surface reaches the value of 22 keV, the spectrum we see will be this one. Will be this one. So we'll have not a black body, we'll have a very sharp cutoff at low energy. And this low energy is not actually very low, it's 44 keV, if I remember correctly. Yes, and then this is a characteristic feature of electrosphere. And it is observable. Yes, it is observable. Of course, the luminosity will be much lower, and the intensity that we see will be much lower than at higher temperature. But still, this is observable, and this is the main prediction from these results: is that if these objects exist in nature, we should see a transition of the spectrum. Initially, it is black body with the temperature decreasing with time as a power law, but then when we reach 22 keV temperature or certain time in observation, we should start to see this sharp cutoff at low energies due to the properties of the electrosphere of this object, and due to the properties of the plasma frequency of electrons in the electrosphere. And well, we have many observational facilities now, so we hope that in future such spectrum could be detected. If not, this would be a strong indication that these objects either are very rare or don't exist at all. So it's a prediction, and I'm happy to give some prediction at least in this work. Okay, I think I finished. Thank you very much.
Question, comments?
It reminds me early era of pulsars. When pulsars were discovered, people considered spherically symmetric star and what happens on the surface. Then people realized that the star is rotating and it has a magnetic field. Do you have a rotation and magnetic field in your stars?
Good question, of course. No magnetic field, and reason could be various, superconductivity in the star and so on. But the question is that, yes, in principle, if the object is rotating and there is no intrinsic magnetic field, magnetic field will be generated in electrosphere. It will change slightly the properties of emission, but not much.
But inside also magnetic field can be, because of
interior.
Ginsburg considered neutron stars. They said the magnetic field in superconductivity second type appears in the form of the vortices inside the void.
Yeah.
And the station is more complicated than in the first paper, but nonetheless it can be inside also.
Sure.
Should I repeat this question? What are my comments? You see, it was when neutron stars appeared to be understood better and better. Kirchnitz and Ginsburg and Kirchnitz, they great experts in superconductivity. They said that neutron star material will be in a superconducting state. And the magnetic field in superconductors can be, but in the form of the vortices. It's not homogeneous, but it's some properties of these vortices which are known. Why not?
Well, this will be different. It's not, they don't treat this case here.
Yes, but they don't, I know that, but my question, maybe next step will be to treat this question about the magnetic field, about the rotation. Otherwise, pulsars would not emit any radiation which we observe if they remain spherically symmetric neutron stars. And next question, if I have a microphone. You considered bremsstrahlung as a collision of particles of high energy, and you should have secondary avalanches or generation of electron-positron pairs due to like beta-Hiter process. Did you consider it?
Okay, let me first answer the first question. I fully agree, magnetic field have to be considered in this problem, and this is the next step indeed that we proceed. But first we need to understand the simplest cases, otherwise progress cannot be done. About the second point, this is very good question, thank you, but actually the condition in the electrosphere itself is very peculiar, it's collisionless. So you don't have direct collisions outside, the flow of electrons and positons is outside. Okay, and of course at certain distance they start to interact, but within the electrosphere itself, where the acceleration happens and when percolation happens and photons are emitted, particles are collisionless. Yeah, so yes, we were thinking about the avalanches as well, but the result is this. Of course, inside the surface density is huge, therefore there is a collision effect, and this collision effect, and it has been treated to explain the temperature, establishment of the temperature in the system.
Yeah, thank you. I think you already mentioned this in the talk, but can you just clarify again how sensitive the spectrum is to the microphysics, like the kind of, if it is superconducting or not, and all those other details? Is the spectrum sensitive, or, you know?
Thank you for the question. Yes, the result is simple. Spectrum is not sensitive provided that you have the structure of the field that you see here. The structure of the field is given just by the charge distribution. So if the surface tension of quarks is such that is expected, then you automatically have all these results.
The pore does not matter.
Yes, exactly. Okay. The pore doesn't matter. Yeah.
Okay.
I am a little concerned, not too much, but I just was seeing this Uzov paper. Then we start to work, I see a citation of 2007. And then there was a further progress around 2010. We are now in 2025. And I'm concerned because what could have been a good problem in 2007 and in 2020, which has been cited, is not necessarily of current interest. And of course, it is interested by itself, but it's not clear that we are facing something today. What we are really interested, and there is a work going on with our chairman and Shurui, especially Sampio Kim and all this group that they have been inside here for a month. We are interested not in Uzov, we are interested in critical field which can be related to gamma ray burst, and especially to gamma ray burst which don't emit in this energy of KV, but emit in the TeV. This we have 5 or 6 papers in preparation. But you cannot proceed in this field without looking at the observation which we are receiving and dramatically change the theoretical outlook. Again, we are looking, we have papers in preparation with Sampio Kim, with Otter and Shuruya and Wang Yu and so forth, which are trying to solve a critical field, not the Heisenberg-Euler, not in Usov, in as a source of TeV radiation, in millisecond binary pulsar. This is, rotation is the key. Critical field is the characteristic. TeV radiation is the characteristic radiation. I'm concerned that we are not penetrating this distinguished group with this problematic, but we are going on anyway. Thank you.
Okay. No need to reply, I guess. Okay, thank you.
Okay, so our last speaker of this morning, Mille.
Interesting. Can you hear me? Yes. Okay. Thank you for opportunity to participate at this great meeting. I'm Mile Karlica. I come from Astronomical Observatory of Belgrade, and I will present you some ideas which kind of coalesced between astrophysics, because I started doing this in astrophysics, and I started slowly moving to electrodynamics and to, like, how to say, plasma physics itself. So the talk is about synchrotron radiation within non-homogeneous astrophysical radiator paradigm. So not to talk too much about synchrotron radiation, I'm quite certain all of you know, like, what is the basic assumptions of it. We have a gyrating particle which keeps the constant radius and proceeds through the magnetic field. We have some pulses which are Lorentz transformed to a very narrow angle, and they go to observer, and then we through that calculated the spectra as it's shown here. So, like, due to the Lorentz transformation, like, if it's a very low velocity, it is energy of the particle, you will have a synchrotron, then you will have something like cyclosynchrotron transitory behavior, and then you have like pure synchrotron. Now, this derivation is quite useful, but generally it started from the laboratory setting, like Electra you see here. So from a setting that you need to calculate the intensity and the spectral signature of a beam in a synchrotron. Is it really applicable in the astrophysical setting? That is the question we are trying to answer. In astrophysical setting, we don't have homogeneous fields. We can have different geometries of magnetic fields. We can have different rates of change. They can be either regular, but non-uniform and non-homogeneous fields, and they can be stochastic, therefore, or turbulent. So we need to see where are the limits of our standard synchrotron approach, where we can use the synchrotron and where we need to be careful, and also a bit to extend the viewpoint. When you like do a lot of simulations in astrophysics, they generally assume singular magnetic field strength, like they promote a small zone which emits some radiation. They say magnetic field is such and such, whether it's like 10 Gauss, million Gauss, doesn't matter, and then they calculate the spectral profile. But like even in this basic assumption, we see some challenges.
So the motivation for my work started in Sweden in 2017, where I was examining how to reconstruct the magnetic field distribution from the radio supernovae, because radio supernovae have a flat-topped absorption spectra. So synchrotron absorption is not as an abrupt function from nu to the 5/2, then to the downward power law, but it's like something which generally observationists were like parameterizing with this parameter xi, which would like pull down the top and spread it out. And there was a need for how to say, physical interpretation of this thing. And the physical interpretation was proposed by Professor Bjornsson and Keshavarzi, that this comes like, how to say, from a distribution of magnetic fields which contribute with different absorption frequencies together, and they like, how to say, have a collective spectra which is flat-topped. Later, in 2024, I did like the numerical way, because, how to say, I brought a bit of foreknowledge from solar physics, where there is a common knowledge how to reconstruct magnetic fields from data sets to supernova field, and we managed to basically see that certain radio supernovae don't radiate at single magnetic field, that their ensemble of electrons could be radiating within like 2 orders of magnitude. Okay. Another point which is interesting, but it's still in development. So this was just like a starting point in which direction to push our research, is the behavior of charged particles in non-homogeneous magnetic fields. And for this special case, I was mostly interested in the, how to say, significant drift within one gyration. So like I made like a 2D magnetic field, which is like reminiscent in this sense to toroidal magnetic field, which is common in some astrophysical objects. And wanted to just see where are my limits of applicability of synchrotron theory. So for very low energy particles, the drift is very small. Intrapulse profile is barely affected, and they are all equidistant. So in this case, synchrotron still can be like safely used as a toolkit to calculate the spectra. Still, like you have some intermediate, and your pulses get a bit narrower, a bit more deformed, but they're still well. But if you have a very high energy particle, you have like basically very stochastic pulse arrivals, and you have significant changes in each pulse. So like, because it scans way more magnetic field values while the pulse passes through the view of observer. Now, this is the motivation. This part is a long-term, how to say, motivation to continue the work, but we will now concentrate on low energy case. So where our drift is slow, and we like can approximate with synchrotron theory. So we built up something called NAR paradigm, because when we started the project, we needed a name for non-homogeneous astrophysical radiators. It's a development of approach to address various levels of non-homogeneity of quantities which influence non-thermal synchrotron radiation. And name NAR comes mostly because in Serbo-Croatian, which is my native language, NAR is, like in Persian and some other Central Asian and South Asian languages, a name for pomegranate. And pomegranate reminded me and my colleagues to the often observed structures and magnetic field geometries we see in universe. So since using like a completely ab initio numerical or analytical approach is quite complicated when you calculate the paths of each electron, then you first calculate the path of electron in non-homogeneous field, then you through linear Wiechert potentials calculate the electric field of the observer, then you do the Fourier analysis to extract the spectra. This is a bit beyond our current, how to say, computational and time limits, but we are working on that. We just assumed, as I told, like the still functioning synchrotron approximation, but we say, okay, we have synchrotron still works. Okay. We are still not in that regime where it doesn't work. Like we are far away from this transitory behavior, or like jitter. Jitter is something we don't look at. But let's then assume how would, if we had like a non-homogeneous source, how the spectra would look if synchrotron works. And we assume like we have a volume integrated flux where we have like a synchrotron spectra, a single synchrotron particle spectra times the electron density, which is function of energy and radius, times like the dB times volume. Now, of course, there is another approximation here that the distribution of electrons is isotropic, but for simplicity, we also assume that. Now, since finding even this isotropic electron energy density would require another layer, which is very long to calculate, we try to, and how to say, it's very hard to categorize the observation by example on that way. We used this zonal approach, like in case of Bjorson-Keshavarzi. We said, okay, let's have a magnetic field distribution, which is given as a volume filling distribution of certain magnetic field values. So this is this calligraphic PB. And let's make it that it's so zonal that in this intermediate step, each electron density can be given as a function of energy and magnetic field strength at a certain zone. And another crude approximation is just, okay, we say, depending like on the size of the emitter, if the emitter is relatively small and these electrons can diffuse quite fast, it can basically also homogenize. So we can take a unique electron energy density. Now, what do we use later? We will like made an example of a n sphere where n is smaller than 3 with this volume, and the magnetic field structure is given with this power law with the distance, which gives us this PB as volume per magnetic field to be of this order. And we use the single electron distribution with a power law index of -3.3. And this is what we get. So we get like the blue curves are the curves of the synchrotron spectra in homogeneous field of same total magnetic field energy. So like, let's say if the average is the same, so we have same average magnetic field energy density in both cases. You see first that like in first case, it is seriously boosted, but the form of the spectra is not so much changed. But if you have like m equal 1 and in n equal 2, so magnetic field index is 1 and the dimensionality of the n sphere is 2, you see that it started to show this transitory behavior. So you basically have shifted this, how to say, power law from the homogeneous case up to a higher energies, but there is also a transition with additional power law. And so for like, you also have here that is just like pushed up, but then like the tail is boosted to higher energies. So it's very hard, like if you have magnetic field inhomogeneities, we need to be careful when we talk about what is synchrotron burnout frequency, because it's not a single number. The same is for this set of parameters. Now, this looks familiar. And I don't claim that I explained the Crab without this reconnection, because most of the electrodynamical models show there must be reconnection. But on the other hand, whichever model of Crab I read, they used singular magnetic field. And singular magnetic field. So they use like 180 microgauss or so, 300 microgauss, doesn't matter. It's one number, and they put the broken power law injection of electrons. Now, it would be interesting to address a bit the inhomogeneities of magnetic field to see basically the proper and true efficiency of reconnection process in Crab. That's my point. So, yeah. Another thing which can be also observed is, again, let's say, I first was reconstructing the magnetic field from observation of radio supernova, but let's now model the effects of synchrotron self-absorption in homogeneous magnetic field. So we can have some profile. I chose this one, which is exponentially decaying on a 2D shock wave for a special case. Now, of course, this depends on geometry. For some, like, how to say, general potato, this is not a general potato, but it, like, in long term, we will also work on code to calculate that. So we have this kind of exponentially decaying magnetic field after the shock. For this field, then for this magnetic field, then electron density energy distribution, we can solve the radiation transfer equation along the line, along the rays, so the ray tracing along the lines of side, and this can be done like for each spot on the shock front. Now again, we use now this FB0, which is kind of like a distribution of the maximum of the magnetic fields on the shock front, and we get the effective specific intensity. So this effective specific intensity is the summation, the integral of these specific intensities for each magnetic field zone integrated over all magnetic fields. Shocks are very thin, so in our first approximation we use that profile along the shock wave, and the most dominant contribution comes from a homogeneous zone, let's say, relatively homogeneous in the depth of the shock. So the majority of effects come from the inhomogeneities in 2D. So how we look on shock front and how much of the shock front we see. And we parameterized the magnetic field distribution as a power law between maximum and minimum magnetic field values, and also parameterize the electron energy density the same way as a power law. And these are the results. So technically, when your magnetic field parameter is big, basically the lower part, there is no transitory behavior, special transitory behavior in the absorption part, because the low energy, low magnetic field radiation mode is dominant. So you have this, but like on the higher end, you have this push toward a bit higher energies. So as previously, your burnout cutoff is pushed up. But when your magnetic field parameters Xi is low, you have a very, very long transition zone, which is both dependent on what is your minimum magnetic field and maximum magnetic field. This can be seen. Let me just find the plot here. So you see this is like rising magnetic fields, and you see how your transitory zone technically grows. Why is this important, for example, in GRB physics? Because very often people in GRB physics speak about synchrotron theory in the framework of single magnetic field, and they mention something called synchrotron deadline. Mention synchrotron deadline. So deadline is like a very, very hard photon index on the lower end of the spectra of the prompt emission of synchrotron. And often, like, one of the way around was like to introduce a thermal component. But what we propose is, for example, for a case of GRB 230307A, is an R model, so that we have an ensemble of magnetic field values. And you see, so this is with photon index 0.5. So standard synchrotron theory cannot explain it. This model fits better than cutted power law, which was used to fit the data. Because if you invoke magnetic field distribution, and if you have enough electrons in the zone that they can contribute into self-absorption process, you will have multiple absorption frequencies with changing intensities, which can reproduce different indexes, photon indexes, and even like very, very hard ones in early phases of a GRB. Now, why we started doing this? Like, this is still work in progress. And coming from a toolmaker family, my father finished like metal worker toolmaker school. You know, you always need a good tool to work with things, like with screws and so. So for me, a very good example is a torque screw. Torque screw, if you that's that star screw you use. You can turn torque screw with a flat drive and with a nimbus, like hex drive. With a flat drive, you can try to turn torque screw. It will work, but there is a big danger you will break the flat drive. With a hex screw, you can turn it, but it's a big danger you will destroy the torque screw. So it's a bit better than a flat drive, but anyway, it's still not there. So we need torque screwdriver to turn the torque screw. So also we need a proper approach for synchrotron theory, like to cover all the, how would I say, zoo of correlation lengths in magnetic field we observe in astrophysics. So whether it's like pure synchrotron, where the correlation length is very large compared to the Larmor radius of the particle, toward jitter, where like it's the other extreme, where the correlation like is so small that particle doesn't manage to gyrate. In essence, in between, there is still a big hole. And these are the conclusions. So basically what ever I said, like I think the major point is the last one. So this is something which is still in development. So any constructive criticism, advice is more than welcome. And I would kind of dedicate along Zeldovich this lecture to two people I didn't meet. Maybe you know them. Yeah, these are Sokolov and Ternov. So they are contemporaries from the Moscow State University, and Sokolov and Ternov were like, their book on the relativistic electron was one of the major contributors of me continuing in this direction. Thank you. Any question?
Is there any question from the audience? Well,
also, a comment is a good thing.
One of the most important work that we did in the study of the afterglow of the GRB was a work in which a very important contribution was given by our speaker now. And I think it's very appropriate that he celebrates Zeldovich, but also Sokolov and Ternov, because we start to learn about synchrotron on their books. And I think you use the books that we had in the library. So therefore, we are grateful to Sokolov and Ternov, even today, for their work that they did at that time in Moscow. But I would like to go back to your contribution with us in the afterglow. And now we are in a magic moment, because I hope to collaborate with your university. I will sign the collaboration agreement with your observatory, because we have a different point of view, which is based on your initial work, namely that the synchrotron radiation in the afterglow, in the afterglow, originates from the remnants of the supernova. Therefore, your effort in building up from inside with different magnetic fields and so forth fits perfectly with your initial work. And I think we should collaborate in this direction, because it's very exciting. It's a global point of view. And we have the fortune of a work which we are going on with Moradi and with Orge on this synchrotron from the afterglow in 220101, but in all of them. And it's extremely exciting that we start to find correspondence.
Sure.
Therefore, I look forward to start again a very strong collaboration like the one historical we had when you prepare your thesis here.
Yeah.
Thank you.
Thank you.
Thank you for the beautiful presentation and for these beautiful pictures.
Thank you. Other questions or comments? If I may, very short.
Yeah.
So the difference with the standard synchrotron you show is evident in burnout limit or in self-absorption frequency.
Yeah.
Okay, but maybe you have some other insight. For example, I don't know about the inhomogeneity, and I fit with the standard synchrotron. What would be the error I infer from the
it's very complicated question. Like just 3 days ago, I found a paper by Beskin or something like that. And he wrote like about synchrotron in homogeneous field, which progresses in like a poloidal field. And per particle, you would see some effects of inhomogeneities, but if you take an astrophysical source, he says it averages out. But that works in that geometry because it preserves the adiabatic invariant very well. If your geometry doesn't preserve adiabatic invariant very well, like the one I presented, which is more close to toroidal magnetic field, or if it's like turbulent, which is even crazier sense, so you have like, you know, current sheet zones where you change the sign, this collapses. So you will see like significant changes in how your pulse cone passes through the observer, which will change also like how your spectra is like it can be pushed to the higher energies and so on. But you know, since you know it's a very simple problem in terms of mathematics, it's you know, Lorentz force and Maxwell equation, but when you put a complicated setting, computer needs a lot of time. Like you know, in standard like gravity models also. Like so, for this we are now looking forward because in Kragujevac in Serbia we opened a data center and a computing center with like large, let's say, supercomputer, and we will get more opportunity to use their facilities to calculate there.
Okay. Thank you. And
Thank you.
I think at this point we thank the speaker.
This is an exciting afternoon. Laura Pescara will be with us from Chile, and we will have the great pleasure to have, I see almost everyone, but I don't see yet Giorgio Sonnino. Giorgio Sonnino is a very good friend, and he's from initially from Pescara, and we developed some key idea, and I hope he will be in the afternoon here with us. Okay, and we have a very intense program, and I took for the Fernando Izaurita, I took I'm a little bit embarrassed. I am a little bit embarrassed. Where are you? I'm a little bit embarrassed because I spoke about Claudio Teitelboim, which was before Teitelboim, and now is different, his name. And I promised to take a picture. That is very funny what I will show you. I show you the picture of Wheeler, and there was somebody missing in the picture, and it was his arm in the picture, and I show you the final one. I told about a meeting we had with Claudio, with Yuval Ne'eman, and with the president, Weizmann, of Israel. Now, I have to show you, I was a little bit unhappy because we were 4 people there. Looking at the picture, there, not by his arm. There is Weizmann and so forth. There is a foot there. That foot is of Claudio. I will try among, here you see, is a foot. Therefore, I will try to find the original large picture, because that day was very important. And the mother was Weizmann. The president said, how many and Claudio answered, and the president said, oh, good, like himself. Therefore, show to you.
Oh.
Okay, so welcome back to the last afternoon of this wonderful conference. So we will continue with a few more talks. The next one will be given by Laura Pescara, and she will talk about the topic on the formation of compact object binaries from binary-driven hypernovae. So the floor is yours.
Okay. Hi, everyone. I think it's good afternoon. Well, I'm going to tell you about the binary-driven hypernova model. And this is a work that has been done by some time ago in my PhD and even before, and it has been done with the ICRANet collaboration. So, let me put this. Well, gamma ray bars has been detected and studied in the 60s by many surveys around through the years, and some of the characteristics of this kind of event is now well known and in concert with all the scientific community. And these events are the most energetic events observed in the universe. They have isotropic and isotropic distribution in the observational universe, and they come in a bimodal distribution according with the emission of the duration of the emission of the 19% of the energy. Is this energy is emitting in less than 1-2 seconds, they are short gamma ray bursts, and if the time is longer, around 100 seconds, there are called there are long gamma ray bursts. With the detection of the afterglow in the optical emission, we can know the redshift and the location of this kind of events, and it becomes possible that associate the supernova of type 1A with the emission of long gamma ray bursts. So according of the property, we can distinguish different progenitors for the two types of GRB. For the short gamma ray bursts is well known, and with the detection of the gravitational waves, that this kind of event comes from the fusion of the merger of neutron stars. And on the other side, for the long gamma ray bursts, since they are associated with supernova emission, they are associated with the collapse of the massive star. And the more popular model for explaining the progenitor of these events is the collapsal model, where a unique star collapse, a massive star collapse, and then emit the high energy emission. I'm going to talk about other kind of progenitor for this long gamma ray bursts, and that is based on the a binary system for different reasons. First, there is a connection between the supernova of type 1c with gamma ray bursts, and the supernova that we have observed connected with these events shows similar properties independent of the gamma ray burst. Gamma ray burst shows a spectrum of different properties, but the supernova is more or less similar in all of these kind of events. Also, since we see a supernova, these events are related with massive star explosion, and we know that more massive stars belong to binaries. Also, the more probable explanation to say what this supernova of time YC is because the star that is collapsing has lost the hydron and helium layers, so the binary iteration with a companion since in a binary. And we also know that through the mesa evolution and different kind of evolution, the formation of a black hole directly from the collapse of a massive star is above the zero edge main sequence star. It should have more mass than 25 solar masses, but in these cases, the star collapse without producing a supernova. That is a constraint for the collapsal model. So we propose a different progenitor based in a binary system. In this case, we will have a system formed by a carbon-oxygen star. That is a star that has lost the hydrogen and helium layer from the interaction with its companion that will be a neutron star. This body star, when the carbon-oxygen star reach condition to collapse and explode in a supernova, the material that is expelled in the supernova will be gravitationally attracted by the neutron star, and different kinds of phase the system could have dependent of the initial binary properties of the binary system. So the material expelled in the supernova will be gravitationally attracted by the neutron star companion, and will be the star will accrete mass in a high accretion rate. And if the system is not compact, if the binary period is short, the neutron star could reach the critical mass and collapse in a black hole. We are going to call this system binary driving hypernova of type 1. This will produce, with the collapse of the black hole, energetic emission. And the most probable scenario is that the system remains bounded and will form a binary system of a black hole and a neutron star. And if the initial binary system of the carbon-oxygen star and the neutron star is not so short, or the star are not so close, the neutron star will still gain mass, but not enough to collapse. They will produce also a high energy event, but with less energy than the first one. And we will have the binary driving hypernova of type 2. In this case, the system could remain bounded and it will form a neutron star binary system, or it could also happen that it will form two runaway stars. And in another case, the binary driving hypernova of type 3, the system, after the explosion of the carbon-oxygen core will disrupt because the accretion rate on the neutron star will be not so high, and we have two unbounded neutron stars. In the case of the system remain bounded, we will have a binary of black hole or a neutron star or a binary of two neutron stars that eventually will merge and producing a short gamma ray bars, connecting them, connecting the short gamma ray bars with the long gamma ray bars in this kind of scenario. What we have done is to model how the expansion of this initial expansion, collapse of the carbon oxygen core, the emission of the supernova, and the expansion of the material will be moved in the binary system, will be attracted by the new neutron star, and how this star will acclimate and reach the collapse condition. We have modeled this system, the expansion of the supernova under the gravitational field of both neutron stars, the remnant of the carbon oxygen core that will be a new neutron star, and the neutron star companion. We have modeled different kind of system exploring all the parameter space that will be formed by the progenitor of the carbon oxygen core, the energy of the supernova explosion, the initial mass of the neutron star companion, and the orbital period of the initial orbital period of the binary system. We have modeled this with a SPS code, and here I show you the canonical simulation that consists of a carbon oxygen core with progenitor come from a star that has 25 solar masses at the 0s main sequence. This means that when it starts the main sequence evolution, at the moment of the explosion, the energy of the supernova is around 10 to 51 Earth. This carbon oxygen core, when explode, is ejecting around 5 solar masses, and the remnant of the carbon oxygen core will be a new neutron star of around 1.85 masses. The binary system has a neutron star companion of 2 solar masses, and the initial orbital period of this system in this particular simulation is around 5 minutes. So the orbital separation is around 10 to 10 centimeters. This simulation were done with 1 million particles, SPS particle, and we have snapshots of the density in the equatorial contours of the density, of the mass density in the equatorial plane of the binary system. At the center, we have the neutron star companion, and we see here the position of the new neutron star that is the remnant of the carbon oxygen. This snapshot corresponds to different times. At the beginning, we see that the material is expanding in the binary system and initially form like a kind of tail around the neutron star companion. This tail starts to circularize around the neutron star, forming an accretion disk. And then, after some time, the material that is gravitational attracted to the neutron star start also to be attracted to the new neutron star. So at the end, we see like a two accretion disks around both stars, the new neutron star companion and the neutron star, the new neutron star and the neutron star companion. Also, these both neutron stars are modeled like a point mass that can accrete particle if they approach enough to the neutron star accretion radius. And we see the accretion rate here, or the evolution of the accretion rate on the neutron star companion over time. We see that initially it starts to increase as the material starts to approach to the neutron star companion, peak at some point and then decrease all the time along the time. we see that the accretion rate or the peak of the accretion rate is around 10 to minus 3 solar masses per second. So it's a high accretion rate that happened but in a short time. And also, we have the evolution of the accretion rate on the new neutron star companion, that is the remnant of the carbon oxygen star. And we see that initially it peaks at the initial of the evolution, in the early time of the evolution, and this corresponds to the material that has not have enough kinetic energy to escape to the gravitational field of the compact remnant. This is what we know as the fallback accretion rate. And then this accretion starts to decrease, and we see here like a bump in the accretion rate evolution corresponding to the time when it starts to accrete the material gravitational in the disk on the neutron star companion. So we can calculate both accretion rate, both are high, so we can have the scenario where also the new neutron star could collapse to a black hole. Here we see a three-dimensional vision of the evolution of the material around the binary system, the disk around the neutron star, and some material point to the center of the compact remnant. We see that this expansion is asymmetrical, so we will also not have an spherical expansion of the material expelled in the supernova, but also we have some asymmetry that we can constrain with observation with the data from GRBs. Well, as I told you, we did a parameter study of the parameter space in this simulation. And for example, here we see how the accretion rate on both remnant change with the variation of these parameters. For example, if we change the energy of the supernova explosion, with this eta parameter, it means that in this case we have less energy in the explosion of the material expelled in the supernova. We see that the accretion rate on the neutron star is peaking more or less the same magnitude, but is sustained in a longer time period. So if we decrease it a little bit, we see here the peak. In the green line, we see like a more extended period where the accretion rate is high, and in the less case, energy is also more sustained. So they start with accrete more mass, but we cannot decrease it more because otherwise all the material will do fall back to the new neutron star remnant. And in the case of the new neutron star, we see that the fallback accretion is more or less the same, independent of the energy of the supernova, of the material ejected in the supernova, but we see that the later point on the neutron stars in the neutron star companion retain more mass in their disk. The peak or the later peak in the accretion rate of the new neutron star companion will be peaking at more high accretion rate that in the case of more energetic supernova. And of course, in this case, the neutron star also will accrete more mass. And we have also here changed the binary period of the orbital system. The accretion rate with the binary period decrease as the period increases, and we see that is more or less in a self-similar shape. We have here the more energetic explosion, and here the less energetic explosion with different binary period. And well, how the neutron star could accrete all this kind of this high huge mass is because, well, around the neutron star start to form an atmosphere that is enough high and, well, is enough hot and is high density that the emission of the reaction that emit neutrinos start to become efficient, and the neutrinos take off the system all the gravitational energy, and making possible that the neutron star could accrete this kind of high accretion rate. The emission of neutrino more or less is in the megaelectron volts channel. So in this case, we have the accretion rate from the numerical simulation. This will correspond to the accretion rate on the baryonic mass. And now we want to see or to study how the gravitational mass and the angular momentum of the neutron star will evolve, and if effectively it reaches condition to collapse to a black hole. So we model the baryonic mass of the neutron star, taking directly from the simulation, and the evolution of the angular momentum. We will assume that the star will accrete the mass from the formation of the disk. So the angular momentum that we will accrete by the neutron star will be the angular momentum of the last stable orbit of the disk, and with a parameter that model the efficiency of this accretion. And we also consider the magnetic torque or the dipole emission of the neutron star, but usually is turned off because the accretion rate is so high that the Alben radius we always stay inside the star. So in this case, to model the evolution, we will assume that the neutron star go through a state of equilibrium evolution. So at each time, we compute the mass and the angular momentum of this star, and recover the rotating configuration that corresponds with this mass angular momentum. For this, we need to assume an equation state for the neutron star. So we have assumed some of them, one with hadron matter and other with hyperon matters. And we here see the evolution in the mass and density plane of the neutron star. In blue is the evolution of the neutron star companion. And in black is in blue is the evolution of the new neutron star, and in black is the evolution of the new neutron star companion. Here is the same simulation of the canonical simulation I showed you before, but now we see that the fate of the neutron star depends on the initial angular momentum it has when the accretion, when the supernova, the system goes to supernova and the star start to accrete matter. So in the case where the star is more or less not rotating or has a low angular momentum, we see that in those cases, the more probable fate of the neutron star is that they reach the secular instability limit. This will happen in short time, more or less in 1,000 seconds. Both stars could reach the secular instability limit, and but in this case, it's expected that the star collapsed into a black hole in one dynamical time. Also, if they have a high accretion rate, both stars could reach the Mach-Scherer limit. In this case, it's not so well known what will could happen. The star could lose mass in order to remain stable and not collapse, or it could go through the secular instability limit and collapse to a black hole. Well, we are not sure what will happen once the star reaches the limit, but in this case, the collapse time could be shorter, more or less for the time of 100 seconds. If there is another case, but we see that in the case of high accretion rate, the star effectively could reach the limit to form a black hole But will be other case where the star gain enough mass, it will not collapse because it will be stable of the rotation. But when the accretion cease, the star will start to lose angular momentum through the dipole radiation, for example, and it will make it to evolve through less angular momentum configuration. So it will increase its central density, and at some point, again, it will reach the secular instability limit, but after some time of the initial supernova explosion, this time is for the order of days, and in the case the system will have remain in a binary system, the collapse of the star will happen first than the merger of the binary system is remaining. So we could have a late collapse also of the initial binary stars. So we can have different kind of phase. Fate on the binary system, the neutron star companion could collapse to a black hole, but also the neutron star also could collapse to a black hole, or we could have late collapse. In the case, the star will range enough mass to be sustained just by the rotational energy. We can also have other kind of phase. In the case, for example, the formation of a strange quark star. In the case of the two-family scenario, where we could have neutron star for barn hadron matter and comparator for bar disconfined quark stars. In this case of the two-family scenario, we will have a critical density at which the star, the matter inside that form the star will disconfine and will form a neutron star or a comparator formed by quark stars. And this critical energy is reached when the strangest fraction of the particle inside the matter reach the 0.2 or 0.3 inside the star. This kind of thing or this kind of event could happen in the binary driven scenario under the assumption of the two-family model. And we see that due to the accretion rate, depending on the progenitor that form the carbon-oxygen core, we will have that, for example, in this case, the carbon-oxygen core could reach this confined condition for the high progenitor of the carbon-oxygen core and for a low energy explosion. So the accretion rate onto the new neutron star will be high, and it would eventually reach density where the disconfined condition could be met. Also, in the case of the new neutron star companion, for these two progenitor, the one with 25 solar masses and 30 solar masses, they will also reach the condition for the confining, but up to an initial angular moment. So if the star is rotating faster, it will reach first the mass shedding limit before reaching the condition to disconfine. The disconfine obviously will produce a considerable amount of energy that eventually will be observed. So gamma ray bars could be approached or a way to prove this kind of constraints. And well, with this scenario, we have, with the binary driven hypernova model, we have different phenomena that we traduce to what we observe from the data of the DRB. For example, for the three kinds of binary, the binary driven hypernova of type 1, where the neutron star collapse to a black hole, the binary driven of type 2, where we have a binary system, but it no produce a collapse to a black hole, and the binary driven of type T that are the less energetic system. In all three cases, we have the supernova emission. We eventually could see an early observation of this supernova, and we have the hypercritical accretion or the four-bar accretion into the compact remnant of the carbon-oxygen star, that is the new neutron star. Also, in the first two kind of scenario, the neutron star companion also will have an hypercritical accretion into it. And just in the first case, we have the formation of the black hole and the emission of high energy photon and high energy phenomena. And at the end, all three objects, again, we have the emission of the afterglow that is produced at the cyclotron emission of the supernova Jetta with the energy into the new neutron star, and the pulsar-like emission of the new neutron star. So, for example, we have GRB that have two kinds of peaks. So these two kinds of peaks could be related to the earlier accretion of the neutron star. If we compare the accretion rate of the new neutron star and the accretion rate of the neutron star companion, we have cases where we have like two peak emission that will be traduced in an early emission of the gamma ray burst events. And also in the afterglow, if we can fit model this afterglow and fit with the the properties of the new neutron star remnant and connect them with the property of the initial binary system, we see that the fraction between or the binary period that separate the collapse of the neutron star with a no collapse is around 10.5. So we have with just the double of the binary period of the initial binary system, we can have the case where the neutron star do not collapse. And we can also study the final fate of the binary system. It is remain a binary, or it remain or is unbound after the supernova explosion. And this again will depend on the initial parameter of the binary system. So for the case where we have less energy and not so high binary system, we have a maximum orbital period at which the two neutron star will remain in a binary system. And it also will depend on the initial mass of the neutron star companion. So less than this period, we will have the both star after the supernova explosion will remain a binary system, and over this period, it will produce two unbound stars. And this, well, the system that will remain bounded eventually will reach condition to merge and produce a short gamma ray burst. So in the first place, we have that the rate of occurrence of long gamma ray bursts is greater than short gamma ray bursts, but just a fraction of these binaries will remain bounded. And what we have with in the binary driven hypernova scenario is like just the 2 or 8% of this long gamma ray burst will eventually produce a short gamma ray burst. So here is the summary of the model. Initially, we have a carbon neutron star, carbon oxygen core with a neutron star binary. In this case, the core collapse, expand, and depending on the initial binary period of the system, if the binary period is short, we produce a binary driven hypernova type 1 with emission energy of 10 to 52 Earths. the system will remain bounded and produce a neutron star black hole binary that eventually will merge and producing a short GRB. In the case where the initial binary period is not so high, we can have two cases, binary driving of type 2. In this case, the system could be bounded or could be unbounded. In the case that is bounded, it will produce a 2 neutron star binary system that again eventually will merge and produce a short GRB. In the case that is unbounded, we will have to run away neutron stars. And if the accretion rate over the star is not so high, it will produce a binary driving supernova system of type 3. In this case, the emission energy is less than 10 to 50 Earth, and the more probable scenario is that the system becomes unbounded. So we have done the 3D numerical simulation with a SPH code, and we can explore the different kind of interpretation of long GRB in this model. We see that the rotational energy by the neutron star and the neutron star companion could traduce in an early emission of the prone emission of the GRB, so we can have the potential detection of precursor of this kind of events, and the binary driving can produce different type of compact binary system like black hole neutron star, or 2 neutron stars. This system eventually will merge through the emission of gravitational wave, and this could be offered also an insight into the equation state of the neutron star companion. So, thank you.
For a very nice talk. I think we have a few minutes for some questions, if there are any.
Thank you for interesting presentation. What is the source of neutrino emission in your simulation? Is it neutronization of accreting matter or something else?
It is an annihilation of electron positron. I mean, here the atmosphere around the neutron star will increase the temperature and the density until it reach a condition where the reaction of annihilation of electron positron become efficient and produce neutrinos that will take off the gravitational energy produced by the accretion of high mass into the star.
Yes, thank you.
Yeah, my question is regarding the first part when you are talking about collapser and long duration gamma ray burst. I understand, if I understand correctly, you do not consider magnetic field. I am wondering, had you introduced magnetic field, which presumably can help producing jet, and GRB could be, one of the possibilities could be jet, whether your result will be affected or not. And second related question is, I could not quite follow what is the nuclear reaction network you consider, all related to the collapser model, because not merger, which is different case. Yeah.
Okay. Well, regarding the first question, we don't consider the magnetic field in this phase of the system where it's produced the accretion into both neutron star, because the accretion rate is so high that the magnetic field will be buried inside both compact objects. What happened after the collapse of the neutron star is another another thing that is the collapse into a black hole. That will be a different kind of simulation. But during the accretion, and at least until the accretion is maintained more or less in the range of 10 to minus 8, 10 to minus 7 solar mass per second, the magnetic field will be buried inside the neutron star. So that's why we didn't consider it. And for the collapse of the carbon oxygen core, we didn't also model the collapse itself, but we start modeling with the short wave reach the surface of the star. So we just take the model from the Kepler simulation, but I'm not sure what kind of reaction they use to model this kind of collapse objects.
Okay.
Thank you, Laura, for this very important and extensive new development of the model. And we are also working here very much because in the BDHN that you have considered up to now, there will be a final event which is represented by the nickel decay, which is observed in all our model up to now. But we have now a new GRB, very, very powerful, which is GRB 220101, in which we have no evidence of the iron emission line of the nickel. And on the contrary, we have very clear evidence of the existence of a pulsar. And we are working on that. We expect, and we invite you strongly, no matter the difficulty, to come to work with us in the development of this very important new model, and at the same time to make a comprehensive comparison and contrast between the two models. We need your presence. Okay? We'll contact you later on today. Thanks. And congratulations for the beautiful images.
Thank you.
Okay, so let's thank the speaker again. And we continue with the next speaker, who is Giorgio Sonino. He will speak about extreme Kerr-Newman black holes, differential geometry, symmetry, and the golden ratio.
Okay. Okay. Thank you so much for the invitation. The subject of my talk is to continue to finalize the work initiated by SMAR. Indeed, SMAR had a very brilliant idea. He wanted to discover new physics information, not by studying the symmetry in the space-time by using Killing vectors, but by studying the symmetry of the geometry of the event horizon. SMART make a series of results, but then he interrupted the study and the talk. Our task is to continue to finalize his work. we start to analyze the extreme black holes in Kerr-Newman geometry, and then we study the geometry this black hole by using the tools of symmetry and differential geometry. Then they extract energy that we can get from these black holes, and then to find, if possible, some new information from this discovery, from these results. Okay, here we start with the metric, of course, of the we start with the metric of Boyer-Lindquist that we know, everybody knows, and then here in this canvas, I resume very briefly. I don't spend time to explain this because we know everything. Very briefly, the main results from this metric, in particular, I focus the attention to the surface of the event horizon, which is an intrinsic property of the black holes. If we integrate with this metric or inverse, we obtain the well-known Cristodolo-Ruffini formula here on the right, and the black hole exists if this inequality is satisfied. Okay, when this inequality will be saturated, we have the extreme black holes. It is we shall rewrite this equation in the formulas of proposed by Smart, where he proposed two parameters: the scale parameters, which is twice the irreducible mass, and the distortion parameters, which is the angular momentum per unit mass over the scale parameters. What is important to note is that the surface depends only on the intrinsic parameter, in contrast with the radius, outer radius, which depends on both intrinsic parameter and parameters beta. We shall see that parameter beta is an extrinsic parameter. What are the main results obtained by Smart? We shall continue to work in this direction. Smart, as said, introduced these two parameters. The first parameter, eta, is intrinsic, and this, roughly speaking, is due to the second law of black hole. But the second parameter, beta, is not intrinsic, because beta is A over eta. A scales as m squared, m scales the reducible mass, so beta doesn't scale with the reducible mass. This is the first observation. The first results, important results obtained by Smart, is that the black holes are divided in two big classes. When the distortion parameter is between 0 and 0.5, the black holes can be isometrically embedded in the Euclidean space. When it is between 0.5 and the inverse of square root of 2, and we shall see why this is the extreme value, can be embedded only partially in a Euclidean space, can be embedded in a pseudo Euclidean space, the matrix +1, +1, -1, or in Minkowski space, but not in Euclidean space. The second important result obtained by Smart is he identified a class of extreme black holes which is very meaningful. For beta equals 0.5, he found this family of black holes, and we note that all fundamental physical quantities are linked to the irreducible mass by irrational numbers. Number different from each from the other. The second important discovery is that all members of this family has a flat Gaussian curvature at the pole. So the umbilic points at the umbilic points at the pole are automatic. Why smart studies focus his attention on the geometry and the extreme black holes is quite evident. Geometry is an intrinsic part, the surface area is an intrinsic parameter, is linked to the entropy proposed by Wheeler and Wittgenstein, and then at the extreme black holes, the two radius coincides, the temperature, Hawking temperatures goes to zero, the surface gravity goes to zero, and the geometrical quantity becomes singular at limited values. Okay, now let's start with our contribution. What is motivating our work? Professor Remolfini asked me to give an answer to 4 questions. The first question is to see if the family discovered by SMART is unique, or we have other family of extreme black holes. The second is to study this family by using the tools of differential geometry and crystal diagram. Third question is to get to determine how much energy we can extract from these black holes. And finally, the final question is which kind of physical information can we obtain by the results obtained by our calculations. Okay, let's start with the first question. If we consider the extreme black holes so should satisfy the mass energy formula, Cristoforo-Ruffini, and the inequality should be saturated. We can rearrange these two equations in the form of 4 equations. 4 equations where geometrically can be represented by 4 different right triangles. Well, any other possibilities is a combination of these 4 triangles. So these right triangles represent the whole family of extreme black holes in Kerr-Newman metric. Now we are looking for the resonance. We have 2 possibilities. This triangle rotating the vertex B goes in B1. If it happens that B1 coincides with E, we have 1 resonance. Another possibility is this triangle rotating D goes in D prime. And if it happens that this catetus coincides with the height of this triangle, we have another resonance. All other possibilities either are trivial or are a combination of this one. Then we have only 2 possible resonances. For the first case, B1 coincides with D, we obtain this family of black holes, which is exactly the family found by SMART. But the second case is another family of black holes. And this family of black holes is different from the first one because now the fundamental parameter depends only one irrational number. By chance is the golden ratio, but this is not important. What is really important is that we have one irrational number for all physical quantities. Now, Professor Ruffini asked me, okay, study this by using the Cristoforo diagram and think about symmetries, etc. First of all, we have to rescale the variable in this way in order that the Cristoforo diagram can be framed into a square. Okay, if now we have this line represents the extreme black holes. As you can see, the diagonals of this square divide the Christodoulou diagram in 4 pieces, equal 4 pieces. The intersection of this diagonal with the boundaries of the Christodoulou diagram, A, B, B, D, and C, are exactly the family of the black holes we have discovered governed by only one irrational parameters. A second thing is the symmetry. If I have a black holes, if by symmetry with respect to the origin of the axis, I mean, the original axis is the Schwarzschild black holes, we have another black holes which is extremal. Another symmetry is with a reflection between the axis, y-axis, and y is the angular momentum, this to this. Another symmetry is the trivial, the reflection between around this axis, the charge axis. But now we have other 2 symmetries discovered. If we make a reflection between around the diagonal, we have another black hole, and from this to another diagonal, we have another black hole. These 2 symmetries belong to the new family we have just determined a few minutes ago. In this picture, you have the Christodoulou-Ruffini formula, and which should be inside the pseudo cylinder. The intersection gives us the extreme black holes, and the yellow surface is the Kerr-Newman black hole, not extremes. Okay. Here I represent the family of black holes discovered by SMAR, and this is the black holes discovered by us, extreme black holes, resonant black holes in the Christodoulou diagram. Professor Ruffini asked me also to reproduce the black holes by varying the mass of the black holes, very, very small, 10 times the Planck mass up to a big mass, a 10 to 8 solar mass. Okay. But let's go now to the section, to the second question. To study the geometry, we follow the strategy indicated by SMART. We embed isometrically the surface into Euclidean space. Okay, and then we determined the Gaussian curvature, the median curvature, and the very special points referred to as umbilic points, which are very important because they tell us the degree of symmetrical symmetry possessed by black holes. Okay, for this we have to rewrite the mass energy formula in the formalism of SMAR by using the 2 parameters, and then this equation is referred to as the SMAR energy formula, but in reality as a Christodoulou-Ruffini written in the new parameters. Here you see that the charge can be from 0 to this upper limit, which is real only if beta is between 0 and 1 over square root of 2. Okay? So SMART discovered that if beta is between 0 and 0.5, the black holes can be fully embedded isometrically in a tree. Otherwise, only partially. This is the reason why we have dotted line. The spherical picture corresponds to beta equal to 0 is the Schwarzschild black hole. Okay, now we have to study the geometry. For this, we use the methods given by differential geometry. We have a surface revolution. We have to write this in the parametric forms, and this is the metric on the surface. Then we have to combine this with the metric of Euler-Lindquist to find the expression for F and G. After calculations, we see that the metric takes this form, f and g takes this form, is linked by a function h, where the expression is given by this, where beta is the deformation parameter, and mu is cosinus theta. Theta is the angle with respect to the vertical axis of the black holes, is this angle. This vertical axis is this angle. For theta equal to 0 and or pi, we are at the pole. So to continue, we have to calculate, according to the tools of the differential geometry, the fundamental forms. We have three fundamental forms to calculate. The first fundamental forms is the metric on the surface, is the point that goes from M to M prime. The placement over the surface is the first fundamental forms. The second fundamental forms is the distance between the point M1 projector on the tangent, and the third fundamental form give us the angle between the two perpendicular vector on the surface from M prime. This transported parallel on the surface according to the affine connection. This once we have calculated the coefficients of the different fundamental forms, we can calculate the Gaussian curvature and the mean curvature. Okay, I don't show you the details of calculation, but just the results. And the results show that given the metric Boyer-Lindquist, we have these two fundamental forms, and this is the Gaussian curvature of the Kerr-Newman black holes. We can see here very fast that if beta equals 0.5, kg goes to 0. Then it's flat at the pole. Then at the pole, mu is equals plus or minus 1, and if beta is equals 1/2, we have 0. For beta between 0 and 0.5, the Gaussian curvature is positive, fully embedded geometrically. If beta is between the 0.5 and 1 over square root of 2, Gaussian curvature is negative. So I can embed it in Minkowski space or in a pseudo-Euclidean space, but not in Euclidean space. Okay. Here I reproduce the family of black holes discovered by SMAR in the new variables, and here is our black holes, new black holes in the new variables. Notice that in our case, beta is 0.43, less than 0.5. Our new family can be isometrically embedded in Euclidean space. Now we have another question. When we have a charge rotating black holes, we lose the spherical symmetry due to the presence of the charge and the angular momentum. We lose, but the natural question is, can I find the highest, the black hole extreme having the highest degree of spherical symmetry? This is the question. In case of SMAR, the answer is no, not possible. But in our case, yes. For a given answer to this question, we know differential geometry says calculate the umbilic points and see if the black hole is a solution of Einstein equation. Okay, then we calculate the umbilic points. For this, we have umbilic points. The first fundamental form should be proportional to the second fundamental form, and there are two matrices. If we make a calculation, we found these equations. And this equation shows that for beta between 0 and 0.5, our family is 0.4, and then can be embedded. We have only one possibility. The umbilic points are located at the pole. no other position. The middle point is the geometrical translation of maximal symmetry, spherical symmetry. Now the question is, okay, but can you calculate this black hole, particular black hole? Then we have found a new family. We see that there exists one black hole, only one black hole that satisfies the maximum spherical symmetry, but now we have to determine this black hole. For this, we evoke one of the quite recent theorems in differential geometry. This has been shown 15 years ago in a context very, very large in pseudo-Euclidean, etc. But for what we need, the theorem says that if the three fundamental forms satisfy the Pythagorean conditions, they are matrix, the point which satisfy these conditions are umbilic points. So if we make these calculations, details in the paper, we see that the only black holes belongs to the family we have discovered is this one. Again, the reducible mass depends on the same irrational numbers. The Gaussian curvature depends on this irrational number, the mean curvature too. So we have only one black holes up to the discrete symmetry Q in plus minus Q, L in plus minus L, which doesn't alter the geometry of the black hole. We have only one black hole where all fundamental parameters, including the reducible mass, depends by one irrational number. Here I show in the histology diagram the location of this particular black hole. Sorry, okay. In this diagram, here we have this particular black hole we have discovered, and this surface is the surface of all extreme black holes. The black lines are the family we have discovered. At this point are the particular black holes which satisfy which are having the highest degree of spherical symmetry. Is located here. What is this irrational number? This irrational number, by chance in nature, appears everywhere. Appears in the morphology, in chemistry. We have discovered in chemistry. I'm a theorist in thermodynamics. Appears in biology, but also in the environment. This is the desert of Atacama. As you can see, the desert is paved by pentagons. Each side is exactly the golden ratio. Why the golden ratio? Well, Parisi gave a beautiful answer, because when we have very complex boundary conditions, the best way to pave this surface is quasi-crystal, in particular pentagons, in particular the golden ratio. So we have shown that even in astrophysics, the golden ratio characterizes one particular class of black holes, a solution of the Einstein equation. Let's go to question 3. Professor Ruffini asked me, okay, now calculate how much energy you can extract from this. Make a complete picture for all class of possibilities. To calculate this, we have to evoke the second law of black hole thermodynamics, stating that we can extract energy by electromagnetic field, by angular momentum, but we cannot extract energy from irreducible mass. So, when we make a transformation, either the variation is 0 always positive, never negative. When it's zero, for the reason that I can explain but in another talk, we speak about a reversible transformation. Otherwise, it's irreversible transformation. Professor Ruffini asked me to make both calculations. For reversible transformation, very simple. Delta E is energy minus what I cannot take. And then you can see that if I use this inequality, the maximum extractable energy for Kerr-Newman black hole between 0 and 50%. Okay, but now we have to go further for if the black hole is extreme, but if it is extreme, I have to use these equations. After very simple equation, the black hole goes, I can extract between 29.28% to 50%. And if they are fully embedded in A3 after simple equation, if this inequality is satisfied, I can extract between 42.26 to 50%. If only partially embedded in A3 is the complementary part from 29 to 32. Here, I calculated how much energy I can extract in a reversible way by the family described by Smart. And this is how much energy can we extract with our new family of black holes, 44%, which is very, very high percentage. Here is this picture summarize everything. Here is a Kerr-Newman black hole. The energy I can extract. This for extreme black holes. This not embedded. For Schwarzschild, I can extract 0%. Reisner-Nordstrom from 0 is 50%, and so on. In this picture, I produce here the energy that can be extracted by a black hole is the yellow of a surface, which to be included inside a pseudo cylinder. Here, the energy that can be extracted by extreme black holes. Here for embedded, fully embedded, here partially embedded. Okay, let's go in case of irreversible transformation. For reversible transformation, delta M now is greater than 0. This quantity should be positive, so I have a maximum limit, and we have the final result, the energy that can be extracted in an irreversible way can go from 0 to an upper limit, which is established by the energy that I can extract in a reversible way. Now, if I use this reduced variable, I can introduce these new quantities, which represent the variation of the surface, and then now it is not 0, C, and then I can plot C, the delta surface of a surface, which is this surface yellow inside the pseudo cylinder. Here I plotted the Christodoulou diagram where I put the number C. The red arrows are the gradient, the gradient of the growth of the surface. As you can see, the gradient forms everywhere for a Kerr-Newman black hole an angle different from 0 with respect to the axis going from the origin to the black hole, except here, where is the maximum. Then we have another property. Our family, the black holes, is the family where the growth is maximized in a reversible way. Now, let's summarize and then go to the first final questions. The idea of SMART to study the surface, it determined a family of black holes. We discovered that there is another family of the black holes which are characterized by a unique irrational number. Inside this family, there is only one were possessing the highest degree of spherical symmetry. But now the question is, which kind of physical information can I obtain by this family of black holes? But the idea is the following, final question, is the following. We now consider not a Kerr-Newman metric geometry, but Kerr-Newman de Sitter geometry. Then we consider now the written dimensionless forms. In dimensionless form, we have this parameter, which is the ratio between the cosmological constant and the Albert constant. This is the metric. Now, if you put numbers, you find that experimentally this parameter is exactly this irrational number to 3/4. This is coincidence. It's quite natural now that if we inject our unique black hole having the highest symmetry, and we impose that this black hole is possesses marginal stability, we solve this Hessian, where S is the entropy, but not the thermodynamic of the statistical mechanics entropy. It's the entropy in the sense of Wheeler surface, is a geometric aspect. If we solve this equation, we have an equation between the omega and the irreducible mass, and the irrational number. Because if we inject our black holes in this equation, we have an algebraic equation giving omega in function of this irrational number. Calculations are in progress, but now we have the possibility to see if there is a coincidence between experimental data phi 3/4 and the solution of these algebraic equations, where we impose that this particular black hole possesses marginal stability. Thank you.
Thank you for the very nice talk. Are there any short questions or comments?
I have a question about the extremality. It is believed that an extremal Kerr solution will never occur in nature. You enter the near horizon extremal case, and that is a very difficult problem because you enter the quantum area. It turns out that the first block, that is the first two parts of your metric, with the n and 1/n, that is conformal, can be written as conformal anti-de Sitter 2.
Yeah.
And that is, then you enter the conformal field theory. So
yes.
That is a quantum issue.
This is an important issue, but I need to link local geometry with global geometry. The only possibilities I have is to say that the local geometry, Kerr-Newman geometry, is at the marginal stabilities. I don't know if they goes in the global geometry. I don't know that. But what I know is that I want to see what is the black holes that imposes the marginal stability in the Kerr-Newman geometry. And then we tell to me, pay attention, this stops to be a local geometry.
Yeah, but then you must make a distinction with the observer. That's the complementarity issue. Do you talk about the inside observer or the outside?
Yes. Yeah.
And the inside observer will completely different experience what he sees.
Yeah. Yeah.
So, to my opinion, the extremality must be larger than 10 to the power -6. Otherwise, he comes in the quantum black hole models.
Okay. I take
Okay.
note.
So I think we should continue. So let's thank the speaker again.
Well, this is very, very exceptional a way to present this in a written form. Excuse me? Yes. That is a possibility to develop a special session on master course, but we have to prepare. We have to prepare this. We need your collaboration because it's a field which is marvelous. And it can mean the underlying physics is not yet understood. But certainly the mathematics is. Therefore, we could find a transition to make this strategic. But we need the collaboration of as many people as possible. And we invite you to participate. And there is another point which is the limit, the Planck mass in the transition between quantum and general relativity. It's the most interesting subject here. It's the most interesting subject. And we have written a tentative paper, which this one we will publish right away. It's very urgent. Thank you so much, because I have to say that Giorgio has been so dedicated to this topic, and it has served to become notorious for this collaboration which we have had. We make all the possibility to make that a reality.
Okay, thank you. So let us continue with the last speaker of this session, who is Igor Kanachikov. Please.
Come è andata? Ti è piaciuto? Oh, questo non è mio. Mi stavo fregando questo.
Okay. Please, just a moment. Thank you. Okay, can I start to just stay there? Why is this like that? Needs time? Yes, I see. Can I move this one?
Okay, so we will talk about non-Keplerian galaxy rotation curves as a testing ground of precanonical quantum gravity. So it is known that galactic rotation curves are not Keplerian. Most frequently, it is mentioned that they're flat, and it was nicely described in one of the first talks of this conference by Lely. So at large distances from the galaxies, well beyond the visible disks, the rotation curves are becoming non-Keplerian. And the usual explanation of that is that one introduces unknown substance known as dark matter, which extends well beyond the visible disk and contains 5 times more mass than the visible or baryonic matter. So just to give you a precise idea of what are rotation curves of galaxies, so that here there is some collection of rotation curves and the typical errors of measurement. One of the alternatives to dark matter, which is known in the literature, which was just reviewed by Lely, is the hypothesis by Milgrom of 1983, where he proposed a modification of Newtonian dynamics such that by modifying the Newtonian law at very small accelerations below the scale of what is known as Milgrom acceleration A0 of the order of tens of nanometers per second squared, and surprisingly connected with the scale of the cosmological constant, which is one of the simplest versions of dark energy responsible for accelerated expansion. This allowed him to predict, and then it was tested, the so-called Tully-Fisher relation between the asymptotic speed of rotation of galaxies and the visible mass derived from the brightness. In this approach, the caveat is that the so-called interpolating function, mu, which interpolates between the Newtonian regime and the so-called deep Mond regime responsible for flat rotation curves, that this function is taken from experiment and has no theoretical justification. One of the results of this of the work which is behind this talk is that we are able to derive Mond as a consequence of quantum gravity, specifically the approach of quantum gravity, which I have been developing for some time, called precanonical quantum gravity. This approach is based on a generalization of a Hamiltonian formalism where no space-time decomposition is required. This generalization was found by mathematicians already in the end of 19th century, namely Volterra, and then developed by a pupil of Poincaré, Théophile de Donder. The Hamilton-Jacobi part of it was also developed by Weil. That's why the theory is called the Donder-Weil. I will briefly outline what are the basic theses of this talk, because I definitely will not have enough time, so at least I would like to mention most of them. So the theory was known since the beginning of the century. The paper by Weil was 1935. De Donder was doing his thesis in 1913 and publishing books in the 30s. But quantization was not possible because nobody knew what are proper Poisson brackets in this generalization of the Hamiltonian formalism. Those were found in my work in the 90s, and it leads to the definition of Poisson brackets on differential forms representing dynamical variables instead of the functionals used in the standard canonical formalism, which requires 3+1 decomposition. and limits the consideration to the globally hyperbolic spaces. To quantize those brackets, we found a representation of operators in terms of Clifford algebra valued operators. Clifford algebra is the most natural way of quantizing differential forms. And during this process, we found that the necessary ingredient is quantization of the elementary volume represented by 3 basic differential form. In terms of the Clifford algebra element gamma 0 divided by kappa, so we have to introduce the ultraviolet constant parameter kappa of dimension of inverse spatial volume. Then we also justified such a generalization of the Schrödinger equation, which in the case of quantum gravity leads to the quantized version of the Dirac operator, where, as we will see later, field binds are represented by derivatives with respect to the spin connection. And the right-hand side constitutes what is the analog of the Hamiltonian function within the de Donder-Weil Hamiltonian formalism, namely the operator of the de Donder-Weil Hamiltonian function. We studied the connection of this formalism with standard quantum field theory and found that in the limit, when the equal point delta function, spatial delta function, goes to the where kappa goes to the single limit of the delta function at equal points, we are able to reproduce the quantum field theory, which is known to have problems just because they require regularization exactly of this in this situation where equal points are ill-defined and correspondingly the distribution theory has to be generalized, or one has to deal with the renormalization and all that stuff. In the Schrödinger functional Schrödinger representation, what one has to define what is the second order variational derivative at equal points. Second element of this consideration will be that the parameter of kappa actually disappears from the results of free field theory. But if one considers the spectrum of the Donder-Weil Hamiltonian of quantum Young-Mills theory, one can make a spectral estimate of this and show that because of that, kappa is related to what is known in quantum field theory as the mass gap of quantum Young-Mills theory. This is quantity in the range of GeV plus minus half an order of magnitude. And this allows us to identify the parameter of precanonical quantization kappa with the hadronic scale. Exactly this feature of the theory is what drives the quantum gravity effects from the usually expected Planck scale to the scale of phenomena which can be seen in the sky. Namely, the estimation of quantum of the cosmological constant which comes from this approach actually leads to the realistic values, realistic small values. This is the theoretical prediction, and one can check that if kappa of dimension length -3 is of hadronic scale, then this lambda reproduces the observable value of the cosmological constant. Problem solved. Surprisingly, this is very close to what Zeldovich has proposed in 1967 when he tried to estimate the cosmological constant and has arrived to this formula. This is the copy of his first page of his paper. Then we also found that if we consider test particle moving on the background of the simplest solution of the quantum gravity equations, which are responsible for quantum fluctuations around Minkowski spacetime, or more precisely, in the non-relativistic limit, in the background of quantum fluctuating Galileo spacetime, we're able to understand where from comes mont, where from comes the scale of mont A naught, why it is related to the square root of the cosmological constant, and how the equations, how the dynamics gets modified at very large distances from the galactic centers and at very small accelerations below the scale of Milgrom's acceleration, so that we are able to obtain different modifications of dynamics, one of which is exactly the Milgromian mont. So now I will proceed with the theoretical foundations. First, what is the Donder-Weil theory? If we have a Lagrangian function, which is usually defined as a function on the, depending on the fields, first derivatives of fields at space-time coordinates, we can define variables analogous to the canonical momenta, which I call polymomenta. We can define analog of the Hamiltonian function on the space of polymomenta field variables, which I call the Donder-Weil Hamiltonian function. And then equations of motion are written in such a beautiful Hamiltonian-like form without space-time decomposition. This Hamiltonian form of field equations has also its own analog of the Hamilton-Jacobi formulation, which was found by different people, including Weil in 1935. And this is how the Hamilton-Jacobi theory for fields looks like. As mu's are iconal functions on the space of field variables and space-time variables, and existence of such partial differential generalization of the Hamilton-Jacobi theory to fields raises the idea what is the formulation of quantum field theory, which in the classical limit would be able to reproduce this partial differential equation. My approach, I believe, answers the question. What allows us to define the Poisson brackets corresponding? Gentlemen, you're actually too loud and you are disturbing me. Excuse me, Professor Ruffini. You are a little bit too loud, please. I have my 20 minutes. No problem. So to define Poisson brackets, we need, the procedure is to start from the analog of the symplectic form, from a generalization of the symplectic form, which I call polysymplectic form of degree n plus 1 in n space-time dimensions. This form can be used to map multivector fields to differential forms which represent, sorry for mathematics here, which represent dynamical variables. One can show that space of this form, this is very limited class of forms, very limited class of dynamical variables on which we're able to define the brackets and this map, which is closed with respect to this product. I call it co-exterior product, but it was known already to Grassmann, as it turned out. Then we can define Poisson brackets, find that this structure leads to the algebraic structure known as the Gersten-Haber algebra, which will play the role of a generalization of Poisson algebra in field theory, which underlines the procedure of quantization. Why we use the term pre-canonical? We do it because the following relation between this formula is the Donder-Weil's and the standard one, namely if we take the polysymplectic form restricted to the space of initial data, integrate over the space of initial data, denoted capital sigma, we obtain the standard symplectic form on infinite dimensional phase space, the one which underlines the canonical Hamiltonian formalism and canonical quantization. Moreover, if we make similar procedures, start from the Donder-Weil iconal functions, restrict them to the Cauchy surface and integrate over it, then the corresponding functional bold S will satisfy the canonical variational derivative Hamilton-Jacobi equation. In this way, pre-canonical formulation is related to the canonical one after 3+1 decomposition. Now, using this definition of brackets, which we can calculate brackets which would generalize the canonical bracket between P and Q and the canonical formalism. Those are brackets between forms of degree 0 and n-1 in n space-time dimensions. They have very simple form, and one can show that the representation, so far the only one I found, there is no proof, mathematical proof of uniquely. Someone may challenge me maybe. That the corresponding operators can be represented by operators taking value in the Clifford algebra of space-time. If the volume form of degree n-1 is represented by 1 over kappa multiplied by the basic element of the Clifford algebra, and polymomenta are represented by partial differential operators with respect to the field dimensions. Then, using that, we can quantize simple examples, and most importantly is that the equations of motion, those which were written, the Donder-Weil Hamiltonian field equations, can be written in terms of the bracket, so that the usual Heisenberg equation of motion, where the time derivative of an observable is controlled by the Poisson bracket with the Hamiltonian function, is generalized here in the following way, where G bullet is the analog of exterior derivative, where the exterior product is replaced by the co-exterior product. And this allows us, with a little bit of guesswork and self-consistency checks, find out what is the analog of the Schrödinger equation in this case. This one is written in the flat space-time context for the scalar field, where Dirac operator is just the Dirac operator. The parameter kappa, as you see, appears both in the representations of operators and in the analog of the Schrödinger equation for purely dimensional reasons. So conclusion is that if we proceed along the lines of the Donder-Weil Hamiltonian formalism, its quantization leads to a hypercomplex generalization of quantum formalism rather than the infinite dimensional one, which is the standard wisdom in the quantum field theory based on canonical quantization. Then, of course,
could you please come to the conclusion?
Already to the conclusion.
Yes.
I started at 39 and I spent 8 minutes.
You started at 26 and you spent 21 minutes.
Oh, really? I need another 10 minutes. Thank you very much. Thank you. Okay, in order to proceed, I have to introduce clarity, namely to show how the precanonical quantization can be related to the canonical one. So it means that we have to ask a question, how our Dirac-like equation with the Donder-Weil Hamiltonian is related to, for example, with the functional Schrödinger representation, which is written down here. And the relation is that the Schrödinger functional can be represented as the operation known as Volterra product integral, the product version or analog of the integral operation in this way. So it can be explained in more pictorial way, but I will not do it. Important is that this expression makes sense on the following map, which, as you may notice, is the reverse of quantization map from differential forms to Clifford algebra. The conclusion is that quantum field theory, one of the conclusions for you, is that quantum field theory is the standard quantum field theory can be considered as a singular limit of the theory which is produced by precanonical quantization, and the regularization is already built in the formulation because of the way the quantization is done. So that standard quantum field theory, the precanonical quantization is in using the Wheeler's language is already regularized quantum field theory with regularization without regularization. Okay. Now we're trying to apply this to general relativity. We start from the Filbine formulation, Palatini for a reason, where spin connection and Filbine variables are independent field variables. We quantize it, we get constraints. I found the generalization of the Donder-Weil theory to the case when there are constraints, understood as the singularities of the corresponding generalization of Lysander transformation where no space-time decomposition is required. So this procedure was done more than 10 years ago, published also in this volume of Zeldovich Proceedings of 2014. We will omit it. And what we get is first, we obtain the representation of the metric operator, and we obtain the explicit form of the Schrödinger equation for the wave function, depending on spin connection components and space-time variables, psi of omega spin connection coefficients and space-time variables, where the Donder-Weil Hamiltonian, I'm writing it here for Young-Mills coupled to gravity, just because I'm using Young-Mills in the middle of my arguments. This is the form for the pure gravity. And there was a representation of the metric operator, which we will use in what follows. Second order with respect to the derivatives, with respect to the spin connection. Important is this coefficient. Also, because of the ordering problem of this operator, this cosmological constant can only appear because of the reordering of operator. And this part is ordering independent, and the only way wherefrom we can obtain this cosmological constant is this spin connection term. This spin connection term. Then one can estimate the order of this constant lambda. That's another interesting feature of the approach. It is totally scale invariant. It knows nothing about Planck scale. And all physical constants are actually absorbed in this dimensionless coefficient lambda, which has following expressions through the physical constant, the cosmological constant, the parameter kappa of precanonical quantization, and GH, which is the Planck scale. If we choose the Weil ordering, we can calculate that the value of this dimensionless small lambda is 3. The scalar product, they are not quantum field theories here as I see, so I will not go to that. This is just to show them that I'm not doing arbitrary stuff. So scalar product is defined. Invariant measure is defined on the space of spin connection coefficient, and it actually becomes operator valued. Now, we want to see the simplest solution. Equation, as you can see, is very different. Now I'm coming to the core of the equations are very difficult, but in the case when cosmological constant is 0, and we can ignore the spin connection term, it means we are considering the space-time characterized classically but 0 value of the spin connection. This is Minkowski space in Cartesian coordinates. We can find the wave in the space of spin connection coefficients and x, which corresponds to this classical object we know as Minkowski space-time. So on the average of the metric operator coincides with the Minkowski metric. Because of this cosmological constant appearing here, the quantity which does not have meaning of cosmological constant in this case, but numerically it coincides up to this coefficient lambda, which is of the order of 110. We know that the wave of this the wave function in the spin connection and in the spin connection coefficients has a range which is characterized by this scale, h, p, g, h, kappa. Now, if we know what is the meaning of the spin connection, or simply connection, it is acceleration. So basically, we introduce the scale in the space of accelerations, and the scale is proportional to the cosmological constant. This is exactly what reminds us the postulate or observation in Milgrovian Mond. Now what remains is to see if actually our values of the cosmological constant and A0, A0 actually make phenomenological sense. And indeed, if we consider Young-Mills on Minkowski space-time, we get relatively complicated the Donner-Weil-Hamiltonian operator, but one can make a spectral estimate of this operator to find the lowest ground state. Because of the Dirac operator equals to the Donner-Weil-Hamiltonian operator, means that all propagating modes, their masses are characterized by the spectrum of the Donner-Weil-Hamiltonian operator. That's why we can say that the lowest non-vanishing eigenvalue of the Donner-Weil-Hamiltonian is actually mass gap in the quantum Young-Mills. And this allows us to identify the scale of kappa with the hadronic scale of the Young-Mills mass gap. This is what produces all the results of the theory, why it is related not to the Planck scale fluctuations, but to the galactic dynamics at extremely large kiloparsec scales. So, what we can do with this? Now we're coming to the end. The picture of quantum gravity, which we have obtained now, actually I forgot to mention what we mean, if someone would want from quantum gravity would ask, what you mean by quantum space-time? The answer is, it is not some discretized object manually invented. It is solution of this partial differential equation, second order in the derivatives of spin connection, which can have two solutions. One is one point function, which is wave function on the space of spin connections and space-time, and second is Green function, which is two-point function, which shows probability amplitude of going from one value of spin connection at one point to another value of spin connection at another point, analog of what would be in differential geometry called connection, but it is quantum connection. So we want to see the particle which moves on the brother, or let's say on Galileo space-time, with the Christoffel symbol generated by the point mass, and all that classical system embedded into the fluctuations of spin connection, described by our wave function. We can do it. We obtain such a generalization of geodesic equation. We just add small fluctuation of spin connection. We know from the solutions of the equation, which was looking like Klein-Gordon in the space of spin connection matrices, in this non-relativistic static limit, only 3 components from 24 of spin connections survive. So we have modified Helmholtz equation. This equation can be solved, and it leads to the wave function of the shape of the Yukawa potential. We can calculate expectation value. We see that the average of spin connection fluctuation is 0, but the dispersion is not 0. So if we take second moment and high moments of geodesic equation with this quantum perturbed spin connection, we get modified dynamics. Namely, we obtain the modification of Newton's second law, which takes into account the quantum fluctuations in the form of dispersion of those fluctuations, defined here. And we can integrate to obtain a generalization of Newtonian potential. In this case, it is hypergeometric function, such that at low distances where accelerations are higher, forces are higher, in this case, with respect to A0 scale, we get the Newtonian regime, but at very large distances, those fluctuations already dominate over the classical Newtonian dynamics, and they lead to the very slowly but linearly growing potential due to the quantum fluctuations of space-time, and we exactly able to describe those fluctuations and their statistics. Now, when we have such potential, we can calculate rotation curves. Still, it is not Mont. Mont appears later. We can calculate rotation curves. Yes, I am really now, there will be no conclusions, but I will show at least the first results. So you can calculate rotation curves, and those rotation curves will be Newtonian. I have graphs, but too long to...
15 of the additional 10 minutes that were given to you. So please come to the end, or we will switch off the projector.
Thank you, Mr. Chairman. I just want to show picture. So this is the rotation curve which we obtain. So it is a Newtonian at small scales, and it is square root law at large scales, not flat rotation curve. But in the middle, which is just around the so-called Milgrom radius, we get approximately flat rotation curve because this parabola is extremely flat. Here it is very exaggerated graph. So we get for Milky Way this region of approximately flat rotation curves with the error of 10% is about between 10 and 30 kiloparsec. If we substitute for the source mass, but it is not the whole story. I will calculate it for higher moments. There is no time for that. But how Mont appears? Mont appears because is that these fluctuations of spin connections are everywhere. So in order to, in one way or another, it put limitation to our notion of inertial frame. We're all subject to those fluctuations. So the most optimal description in such universe with fluctuating field of acceleration is to go to the frame of average accelerations determined by dispersion, use the standard tool in Newtonian mechanics of using a fictitious force. Then we eliminate the effect of this asymptotical small cosmological acceleration, and then from the equations which we derived here, we obtain exactly equations of Mont. So Mont is really a very phenomenological description, using into account that all observers in the universe are accelerating, and acceleration is determined by fluctuations of spin connection of quantum gravity. We're able even to generalize this, but that is already technicality, so I will respect your desire and also desires of people to have cup of coffee, and I will even not show my conclusions because it will take another 5 minutes to list all of them. I think it's enough. Thank you very much.
Okay, thank you very much. Yeah, I'm afraid there is no time for questions since we have to proceed towards the coffee break, and we will reconvene here at 5:15.
Okay, as a
afternoon session after this coffee break. So our first speaker will be Noreis Tahir.
Session after this coffee break. So our first speaker will be Noreis Tahir. Session after this coffee break. So our first.
Okay, there is a bit of echo, but I hope this will be resolved. So he will speak about the evolution of virial clouds too, from the formation of first stars up to their explosion. So please.
Thank you very much, everyone. So I'm very happy to be a part of Zeldovich meetings. This is my first one. I have been a part of the Marcel Grossman meeting. So I started this work with Professor Zilkader and Francesco De Palis back in 2019, and I'll be talking about how we have been able to develop this viral cloud theory. So I'll not take much of the time. So the observations of the luminous universe show only half of the 5% of baryons that are required for the cosmological data to best fit in. But the other half is missing. So it was proposed in 1995 by De Palis and others that there could be a large fraction of missing baryons in the form of pure molecular hydrogen clouds. These clouds are very close to the CMB temperature, so they are very special. And since they are hidden, so they might be in the galactic halos, and galactic halos are populated with a large fraction of them. But to see the clouds, it was not very easy. So a proposal was to look for the rotation of the clouds. So if the clouds rotate away from us or towards us, there should be a Doppler shift effect in the galactic halos. This was the main proposal by De Palis in this paper. In 2011, WMAP data was released, and the group gave a shot towards M31. A frequency-independent temperature asymmetry was detected. But this was only M31. Later, Planck satellite was launched, and the data became public in 2014. The group again analyzed M31, and the same asymmetry was seen, but at a more precise level. Then they analyzed 6 other galaxies, same sort of asymmetry. This was a very strong indication of the main proposal that there could be some clouds in the galactic halos rotating with the halos and are contributing in the missing baryon fraction. Since the clouds were formed due to virial theorem, so we called them virial clouds. It was
I'm afraid we lost your connection. Okay, can you still hear us? Are you still connected? Okay, I think we have you back, but we have lost your screen share.
wrong. So can you see the screen again?
Not yet. I think we need to confirm. Okay, yes, we see it again. Okay, thank you.
Perfect. So I was here that virial clouds had 3 main objections by the Planck group. The first objection was that the clouds cannot be pure hydrogen. They should be contaminated with dust because in the disks of the galaxies there is star formation, and dust can be shifted towards the halo due to radiation pressure and the winds. The second objection was that the clouds cannot be thermally stable. They should be unstable under a gravitational collapse. So they should form compact objects or other things. And the third one was the asymmetry cannot be completely due to virial clouds, as our main proposal said. There should be a fraction of the hot gas component in it and a fraction from the dust grains. The hot gas component will generate the rotational kinetics in the Zeldovich effect, and the dust grains will give us the anomalous microwave emission. So we had to cover up these 3 objections. The first and the second objections were taken care of. We presented the paper in the Marshall-Grossman meeting, the 15th Marshall-Grossman meeting. We modeled the viral clouds, found that the dust is not contributing in the clouds much. So with the contamination of dust, the cloud physical parameters were not changing. We also checked the stability time and the time for the cloud to be to collapse. So it is very clear that the clouds collapse in like 1.6 mega years, and in 1.5 kilo years they'll get stable. So they can be stable, and the dust is not contributing much. Very recently, with Depalis and Professor Kader, we were able to check the two main effects that can contribute towards the asymmetry, the anomalous microwave and the RKS-Z effect. We found that they are not contributing much. Like RKS-Z effect was giving a less than 1% in the asymmetry, and the anomalous microwave emission was giving us less than 7% in the asymmetry towards M31. We also checked it for M90 and another candidate, so it was not very much towards them also. The objections were taken care of, but this does not reveal the true nature of the viral clouds. To check this, we had to trace the evolution of them, because the asymmetry does not show what the viral clouds exactly are. We just had made a toy model and checked the parameters, but what they truly are needs some evolution. It is proposed that they were formed at the surface of last scattering when hydrogen and helium was born. So we had to trace their evolution. Since then, they collapsed in a dark matter halo. So one can simply check the evolution from the last scattering surface to the present. So we don't have to rely on ad hoc models. We divided the evolution in two stages. The first one was a very simpler one. We don't need to consider population 3 stars in this, so we stopped up to the formation of population 3 stars. The second one was to look beyond the formation and then the explosion of population 3 stars to the present. So the redshift will be 48 to beyond. The evolution one, during the evolution one, since it is last scattering surface, so we should have a primordial mix of hydrogen and helium in the viral clouds. People say that there could be other elements in it during that time, but the fraction of other elements is less, very less. Atomic hydrogen to molecular hydrogen is like 10 to the minus 6, and other elements are also negligible. So we can rely on the primordial mix of atomic hydrogen and helium. Since the clouds were in the thermal equilibrium, they are stable, so CMB will act as a heat bath. The canonical ensemble distribution can be used very well. We modeled the clouds using the canonical ensemble distribution. We got an expression for the density distribution of the clouds. Look at the equation number 2. It is more like the Lane-Amden's equation. By solving this, we got the density distribution of the clouds. So it is clearly seen that with the passage of time, the clouds got more denser. And for the mass and the radius, they lost their mass and they shrunk in size. So became more denser, lost their mass, shrunk in size. So this was the story until Z equals to 48. For the second part, it's not very easy. The first part does not require any nuclear reactions to take place. But in the second one, there should be nuclear reactions and there should be heating and cooling, because of two reasons. The first one is that population 3 stars are forming, and so viral clouds are there. During the formation of population 3 stars, there will be bursts and viral clouds will get contaminated. So nuclear reactions will get triggered. Also, there is a gravitational collapse and there is a loss of energy due to radiation. So heating and cooling processes will come in. For this reason, we started again with we started the evolution 2 by considering that there's cold dark matter halo around viral clouds, and they are gonna collapse inside the potential well of the CDM particles. Since this is a very complicated system, so we got 4 coupled ordinary differential equation. The first one will explain the temperature variations with respect to time. The second one will give us the metallicity. The third one will give us the heating and cooling rate due to molecular hydrogen. And the last one will give us the mass evaporation rate. These equations are not very simple to solve. There are other parameters involved in it. So we have to take care of all of them one by one. And the other things are the constants. And this is the mean molecular weight, the number density of hydrogen, the radius of the cloud, the volume it carries, the cooling rate, the external heating, the redshift with respect to time, and the so-called Jeans mass and radius. Hence, it is very clear that dark matter has shaped up the universe, and missing baryons are in the cold regions of the galaxies, the galactic halos. Viral clouds are populating these regions and can be seen by the CMB data, and they give a very good effect in the cosmic microwave background radiations. The evolution of these clouds is needed to understand the true nature of them. They will open up a window to understand the formation and evolution of galaxies more precisely. Since they are in the halos, halos are mysterious, so we have to understand the halos. To understand the halos, we need to understand virial clouds. The first stage was very simple because there were no quantum effects and they were neglected. The second stage, we are incorporating the quantum effects, and we are also incorporating the other stuff in it. And we hope that with evolution, too. Thank you so much.
So are there any questions? We have some time for a couple of questions, I think.
Okay, I cannot see now. I think I can see.
Okay, seems there are no questions, but Timo, would you like to? Okay, there are no questions. I think everything was very clear. So thank you very much again.
Thank you so much. Thank you so much, everyone. So thank you.
And we proceed towards the next presentation. So the next talk is by Simone Monda on neutrino mixing in torsion-fold spacetimes, quantum gravity signatures, and dark universe implications.
Sì, ma ritiro tutto. Aspettate. Ok. Adesso. Tutto buono? Sì, sì. Ok. Con la traccia vai avanti e poi dopo. Ok. Se ti serve il puntatore. Ok. Questo qua. Ok.
Hello everyone, I am Simone Monda, PhD student of the University of Salerno, and today I'm talking about how a torsion coupled to a binaural field in framework of quantum field theory. We start introducing the formulation of Einstein-Cartan theory, and we introduce what about the affine connection and what is the metricity condition. We generalize the field equation in U4 theory via variational principle. We show you new oscillation formula in presence of torsion, and we show you how torsion couple to fermionic field in quantum field theory in torsion full gravity. We know that the sum of two affine connections is not a tensor, and so let me introduce the S tensor, the Cartan tensor, defined as the semi-difference of two affine connection gamma. So generalization of Einstein-Cartan theory is obtained by considering this non-metricity equation. In particular, we consider the case in which the non-metricity is equal to 0. That's ensuring the conservation of length units at angle under parallel transport. The affine connection can be split in two parts. The first one is the Christoffel symbol, and the other part is the contortion term. And so the linearly connected spacetime L4 endowed with the metric G reduced to the Riemann-Cantor spacetime in the case in which the non-metricity is equal to 0. In particular, then the entire this U4 spacetime come back to the Riemann spacetime characteristic of general relativity in absence of torsion, and then we come back to the Minkowski spacetime in absence of curvature. In particular, to introduce how to obtain this field equation in U4 theory, we start with the action of the field, in particular with the matter field and gravitational field. In particular, varying this action respect the two independent variables like the metric and the Cartan tensor, and using the modified Palatini equation, we obtain the two field equation in U4 theory. In particular, the second one is an algebraic relation between spin and torsion, while the first one is a generalization of Einstein equation. In particular, we can split the Einstein equation in two parts. The first one that depend only on the Christoffel symbol, and the second one related to the energy momentum tensor. In particular, it's trivial to show that in absence of torsion, we come back to the Einstein equation, and in particular, this energy momentum tensor is symmetrical by definition, and it satisfies this conservation law. In particular, geometric concept of torsion is intrinsically linked to the local transformation of Poincare group. And so the local Poincare group leads to the Einstein-Cartan geometry. That was shown by Hell in one of the review modern physics in 1976.
And what is this D exactly?
What is this? This
So
one?
No, in the last equation.
Okay, it contains the energy momentum tensor of standard general relativity plus an additional term related to torsion. And in particular, in principle, you can obtain a variation of what are considered only in general relativity. In particular, if you have this operator depending on time, you can consider, for example, additional term related to, for example, gravitational wave related to the time dependence of this term. But we don't have considered, we don't have used this equation because we are focused on quantum field theory. And so to introduce the new neutrino oscillation formula, let me explain what about the mixing in quantum mechanics in particular. We know that the neutrino flavor state, it is related to the neutrino state with a well-defined mass by the mixing matrices. And how was showed by Pontecorvo in 1978, this is the oscillation formula for the transition electronic neutrino to an electronic neutrino. But in quantum field theory, the generalization to quantum field theory consider the mixing between not the state but the field. And so, as was showed in the PRD in 2002 by Blasone, Capolupo, and Vitiello, here are reported the analytic structure of the oscillation formula for the transition neutrino-electronico in function of time, in which U and V are the Bogoliubov coefficient. But what we have considered is we have obtained the new oscillation formula, but in the case in which we have torsion. As was showed in this paper in Universe that was published in Universe in 2024, we considered in the framework of quantum field theory this equation that contain torsion. In particular, the only one term that coupled to fermionic field is the axial torsion. In particular, we are considering two different cases. The first one is the case of constant torsion, and the second one is the torsion that depend on time. And so we have solved this Dirac equation in presence of torsion in the first case of constant torsion. And these solutions are analytically similar to what are considered in quantum field theory in absence of torsion. The only difference are contained in this term, m tilde, that contain the mass of the neutrino and plus or minus depend on the the spin which is oriented, aligned respect to the axial torsion, this term of this quantity that is the axial torsion. In particular, the linearity of the generator allows us to define the Flavor annihilation of the field. And in the case in which K is only on the third direction, this is the analytical structure of this Flavor annihilator, in which gamma and sigma are the Bogoliubov coefficient. In particular, in the case of constant torsion, here are shown the analytic structure of the Bogoliubov coefficient. To introduce, now it's possible to introduce how was defined the neutrino oscillation formula in the case of constant torsion, and what is the, and it is trivial to show that it satisfies the this normalization condition. In particular, we can retrace the same calculation made in the case of quantum field theory standard in absence of torsion to include torsion in this case. And so the reason is that the entire effect is contained in the Bogoliubov coefficient. And so this is the analytical structure of the oscillation formula that we have obtained in Universe, in the paper published in Universe in 2024. And this oscillation formula depends on the orientation of the spin. And the entire effect is contained in this Bogoliubov coefficient. In particular, here I need this slide only to show that the oscillation formula depends on the spin, and in particular, the oscillation formula for spin up is different to the oscillation formula for spin down, as was shown in this plotted, that we have plotted the oscillation formula in function of time for spin up and spin down. And on the right side, in this panel of the right, in the right side of this panel, we have the corresponding one is only how to say the detail of the same formula compared to the corresponding quantum mechanical oscillation formula. Then also we have solved the case of the Dirac equation in presence in quantum field theory in presence of torsion, but now the torsion depends on time. And to solve this equation, we have considered this expanding of the in flat wave in the usual way that we have in quantum field theory in curved spacetime, and we have used the standard ansatz to solve this equation for positive and negative energy. In particular, the function what we need to solve in particular in this equation is the function f and g depending on time. And so we have, this is the solution that we have obtained analytically, and so then imposing this normalization condition, we have determined the coefficient that appear in this solution. In particular, also in this case, it's possible to write the Flavor annihilator for the Flavor annihilator by the linearity of the generator. And here we have reported the Bogoliubov coefficient in the case in which the torsion depends linearly on time. And so also in the case we can retrace the same calculation made in the case of torsion for constant torsion, because the entire effect is contained in the Bogoliubov coefficient. Also in this case, the oscillation formula depends on the orientation of the spin, and at the same way we have in this plot the oscillation formula for spin up and for spin down, and the detail of the same formula compared to the quantum, the corresponding quantum mechanical oscillation formula. Then we have studied the impact of torsion on the psi-p violation in case of constant torsion and time-dependent torsion. In particular, also in this case, this p violation depending on the orientation of the spin. And here we have plotted, in the case of constant torsion and time-dependent torsion. Also, we have evaluated the vacuum expectation value of the number operator, and for three for three generations of neutrino, we have not only that the vacuum expectation value depend on the mass that were considered, but in this case, in presence of torsion, depended also on the orientation of the spin. And in particular, here we have the case, the plot of the case of, in the case of constant torsion and time-dependent torsion. But what we have then published in another paper is how torsion couple to fermionic field, but in this case in torsion full gravity. And so in particular, then we have solved this equation in curved spacetime. In particular, we have considered the Friedman-Robertson-Walker metric, and we have solved this Dirac equation in torsion full gravity. We have used these answers typical for general relativity in this frame, in this context. But in this case, we have only one fermion. So we don't have considered the case of neutrino. We don't have considered now the oscillation formula of the neutrino. But we have considered only how torsion coupled to fermionic field in torsion full gravity. In this case, due to the torsion, the Hamiltonian is not diagonal in the annihilator of the free field, in particular on this expansion that are expanded by this B and D operator. But due to the torsion, the Hamiltonian is not diagonal. In particular, it assumes this particular matrix form. But this Hamiltonian can be diagonalized by a Bogoliubov transformation. And so let me introduce this new operator B and D, and the vacuum annihilated by this new operator, let me say by 0C curved spacetime, is linked to that one considered in the other expansion where B and D are that one annihilator. By the following relation, which R is the generator of this Bogoliubov transformation. And so let me define this tensor L mu, that is the vacuum expectation value of the axial current on this vacuum, where this vacuum is that obtained by diagonalizing after the diagonalization of this Hamiltonian. And what we have obtained is that this vacuum expectation value is different from 0. And furthermore, this vacuum expectation value of the energy momentum tensor is different to 0. So this leads to a typical equation of state for the radiation. In fact, this is 1/3. And torsion introduces additional term in the Einstein equation, in which on the left side we have the standard Einstein equation, Einstein tensor, and on the right side we have also this new term, this additional term, related on the condensate of this structure. And so the Einstein-Cartan theory is a modification of general relativity. And since spin and torsion are intrinsically linked, it has been shown how torsion couple to Dirac fermion. We have derived the new oscillation formula that depends on the orientation of the spin. And we have shown that the energy splitting introduced by this torsion term affect the oscillation formula. In particular, torsion are relevant for neutrino oscillation in non-relativistic regime. Therefore, experiments studying neutrino with very low momentum, such as Ptolemy, could provide verification of these results in future. So, thank you for your attention.
Thank you very much. I think we have time for one short question there, or maybe two. Okay, well, let's see. Let's start on the front.
Thank you for your talk. My question is about CP violation. What kind of implications your solution have for the CP violation in case of time dependent or time independent torsion?
Okay, the different we want to show how this case, which is the difference between the standard case in absence of torsion. In particular, we only show that the most relevant important thing is that now CP violation depends on the orientation of the spin. Your question is how that these two different type of CP violation are splitting. But what we have considered is only relating on the what is the difference between the case of the standard thing. So for us, it's really important that they split to the standard case. Probably I can show you something after. Yes, it is defined in this case, which now it depends on the. It is defined as follow as the oscillation formula for spin up in a fixed spin. It depends on the neutrino oscillation by neutrino and antineutrino. But the most important is for this case is that depend on the orientation of the spin.
Would it make sense maybe to think about a neutrino as particle with no mass, but with what we interpret as mass just being due to axial torsion background?
Interpreted neutrino as?
The neutrino mass as coming as some kind of an effective effect from a background torsion.
Okay, the problem is that when you consider it in quantum field theory, standard quantum field theory, without introduce torsion and other generical thing, when you is really strange for us to introduce these in quantum mechanics. You have the matrix for the oscillation, the mixing, but in standard without introduce torsion, something like that, you obtain the oscillation formula that is related to the generator of the transformation for to the Flarer state on the mass state. In absence of mass, you don't have this mixing term. So you can consider without mass this quantity. You can, in principle, consider an effective theory in which you can introduce a mass, but you need to choose a very particular effective theory that you need to choose why, you need to explain why you have this particular mass, and so we have fixed the mass, and then in the standard way that is accepted by everyone, we only modified the Dirac equation.
Thank you.
And so only to simplify, in absence of mass, you don't have the mixing. Because they depend on the difference of the mass of the two mass of neutrino. Also in this case, you can consider for Pontecorvo in 1978 the probability oscillation formula depend of the difference of the mass of the two neutrino.
Actually, in the curve spacetime, if you write down Dirac equation, I'm sure you know this, then automatically this axial vector term will arise. And then if you write down the inter-Hamiltonian in local coordinate, you will have actually effective mass. You will have mass term, normal mass, and then other off-diagonal term will have terms arising through the axial vector. If you write down straight away Dirac equation in curve spacetime in local coordinate, it is still Leonard Parker, 1980s. It is nothing, I'm saying something new. Look at since 1980s, Parker and then Huang, you can look at. Anyway, my question is different. My question is, as because you repeatedly showed that correctly, nicely, upspin and downspin will have different oscillation probability.
Yes.
And as because you are applying for neutrinos, as you know, I'm sure, according to standard model, upspin is almost, if you neglect small mass, upspin is basically neutrino, downspin is basically antineutrino. That means you are saying effectively neutrino and antineutrinos have different probability of oscillation, which implies that you have effectively leptogenesis, lepton number violation, because by oscillation. So is it, so basically my question is, at which limit you are actually, basically you are predicting, it's interesting, you are predicting leptogenesis, which could lead to the baryogenesis eventually. So what limit it can be really visualized, and can it be really recast to the famous baryogenesis problem?
Okay. Thank you for the question. We don't have considered this thing only because when we have analyzed this quantity, quantum field theory in presence of torsion, that is the first paper that we have studied in this context. And so we have only analyzed the first approach. This is the first approach in quantum field theory in presence of torsion. So a lot of aspects that we want to work on these things, but we need more time to explain you all these different aspects. But also for the other question, we can also work together on work a lot on this theory. But in this case, probably we don't have focus on this particular thing. So for sure we have, I understood what you want to do, but for sure we have this split, but we don't have focus on this particular thing.
Okay, thank you again. We need to continue to the next speaker. So the next speaker is Fernando Isabella, and he will speak about toward principle unifying the standard model and gravity.
Thank you. Thank you. Thank you. Mine, I put it in the web page. Let me see. It will be in, where is calendar maybe? Okay. Let me see. And that's me.
It's yours,
Yeah, and the materials are here.
Okay.
If we could download it. And, okay, cool. And coach. And next is with this one.
Next.
Okay.
Only point.
Okay, on the point. Okay, thank you. A big unified theory of everything. That's the holy grail of physics, the one ring to bind them all. Yes. How I pass it? I would love to show you that unified theory of everything, but I can't. I don't know how to make a unified theory of everything. And this talk maybe should be called maybe how not to build a theory of everything. I want to show you some funny coincidence. If you try to do this in a very naive way, it is interesting. I promise to be short and simple because it is the last afternoon, so I know everybody is a bit tired. So I want us to have fun with it. So I would like to invite you to a little game. It is in the spirit of Feynman's dad's game of look at it as a Martian. Let us look a bit at physics in a completely naive way, as if we don't know anything. Okay? If we do that, and we look at a theory of almost everything, all the known physics, we may ask if does it look as a coherent whole? And you're a very sophisticated audience, so I know that if I ask that, you will start thinking about string theory, about grand unification, symmetry breaking, etc. I mean something way more simple. I'm meaning something more in the spirit of, should you print that into a t-shirt, okay? Because if you look at the fundamental physics, you will find that it looks kind of strange. I mean, you have a quadratic in gauge curvature, the Young-Mills term. It is nice, it is elegant. And then you have a linear term in the sector of gravity. It is in the curvature, but it is not the same kind of term. You know, it is a linear term and it is a contraction. And then you find the fermions as fields in a multiplet. Now it is not a curvature, it is a multiplet. Okay, so okay, it is another ingredient. And then you add an scalar. And then, as just a last act of craziness, you add a constant. Why a constant? It is just there. Okay? So if you look at it in a very naive way, in this spirit of Feynman's that game, you will conclude that actually physics is not like a coherent whole. You know, if it was a suite, it is not a kind of an elegant suite. You know, it is more like this. You know what I mean? Every piece is kind of beautiful in its own. It works, of course, but it doesn't look as a coherent whole. So we may ask if it is possible to do that, or maybe trying to do that in D=4. Okay, just as a game. Okay, don't take this too seriously. Okay, so let us try to do that. We may ask, what about making something as a Young-Mills gravity? How will that work? Well, it doesn't work. Okay, don't do that. It is a bad idea, but it is interesting why it fails. Right? That is what I want to show you. You know, it starts nice. You can think of an ADS algebra valued connection one form. You have the spin and the Firmine. There we are just in D=4. Okay? And you may write the gauge curvature for that, and it is that. You know, it is the ADS term plus torsion. Okay. And you may ask, well, what will happen if I write the Young-Mills term for that F? It is simple. We can do exactly the same that with all the other interactions. We have to use the Hodge dual, of course, that maps P forms in D minus P forms. And when we do that, it almost works, but it fails. How it fails? Well, the first crack is that the gauge invariance gets spoiled. Okay, why? Because the Hodge dual is a function of the Firmine. So if the Firmine is part of the connection, it will also change. So it won't be gauge invariance. But let us try. Let us see what happens if we do a Young-Mills gravity. And what we find is the first term is just the Einstein-Hilbert term. So it is very much welcome. Then we have a cosmological constant term. And then we have these two yellow terms. The first one actually is just the Kretschmann invariant. Yeah? And the last one is a contraction of torsion. And we may ask, maybe, why not work with this theory? Well, it doesn't work because these two last terms are sources of ghost. So your theory will get eaten away by ghost. It is a bad theory. Don't do Young-Mills gravity, okay? And the actual thing there, it is that D Hodge D is not zero, you know, where this D is just the exterior derivative. But anyway, okay, if we are in this game, why not trying to add fermions? Okay. Well, I was thinking of Occam. You know, everybody knows the Occam's razor. That is the only portrait of Occam I could find. He was from the Middle Ages, so that is what it is. But the point is, what if we try to write a theory with the only ingredient as a gauge connection, and it has to be valued in some super algebra, so we can put fermionic fields. The only problem is that these fermionic fields have to be a kind of a Rabita-Schwinger field. They have to be 3/2 fields. But anyway, we can do it. It is just a game. So we can try to do that, and let us see just to the sector that has fermions, what happens. To introduce fermions as the ones of the standard model, we need to split this Rabita-Schwinger field and just focus on the sector that can be written as a field of spin 1 plus a field of spin 1/2 as a standard fermion, as a standard model fermion. It means in practice to write it as a Vierbein times a fermion. Okay? So we do that. We introduce it, and it almost works. And that is the exciting thing. You know, we get the Dirac term, we get this other term here. It just adds a non-minimal coupling with curvature, actually, this term, but it is kind of inoffensive. But the problem is that we get the Klein-Gordon term. So our theory, again, is eaten away by ghost. Don't make this, it won't work, okay? So that is the lesson. It is not so easy to make a theory of everything in D = 4. Okay? But how we can solve it? There are some ways of solving it. In fact, there are some ways that everybody knows as McDowell-Mansouri gravity. You know, what you do? You change the dual. This Hodge was the problem. So you just came up with some other dual. Why? Because it works. You create a dual, so you get what you want to get. Okay? And you introduce this new dual, and the Kretschmann term transforms into the Gauss-Bonnet term, which is inoffensive. So this thing works. But maybe it is a bit ad hoc. You know, it works too well. It works because we created it to work. You know, it is not kind of intrinsic. We created a new dual, so we get the answer we want to get. But anyway, it is also possible to do a super version of that. And in fact, it also works if you are really tricky. You know, you can create a new dual, so you get gravity and also fermions, but it is also a bit ad hoc. You know, you are creating a dual, so you get the answer you want to get. So maybe if it is possible to do something distinct to this. And actually, the answer is yes. You know, what if the Young-Mills term is only the first one from a series of terms? What about if we think of some unknown series with only these ingredients, with a connection and a Vierbein and the Hodge dual that we already have it in the Young-Mills term? If we do that, we may wonder, okay, a series with that form where this thing is something I don't know. This kind of series may look very general, but actually it isn't. If you are in D = 4 and you use the differential forms language, you will find that this series is not infinite. It has really a very small number of allowed terms. So you may wonder, what happens if we make this game with this new action? We will get rid of all the ghosts. No. Actually, it turns into a ghost party. Every possible ghost there goes into your theory. It is terrible. Unless you choose the coefficients rightly. It happens that for a very particular choice of the coefficients, the theory turns out way more healthier than you would expect. If you do that, the theory finally will look as the following. This first line is just standard ADS gravity. Okay. The second line is the Dirac term plus some non-minimal couplings. Then we get a Young-Mills for the internal sector, plus these other terms that also don't have ghosts, plus these yellow terms that maybe have ghosts, but we are hunting them. We don't know still if some ghosts survive there or not. But it is really curious that all this yellow line is affected by torsion. You know, if we don't have torsion, then it looks as a completely healthy theory. So some questions, we don't know the answer. You know, it is just a game. Yeah. So well, it is the path to a one ring, or maybe it is the path to Mount Doom. Yeah? The first question is why such a naive idea works so well. Okay, it is such a very simple idea, and it gets way farther than we will think at first. Then, how to explore all these ghosts? It is still a trouble. We are doing it now. We are working on it, really seeing if some ghosts survive it in this torsion sector. Why torsion is always in the way, I don't know. And well, and how to put Higgs here. We are also working on that. And there is one question I can answer, and why it is called LL. That is the only question I know the answer. And the real reason is kind of funny. It happens that my collaborator and me, we both have daughters of the same age, you know, and both of them have names with L. You know, they are exactly of the same age. So we put to this theory LL, you know. It was. So, grazie mille. Thank you very much for your attention.
It's very nice and unifying talk. Are there any questions?
You mentioned conservation principle.
Yes.
Why should nature choose the combinations of reactions?
Actually, there is no reason for that. Actually, it started just as a game with a colleague. Actually, we were betting on a bottle of whiskey. Okay, and it was kind of a dare. Can you make it really work with only one ingredient? It was really a game, and I wouldn't expect it to work so well. But it worked so well that I wanted to share it with you.
Okay, so we should continue. Thank you again.
Thank you.
And we come to the last scientific talk of this meeting. The speaker is Stéphane Vallerand. And the topic is addressing the Hubble tension with a dynamical lambda of Z induced by galactic gravitational safe energy and the back reaction force from gas cloud collapse.
Sorry. Put in my pocket.
What is
It moves the slides also?
What is the presentation?
The last one, you can... No, really the last one, Friday. Voilà, addressing the Hubble tension this way. This move the slides also?
Next.
No, it's okay. No, just stay there.
Only point.
Only point, okay. Okay.
Next, please.
Okay.
Okay.
Okay. Okay, dear colleague, good afternoon. I will present you how a back reaction can explain or address the Hubble tension. So we start with the FRLW perturbation metric in the conformal Newtonian gauge. This metric uses the two gauge invariant Barden potential psi and phi. And we make the simplification that these two potentials are equal. It is quite easy to demonstrate that if a quantity Q is solution of the Einstein field equation due to the invariance of the Barden potential, the expansion, the whole expansion is also gauge invariant, and then because if you multiply the potential by any constant, the series has to be invariant, and so with the property of the power series, each term of the series has to be gauge invariant. The first Einstein field equation show two additional terms at the one of the second order to the Friedman equation, and this see that phi is solution of the relativistic generalization of the Poisson equation, and thus phi represent well the gravitational potential. The velocity Einstein field equation contains two additional terms versus the Friedman equation, one nonlinear and one second derivative time of the potential phi. For a random distribution of identical spherically symmetric bodies, we have the liberty to choose a reference frame where all the bodies center, the center of the bodies, are at rest. And you show that with that, we get here a positive term which acts like a cosmological constant. This was already supported by the work, or pioneer work of Thomas Blücher, where he showed that localized events can back react on the global expression. The difference here is that there is no averaging need. It's just a second order term. It is the self-interaction of the galaxy mass at the center, Laplacian phi, with its own gravitation field phi. It is just like similar that the self-interaction of the electron with its electromagnetic field in quantum electrodynamics. Let's just recall that the Mercury perihelion precession is already due to a nonlinear effect, the interaction of the sun potential with the centrifugal force on Mercury. We modeled a 3D lattice of spherical Gaussian bodies, and Fourier series analysis give this expression for the potential at the center of the bodies, for its derivative, spatial and time, and also this expression for lambda. This was already done by Bruneton and Larena, but using an expansion NV to C. Now look this expression of lambda. to be applied to the universe, we need the ratio, the mass to the square, the sigma square should be uniform across all galaxies to have a global lambda. And it is exactly what the gamma survey revealed, that the compactness ratio is almost constant for all the galaxies. You see at the point there are some dispersion. And if you use this compactness ratio measured by the gamma survey, you see that the predicted lambda value is in line with the experimental observation. Next, it's possible to show that to preserve the energy, we need that this term is constant. This involves that the galaxy radius is proportional to 1 plus z exponent minus 1.5. And also here, it's exactly what the candle survey show. The experimental value is minus 1.48. So, because the lattice pitch is not present in the result, and that the mass compactness ratio of the galaxy is uniform across all galaxies, shown here, it's safely applicable to the actual universe. Now, let's have a look on the second term. In a free-falling collapse, the second derivative time of sigma is negative, so you get a positive back reaction, in contrary to the cosmological constant. Of course, at the end, when the collapse ends to form a star, you have a negative back reaction, but this back reaction is reduced because in the other side, a pressure term also back react in the opposite sign with the collapse ending. A really rogue approximation computation show that omega alpha in the Lyman alpha Forest epoch is around 20. So it's not a negligible term. Here you can see here bottom the fit of the omega lambda and the omega alpha needed to predict the modern value of the Hubble constant. And you see that the evolution is coherent, consistent with the cosmology history. Before z equals 3, the universe is almost homogeneous. Donc, in this theory, the 2 alpha vanish, are 0. The gas clouds start to collapse after z equals 3, and to reach a peak star formation around 2.3, which decrease and finally vanish when the galaxies are running out of gas for star formation. And at that time, the galaxies start to assemble into modern structure to give the modern lambda value. You can see that using this history of the Hubble parameter with this value, it's possible to exactly reproduce the Planck angular scale. You can see that the major difference between the lambda CDM model and the model here is, of course, the period between 0 to 3. And also it reproduces the baryon acoustic oscillations and also preserve the structure clustering amplitude S5 because it's only a late effect. So, in conclusion, the model shows that exactly like in quantum electrodynamics, the non-linearity term of relativity cannot be overlooked. And it's already the case for low speed, low field for the Mercury planet. So I don't see how we can imagine that we can neglect this non-linearity of general relativity for the whole universe. It also shows that localized events can back react on the global expansion as pioneered by Blücher. The model predicts the gamma and the candles survey data of the galaxy. It predicts also the angular Planck scale, the baryonic acoustic oscillation, and the growing factor S8. The next step, of course, should be to predict the real theoretical form of this back reaction during the Lyman alpha forest epoch, rather than to use, and in this first attempt, a phenomenological function. Thank you for your attention.
Thank you for this nice presentation. Are there any questions? Okay, I don't see any questions. Okay, so then thank you again. And then there is just one item on the agenda, which is concluding remarks, and I hand the microphone to Remo Ruffini.
Thank you so much. And it has been a very, very intense week. And we started, please come in front. We started after a meeting in Lausanne in which at the European Astronomical Society, all the astrophysicists were under shock because a new reality appeared very clearly. They symbolized this new moment with an analogy with eggs and chicken, which has become very, very common for representing this new paradox. At the center of this paradox, there are black holes, which were introduced many years ago at Princeton by John Wheeler and myself. And we always moved under the general understanding that black holes had necessarily evolving from the initial formation of structure in the universe to the latest phase of evolution where the black holes were observed. And indeed, in this meeting, we had the pleasure to retrace all the details of the formation of the black hole from the beginning to its observation. In GRB 220101, the formation of a black hole of 2.35 solar masses with a very small error bar. But this is the traditional physics of black holes. But what happened thanks to the enormous progress made by the James Webb Telescope, enormous revolution, it started to be presented a very new situation that in the beginning of the universe, in the early phase of the universe, which had been well described by Fermi and Turkevich and Gamov, in that early phases of the universe, where the hydrogen and helium were initially formed in the Big Bang, there appear to be also a new kind of black holes, very big, of the order of 10 to the 6, 10 to the 7 solar masses. Therefore, not only black holes small of matter at the end of the thermonuclear revolution, but also black hole very, very massive in the beginning of the universe. This, the evidence for them was clear by what everybody knows in all the scientific journal today, even the red dots, this very tiny red spot which are identified by this marvelous telescope in the earliest part of the universe. This is very likely the greatest revolution in astrophysics. Certainly, it changes observationally everything, but also the paradigm need a new understanding. And the beautiful result of this meeting is that we started the first lecture exactly on the red dots after my introduction by Wang Yu. We gave the first image of understanding this novel structure of the red dots. And bit by bit during the week, we start to focus every day and understanding more. But we were in good company. And finally, we have reached a grandiose understanding that I will indicate at the end, or even now, that we have evidence for the first time clearly of the discovery of a new component of the universe, the dark matter component, and contrasted with baryonic component of the universe, which form the traditional black hole. And this has been one of the major understanding outcome which we are developing. Therefore, the beginning was represented by this, which then was understood more and more during the entire week. And it was presented in the first day as an opening. And also we took advantage, because the meeting was dedicated to Zeldovich, Yakov Borisovich Zeldovich, who we all admire and recall, and is also in that picture there on the wall, which I took in Moscow, and Zeldovich is on the left and Bruno Pontecorvo on the right. We celebrate this Sixth Zeldovich meeting with the presence of his greatest collaborator, Rashid Sunyaev, who gave us a splendid lecture and a lot of result coming from the observation of the Atacama Desert, and we were really, the other specific great moment of the meeting. Collaborator of Rashid came from various parts, and Battistelli came here in person from the group in Princeton, Shuba, and other people. But the day after already, we decided to look at the new physics of GRB. and we analyze a new structure of the GRB, which has become preponderant and very with the presentation by Orger Ueda and Raim Moradi. Raim is here, I think. Oh, there it is. Come in front. And this was a splendid occasion to again present a possible change of paradigm in the understanding of the early phases of GRB. It is clear now that the early phases of a GRB are dominated by very powerful sources of ultra-relativistic acceleration process, the UPE, the ultra-relativistic prompt emission phase. And we think that the early beginning of a GRB is dominated not by general relativity, but the first appearance after the formation of the supernova of electron-positron plasma and by quantum electrodynamics. This was a novelty which we presented in this meeting and was presented very beautiful by Raim and Orger Ueda. But that same day, after this very conceptual revolution again, we had the great honor to have here Bing Zhang from used to be in the United States. He used to direct one of the most prestigious journals in relativistic astrophysics, was a founder. But he came here in person because we have started working on the preparation of the next Marcel Grossman meeting, which will be next to July in Hong Kong. To have Bing Zhang here with us has been a strong motivation. And in parallel, we had the fortune, we have very, very strong contact with our Chinese colleague, in addition of Wang Yu and Shui, who are here always. But we have contact almost daily with the group of Dili, who built the largest radio telescope in China and is having a great success. And we are trying to collaborate, implementing the use of the telescope fast telescope in China with observation from the radio telescope in Italy, also from Sardinia, and the SCA telescope all over the planet. And it was fantastic to have here the presentation of Dili. But together with the presentation of Dili, because this has been the mixture of this meeting, because we had a very new concept and big participant like Zeldovich, like Rashid Sunyaev, who was one of the first collaborators, and was a pleasure to have him participate because we could recall a lot of anecdotes. My first going to Russia, to a meeting there in '68, and meeting for the first time der Zeldovich. But this was already an adventure, because to reach the place of the conference, the plane left from St. Petersburg, and it went we were very happy to be in this very advanced airplane. And it was quite an adventure, because as we came on the plane, I was with Komar, and they said, "Oh, please come in front, because there are 2 places reserved for you." And I had heard a lot of joke about this place reserved on the Russian plane. And indeed it was true, there were 2 places reserved for us, but the only place in the plane without window. And, and I was very upset with Komar. But I tell you, because all our life has been with accident, pleasant. And in between Komar and me, there was another person. And we start to speak about this situation in Russia. How can they do a thing like that? Not to put us, and then Komar said, "Well, yes, because we read the New York Times. You know, there is a new person in Russia speaking loudly against the existing rules, Sakharov." And we start to speak about him. But we forgot that there was somebody between me and Komar listening. Well, anyway, I want to tell you this story because it's so beautiful. The plane went down very rapidly, after 3 hours flight. There was a great bad weather. They decide to land. And this gentleman, which was between the 2 of us, we had to spend the night there. He was very distinguished, calm, sitting on a chair in the airport. And I decided to approach him, Ruffini, Italy, and he answered, Sakharov, Soviet Union. This was the first time that I met Sakharov. And we were good friends for all our life, and we celebrate many times together this adventure. And the day after, finally, we reached Tbilisi, and I met for the first time Zeldovich. But Zeldovich was at times very unpredictable. And he asked me, "Please, what you are doing, what you are working on." And I told him about scalar field. And I am very happy to have here some of the people who still cultivate this topic of the scalar field in general relativity. And I start to speak, and Zeldovich said, "Stop!" Why stop? Well, he said, if Landau was here, he would have, how long did you speak? 20 seconds. If Landau was here, he would have stopped after 15 seconds. Why? And I look at him, I said, and this continued for all our life, this relation, I think you are wrong. If Landau was here, he would said, Remo, please continue. And this was the first, my meeting with Zeldovich. which characterize all the subsequent discussion and dispute, even when I introduce him to the Pope. Paul's in the Vatican, and they were very beautiful moments, which we recover still because present in that first meeting was Rashid, and we had the pleasure too. But I was saying something that this mixture of history and Russian is really flourishing also in this meeting, because we have Bulanov who is here, and he managed to introduce the work on laser to make a model precisely of the fast radio bursts which were presented here by Dili. This has been the beauty of this meeting, to have some of the people, the most advanced people in the field, like Dili, presenting fast, and Durbe presenting the data from the Observatory of Cagliari, and propagating to all the SCA mission, and to have also some historical people who could present a model finally for the fast. And this happened here in this meeting. This has been one of the beauty of the meeting. But we continued after, on the day after, we presented the BDHN model, and Bulanov presented his first model, and we had a beautiful meeting. And then on Thursday, Aymuratov and Shurui presented novelties about the energy extraction of black holes by the Penrose process. And still keeping going, we had Jutta Kunz, Perlik. Jutta was very interesting because I explained to her why I am skeptical about the creation of sources of gravitational waves from black holes, because I am convinced, not only me, but Einstein himself was against the production of gravitational wave, not in bulk, like people are proposing from black holes. And he was much in favor instead of a creation, emission of gravitational waves at the linearized level out of binary, the process which was presented here by the group of Cagliari Observatory. But let's continue, but I don't want to continue for too much. This morning, therefore, we had also a very, very, very important visit by a university which is member of ICRA. You all know that the president of ICRA is Wang Yu. But the university in China, which is member of ICRA, is USDC. And in this meeting, USDC sent a jewel, a real jewel, when women Liu. And what is the jewel? Was the presentation that the rotation curve of galaxies, which have been studied for a long time by our group, and especially our group in Argentina, he showed the clear identification of this flat rotation curve with this dark matter, and realizing just in the images that the dark matter component in the rotation curve and is the key for the formation of large black hole. And this we had an important set of discussion confronting the idea of the center of the galaxy dominated by fermionic particle, which we call X-fermion, which were introduced here in Pescara by the collaboration we have had on this dark matter, which is really very, very beautiful and very important. Well, there were many other important contributions. And we had also this mixture of historical people looking just around and which are still related to Zeldovich and Lubimov and is here and all the observations which are made of the supernova and many other topics. But going back to the fundamental, we had also today a beautiful presentation by Giorgio Sonnino. Giorgio was here with us in conclusion. He presented a work which we did over, I think, 15 years together about not only the Kerr solution, but the Kerr-Newman solution. And we are enjoying the presence of Reinhold Jan Slater here, okay, from Netherlands, which we are trying something enormously exciting, that the Kerr-Newman black hole can be the gate to the quantum aspect of gravitational collapse in black hole. This may be the most advanced topic which we have treated and which is in seed. Well, I would like to continue, but I would like also to conclude. And we have a great fortune to have so many people, and we decided to inform. I have the Minister of Research every day. We have recorded all the lecture, and we have sent to the Minister of Research, to the Foreign Minister every day, to the Minister of the Planning of the Economy, copy of all the publication, of all the registration. I think, and then just to make sure, we also put in copy the President of Republic of Italy, not in first, but in copy. We are sensibilizing the Italian people about the frontiers of general relativity. But the frontiers now are really revolutionary. It's not the tale of looking at a small effect. It's the fact that we have identified, thanks to the collaboration with the Russian colleague from IKI, the evidence that that matter, which is in the galactic center of 10 to the 7 solar mass black hole, is form of dark matter and not of baryonic matter. We have proved this in the last few days. It's a great, we will write and everybody will appreciate. But the next frontier, of course, is to enjoy this new understanding of 50% of the matter in the universe. The X-fermion of dark matter and the fermion characterizing the normal baryonic matter. This is the real moment and extremely beautiful because the synthesis comes from this shock which was presented in Lausanne. The astronomer start to speak about egg and chicken. We were assuming that black hole end only at the end of the universe. And instead, we find out that black holes of much bigger mass of dark matter exist in the first early phases of the universe. And they are huge, 10 to the 6 solar masses. And we can verify this with these data which were presented here for the first time of the data from the galactic center and the X-ray emission from the galactic center. This will be one of the major results of this meeting. And of course, now the situation is open because every moment here, every day, something happened. Even today, we had the fortune to have Reinhard Jan Slater to bring the possibility that even the field of Kerr-Newman black hole could represent the bridge to quantum physics in general relativity. But again, it's a magic moment. I hope very much that the people who listen and the minister will take occasion of these great discoveries. Of course, in all this, we were pleased with historical anecdote. And for example, this time in which Claudio Teitelbaum, by accident mentioned yesterday, went with me to meet the president of Israel, Weizmann, who had the same family name of his mother. And even in this, Claudio came to Pescara, to ICRANet, and from our activity had the idea of start a new center in Valdivia, similar to us, Pescara with Rome and Valdivia with its capital. And we sent him an invitation to open a ICRANet center in Valdivia. But at the same time, we had the pleasure of having many new universities asking to join ICRANet. There are a remarkable number, The one more close to us, on which we count very much to collaborate, is the University d'Annunzio, very close by, who apply to be member. They are already member of ICRA, and Wang Yu is the president of ICRA, but they have also applied today to become member of ICRANet. But at the same time, two other universities have applied. One from Israel and one from Iran. This is the hope, to bring to ICRANet serenity, peace, and great scientific adventure. To work in discovering the universe in peace and in competition of scientific work. That is the most noble, nobile action that ICRANet wants to propagate and promote. And I count on all of you, also on you and everybody, to participate in this continuing adventure. And you can see on the you can see all the presentation, which will be eventually later also appearing in a book. But what more important, thanks to the people, the technical people who have helped us a lot, we have broadcasted in China, in US, in Italy, these activities. Everybody can go on the website and see the presentation and enjoy and participate in bringing this message farther and farther and farther. Thank you for coming.
Let's also thank all the organizers, in particular Remo Ruffini, of course, Remo Shagin, who has been working on the background, and everybody who has worked in the background here as well. So thanks a lot to the organizers as well.
And everybody, we are not many, but with few people in ICRANet, we do a lot. And we count on your connection and participation over the next year. The latest in Hong Kong for Kirby, the next watchman. By the way, I want to make sure to mention that this we have patented this logo, and as a difference from this one, we have patented today. It has a black dot here in the middle. And the reason is that we have discovered finally in ERP 220101, we have discovered